Announcement. There's women's lunches happening this lunchtime, so please go if you wish. But now I have a very serious matter to inform you about. We have this extraordinary meeting because the publicity chairs have some comments to make about the peer reviewing process.
Good morning, everyone. Across all academic disciplines, people have very strongly held beliefs about the peer review process, and I think programming languages is no exception. And we like to share some of our views on this process with you.
Since we're in London, home of Charles Dickens, Oliver Twist, the birthplace of Lionel Bart, who wrote the musical Oliver, which has the song Reviewing the Situation, we'd like to present reviewing for publication. Lend us your ear once again.
It's that time of year once again, when you're handed a pile of manuscripts 7 feet tall,
and given just over a fortnight to study them all.
I'm reviewing for publication. It's a noble task and one I mustn't shirk.
There's no time for equivocation. I must form a quick decision on this work.
Well, it lacks important references,
has strange linguistic preferences.
The abstract goes on much too long.
The contributions aren't that strong.
A firm reject.
But oh, look here.
It cites our paper from last year. I think I'd better think it out again. I'll get with my task. Somebody,
who can I ask? Nobody.
All our dearest companions complain that they're so overworked. If I were to ask them to write my review, they'd be irked.
I'm reviewing for publication at a venue that's prestigious and well known.
You'll be seeing no delegation. I'll be writing this review all on my own.
Well, this manuscript seems suitable.
Its impact indisputable.
Its theorems irrefutable.
And every proof is scrutable.
A strong accept this work demands.
But is that font there Comic Sans? I think I'd better think it out again. Well, now I have done 70
and not yet begun 70.
So I'm half the way through my gargantuan reviewing load.
I'm wondering whether I'll ever leave reviewing mode. We're reviewing for publication, and we hold someone's career in our hands.
I must write a justification using language the committee understands.
Well, this data isn't usable.
Those typos inexcusable.
These figures drawn in MS Paint.
Those error bars are much too faint.
I've had enough, the standard's low. I'll take my money and I'll go.
What's that? Reviewers get no pay.
Well, next year we'll be sure to say, I think I'd better think it out again. Hey!
Thank you to the publicity chairs for that amazing start of the day. It is now my pleasure to introduce the next speaker. Nate Foster, many of you know and saw in the business meeting yesterday, he is the recipient of the Milner Award 2023. I will say a little bit about him, even though he needs no introduction. He did his bachelor at Williams College, he did an MPhil in Cambridge, and then went on doing a PhD with Benjamin Pierce at the University of Pennsylvania. After a postdoc at Princeton with Jen Rexford, he has been a professor at Cornell and a central figure in our department, where I'm now honored to be his colleague and his next-door office neighbor. Today, he is going to tell us about the network is the computer. Nate has done fundamental contributions in programming languages in different areas of programming languages, but he has also done many, many contributions in networking, and he's also a central figure in the CCOM community. So it is my great pleasure to let Nate tell us about the network is the computer.
Thank you for the very kind introduction. What Alexandra didn't say is if you have her as your next door office mate, your coffee consumption will go way up because she'll go down to the coffee shop and bring you coffee pretty much 2 or 3 times a day. Great. So I want to talk about networks, but this is POPL, so we should talk about some principles as well. If we can advance the slides. We should talk about some principles. So I was reflecting on kind of what are some of the big principles that have guided programming languages over the last 50, 60, 70 years. And I think you can distill it down to a few big ideas. So one is, of course, abstraction. The idea that our field is about finding sort of the right or elegant building blocks for expressing computation. And this is captured well in, I think, Backus's famous Turing Award speech, where he advocated for a shift to functional programming because not only do they simplify programs, but they allow you to define new abstractions, which is very powerful. Another big principle is modularity. Liskov, of course, spent much of her career working on modularity. So the idea is that we have really big programs. We're not going to make them robust if we have to think about every detail all the time. We want to have ways of breaking down big programs into small programs, of encapsulating complexity, and then reasoning across interfaces. And another principle is precision. One difference that computer science has compared to other disciplines is we can analytically derive exactly the meaning of programs from their text. And work by Hoare and everyone who works on program logics and verification is driven by this insight. So what about networking? Well, networking is also based on many of the same principles. It's maybe not too surprising because computer science used to be a really small community, and there weren't these kind of strict boundaries between areas like we have today. In fact, I learned this week that one of Phil Wadler's first jobs was writing code for Vint Cerf, who's sort of one of the founders of the internet. So there, abstraction is also very important. And if you go back and read the papers about, say, the internet protocols, when Vint Cerf and Bob Kahn were developing the structure of the internet, they were thinking about abstraction. So they were thinking about how they wanted to find the right building blocks that would let applications be built on top of the network, and also deal with all kinds of variation in things like packet sizing and failures and so on. Modularity is also important. Here I didn't pick a historical paper, but there's a wonderful CACM article by James McCauley, Scott Schenker, and George Varghese that talks about the essential simplicity of the internet's architecture. And they call out modularity as one of the big benefits. And again, the way that these protocols were designed, ideas like layering, have allowed innovation to happen all across networks. So the network infrastructure gets to focus on better support for what the internet does, which is best effort packet delivery. And applications can think about all the rich services that they can build on top of that model. And these things are not really coupled, which allows them to proceed sort of independently. And then there's precision. I called this precision-ish because I think it's fair to say that formal methods and precise reasoning has not been the way that networking has been driven over most of its history. That's not to say there's none. There are, of course, some great examples of formal methods, even in very early networking. But by and large, network protocols and the internet community have been driven by this slogan. They do have to agree on certain functionality, captured in things like RFCs, but they tend to follow what they call rough consensus in running code. So when they define a protocol, they don't spell out every last detail. They achieve this sort of level of rough consensus, and then they declare success when they can have different implementations that can interoperate. Okay, so there are some similarities between these two communities, but also some differences. And I wanted to just do a little example to kind of illustrate how the network designs and these principles of abstraction, modularity, and precision have played out. So let's imagine that we're building some kind of service, maybe to stream videos over the internet. I don't want to get sued, so let's call it Netflix. And the basic operation of this is going to work, building on the internet. So the beauty of the internet is I don't need to, go talk to every ISP and every cloud provider to build this. I can just stand up a server that has the videos I'm going to sell to customers, and then register a name, and my customers can reach me. Right? So we all know this story. And under the covers, there's of course a lot that goes on. So my customers might be accessing their network over a Wi-Fi router, and then they go maybe to some bigger router. On the server side, there's probably some kind of fast wired connection talking over a NIC. And again, the kind of abstractions and modularity that the internet gives, you've probably all seen a picture like this in an undergrad networking class. At the top level, I build this service that maybe provides some streaming video protocol, and my packets kind of go down through the layers, each doing their own job and then flowing back up. So it kind of works beautifully. Or does it? If my service is successful, I'm probably going to get some more customers, maybe a lot more customers. And so pretty soon, just having sort of one box parked at Netflix.com is not going to be enough. I'm going to have to build more boxes, maybe even have data centers, maybe several data centers. And so now I've got this problem that I've got all these customers who want to watch my videos and have them be fast and high quality and so on. And I've got all these servers that are hosting probably replicas of all the videos that I'm serving. And now I need to somehow get the network to steer the customers or their eyeballs to the right servers and vice versa. So what do I do? Well, first, the most common design would be to introduce an appliance called a load balancer. So this is something that kind of goes against the original elegance of the internet's design, because it's kind of, in many cases, cutting across layers and trying to divide traffic amongst the possibly hundreds or thousands of servers in each data center. I also need to find ways to spread the load coming from my customers, also optimizing for things like congestion and latency. And so I'll use some techniques to do load balancing on their side as well. I might use DNS, sort of a souped up DNS server to allow customers to direct their browser to Netflix.com, but then have it actually pick the closest IP address of the data center that I want to go to. I might use BGP to, again, help load balance or pick the best paths getting to those data centers. And if I'm really getting serious, I might even have what's called a content delivery network to cache the most popular videos close to the customers, so they actually don't have to even leave their own ISP to get there. Okay, so this is still a cartoon, but somewhat realistic and kind of reflects how these modern web services are built. And if you're me, I don't know, I kind of find this a bit of a horror. It's gotten very complex, and it's not an edge case, right? There's lots. Video is very important, and there's lots of services that need something beyond what the internet provides. So, stepping back, I think it's clear that networks have been a huge success, right? Pretty much all modern systems depend on networks in some way. We don't, send software around in floppy disks. We use our phones. We power data centers, machine learning. All of these are enabled by networks. But in the SIGCOMM community, there's a growing sense that the internet architecture and I'll say that the internet architecture and internet protocols have also driven much of the private networks and private protocols that are used just because of the way that network hardware works. And there's a sense that these architectures have kind of gotten ensconced. There's talk of ossification and them being brittle and hard to change. And there's also agreement that some really important considerations were left out of the internet's original design. Back when Cerf and Kahn were designing the internet, they were thinking about problems of internetworking multiple different networks, and they weren't so concerned about things like security, and they also weren't really thinking about extensibility, which today are very important. Okay, so I want to talk about an alternate history. What if we had fused networking and programming languages earlier? So what if networks were just other systems that we could program sort of just like or in similar fashion to computers? Well, so one advantage is, network owners, or more generally, users of networks, might be able to customize the network to suit their needs. And that might simplify building a service like Netflix, where what we don't want is really point-to-point communication, but we want to somehow deliver content stored on many, many servers to many, many customers. We might also be able to start to use ideas from our community, formal methods, to start to reason about network behavior. And in fact, this vision is not really new. I was reading around and looking back at some history, and actually one of the first articulations of this idea that I was able to find was from a POPL paper from more than 40 years ago, from POPL'22. So David Wall, who was then at Penn State, had this paper on messages as active agents, and he was thinking about how you express network algorithms, sort of basic routing algorithms and so on, and had the observation that you can sort of write these algorithms from two perspectives. You can write it from the perspective of each individual router, or you can write it from the perspective of the packets or messages that are traversing the network. And this was a sort of inspired idea, but I think if we had taken it seriously, we might have ended up in a very different place, which would have some benefits. And more broadly, there has been a long effort spanning multiple decades to try to make networks more extensible and more programmable. I put Wall's paper back in the 80s. There were a bunch of different protocols and approaches that kind of rose in prominence and then fizzled out. So there was a technology called ATM, started in the mid-80s and kind of rose to prominence in the 90s, that was being pushed by a bunch of telcos and ISPs. There was a major effort funded by DARPA in active networks. I think some people even in this community worked on that. So there, the idea was to really take Wall's vision and make it practical. So to have packets that would carry programs, and you could customize the behavior of routers by sending special packets that would set up certain paths or create different services. And then later in the early 2000s, as things like cloud computing and virtual machines and such became very prominent, the challenges of managing those networks led a bunch of folks to propose what's now called software-defined networking. And they were thinking about new ways of organizing kind of top-down control of private networks. And then what I'll talk about today is, again, about a decade later, there were some folks who thought about designing network hardware that could be customized using a DSL called P4. So you might take a skeptical view and wonder, if people have been proposing these programmable networks for decades, and I didn't show this, but really, each one has kind of gotten some initial excitement, some hype, and then really fizzled out. What's different this time? And I think there's a couple of things that are really different and mean that these efforts won't fizzle. So one is that there are true kind of pulls from applications needing services and functionality that goes beyond the basic internet model of best effort packet delivery. Some of these are related to network management. A lot of the early SDN work, for example, was motivated by the challenges of trying to make a big network like in an ISP or a cloud provider. Trying to keep that network working is really hard if you have to express everything in terms of fully distributed protocols. There's also new services. So network virtualization was one of the big drivers of SDN. And there's also certain applications or certain functions that have become very important for reasons of performance or functionality. So traffic engineering, being able to monitor the network to understand what's going on, and increasingly security. So there's things like, if you've heard the buzzword zero trust, at the network layer, this turns into networks that basically set up and tear down forwarding paths based on some kind of policy and authorization. So that all of this requires the ability to modify the network at pretty fine timescales. There's also some things that I think are coming from the bottom up. So I call these pushes, architectural pushes. So one is that Moore's law has really ended for CPUs, and a lot of the ways that people have kind of layered on functionality and services on top of the internet has involved plunking down these special boxes, things like the load balancers or CDNs that I showed in my Netflix example. And until very recently, it's been possible to take a server and get it to process packets at a sort of competitive rate. So you can, for example, get one core to process with lots of tricks about 100 gigs per second of data. But that already requires some heroics, and we're not going to go much further. And meanwhile, the speeds of networks have continued to grow. So 400 gig connections are common now. We're going to 1 terabit, and it's just not going to be possible to do packet processing on CPUs at those rates. There's also, again, these advantages of SDN architecturally of being able to separate concerns, I think is a fundamental idea, and we're not going back for that. And then third, as Moore's law has ended, a lot of hardware designers have started to take devices that were traditionally not very programmable, so things like routers and switches and network cards, and think about how you could build some domain-specific hardware that would still be programmable so that they can host more applications. Okay, so in this talk, what I want to do is, it's not going to be a very kind of programming language talk in the sense that there won't be, denotational semantics or program logics or lots of theorems, but I want to show you some examples of how we can rethink the foundations of networking by taking more of a language-based approach. So we can use networks that are programmable to make them more extensible and to do better reasoning about them, and generally to kind of unblock networks from the current sort of state of ossification that they're in. Okay, so to start, let me tell you a little bit about some of the abstractions that I and many others have been working on for the last 6 or 7 years. And the vision here is really to kind of nudge the community out of its current way of developing new functionality and new protocols. So again, going back to Clark's quote about rough consensus and running code, for many years, the way that if you have some new idea about some new protocol that you want to have supported in a network, the way you do it is, well, first you do some design and prototyping, probably just with yourself, and then you take it to the IETF, right? And you propose a new protocol in an RFC document, and you go through a social process to convince others that it's a good idea, incorporate their ideas, and write it down in some kind of document. So that process takes, sometimes 6 months, sometimes 3 years, sometimes more than 3 years. And then you can then go to vendors and say, okay, I've got an RFC, and look at all these other people who want this functionality, and then you try to convince them to add support for that protocol into their device. And that takes, in the best case, a couple of years, maybe more. And this is not just a story. Like when software-defined networking first became really big, and one of the big uses was network virtualization, VMware wanted to add a new tag, something called VXLAN, to give them sort of more control over how their virtual networks were being implemented. And they experienced about a 5-year delay from having the desire for that feature to having it be supported on, I believe, Cisco routers. So that's just a very slow process. And so what we'd like to be able to do is, instead of having to go through all these rigmarole, to basically just be able to write a program and get that protocol running in a production setting right away. So before I tell you a bit about the P4 language, let me just set some terminology. I won't be talking too much about control planes or sort of the software-defined networking side of things, although it's very important. But I just wanted to sort of set terms and remind you that networks really have sort of algorithms that run at 2 levels. So the one that you probably focus on the most, say in an undergrad class, is the control plane protocols. So these are the protocols that do things like learn the topology of the network, compute shortest paths or spanning trees or other paths through the network. And they're also responsible for managing policy, things like security policies and firewalls and so on. And then the control plane communicates with the data plane, which is the piece of the network that runs the forwarding algorithms. So these algorithms are different. They're really functions on packets, and they are responsible for performing lookups in routing tables, keeping track of usage through things like counters and other accounting mechanisms, and increasingly also doing some limited forms of stateful processing. And I'm going to focus on the data plane here. So at the hardware level, because sort of Moore's law has ended, the way that most data planes are organized is in terms of some kind of pipeline. So this is a different kind of processor than what you probably have inside your laptop or a server. It's really designed for throughput. So the idea is that packets come in, and they go through some number of steps of processing, and then they go out. And so there's no possibility of stalling. You don't really ever visit the pipeline multiple times. And also the program, instead of being a thing that's sort of traversed and fetched like in a binomial model, here the program literally gets loaded into the pipeline. So your program sort of gets sliced up, lowered into the pipeline, and you execute it in one pass as you go through. More generally, the sort of high-level steps of processing that you do in one of these pipelines is first you take bits coming in off of some line card or wire, and you parse those bits into some kind of structured representation. Maybe you're parsing out standard protocols like Ethernet and IP and TCP. And then you do some processing on that typed representation. So you might do lookups in some routing table like I've shown here. You can do other things as well. And then finally, you deparse the structured representation back into bits and apply whatever effect has been computed, so forwarding the packet or dropping it or something else. So the P4 language, which I've been working on for the last 6 or 7 years, is a language that's really a DSL for these kinds of pipelines. And historically, these pipelines were not programmable or not very programmable. They would implement the protocols that are in the internet standards. So different hardware vendors had different ways of doing that, but essentially there'd be some units devoted to IP and some units devoted to access control and some units devoted to other protocols. But P4 was anticipating a class of these routers where instead of having dedicated units for different protocols, you just have a bunch of memories and arithmetic units and hashing units and other things, and you can then program it to implement whatever protocols you like. So in terms of language design, you can think of this as being pretty similar to sort of the data flow paradigm, but of course it has some network-specific features. So first and most important, these pipelines are restricted. So you typically don't have a memory, or any memory you have is a finite size and very small. So you're not going to support operations like malloc or things that can't fit into some statically allocated memory. And also, although it's possible, of course, to visit the pipeline many times with a single packet, it's easy to see that that will greatly hurt your throughput, right? So if every packet's visiting twice, then your throughput gets cut in half. And if it's 3 times, 1/3, and so on. So generally speaking, visiting the pipeline many times is not something that's done. And so if you want to think about a programming model for those devices, it probably makes sense for that language to be restricted in some way so that you can't accidentally write a loop or something that would kill performance. The other features of this language are, the bread and butter of packet processing is manipulating low-level bits. And not just things like, not the sort of normal types of things you use in a language like C, but some protocols have 1-bit fields. So the language has a bunch of types and other features, a rich collection of numerics, a bunch of operations that make that kind of low-level bit wrangling more convenient. And then the third thing is, the data plane is one piece of the puzzle. There's also a control plane. And so there's an important interface between the data plane and the control plane. Namely, the control plane needs to be able to reconfigure the data plane by changing the entries in routing tables or access control lists and so on. And if you're making this programmable, you need some way to decide what that interface is going to be. So P4 has a piece of the language that's devoted to explaining how the control plane can reconfigure the behavior of the data plane. I'm not going to take you through the language kind of piece by piece because really, if you understand those three kind of high-level ideas, there's not much more to it. It's an imperative language. It's got low-level bit wrangling stuff. It's got some elements that are control plane programmable, and that's it. But to give you a sense of what programs tend to look like, this is kind of this is sort of a hello world example from 50,000 feet. On the left, you see that most programs actually start with some description of what we call the architecture. And that's because P4 is really a family of languages. We use P4 for programming network cards. We use it for programming routers. And each of those does their work in a different way. And so what the architecture does is it lets us factor out the differences between different kinds of hardware, giving just the shape of the pipeline, and if the device allows some other operation, has some built-in functionality, we can expose those in the architecture and use them. So that's what's here on the left. And then on the right is the program that we write. And basically, there's going to be one chunk of code for each of the sort of holes in the architecture. So most architectures have sort of a number of P4 programmable blocks, and the code you're writing is ultimately determining what code goes in those blocks. And so a typical program would have a whole bunch of type definitions because P4 doesn't bake in any of the standard protocols. You have to define them yourselves. And then we'd write parsers for those types. And again, these could be standard parsers or they could be custom parsers. And then you write what P4 calls controls for control flow, where you explain how to sort of string together different processing blocks together to get the end-to-end program. So very quickly, just tell you about the impact of P4. It's been around, actually, the language has been around for about 10 years. So Dave Walker and Jen Rexford and Nick McEwen and a bunch of other people proposed a first version around 2013 or 2014. And then there was a second version done about 3 or 4 years later called P416. And it's had quite a bit of impact in industry. So there's, by now, P4 support on most of the different classes of network devices that you could imagine. So switches, some devices that are called smart NICs. So these are network interface cards that are programmable and have some processing engines on them as well. Just in the last 2 years, there's been support added to the Linux kernel. So you can write P4 code and have it run in the kernel. There's support for doing processing relatively efficiently in user space in a framework called DPDK. And kind of closest to my heart, there's also a growing community, including folks at Google and Microsoft, who are using P4 not so much for programming the behavior of devices, but actually as a specification language. So they're using it to drive testing and validation, and also just to kind of move their specifications of different APIs and functionality into a mechanizable, precise form. In terms of the research community, P4 has become, I think it's fair to say, the way that the SIGCOMM community expresses innovative ideas. Certainly, if it has to do with sort of protocol design or packet processing systems. I did a count last year. I haven't done it for this year, but last year, fully 30% of the papers at POPL'22 used P4 in some central way. So I discounted papers that just cited P4, but these were papers that were using P4 as a modeling language or a programming language for developing their system, which is a pretty big fraction. And then sort of at the intellectual level, you might wonder, well, what are people doing with this language? And there's a growing collection of what you might call in-network processing or in-network services. And some of these are kind of wild ideas that will probably never see the light of day. But some of them I think are fundamental. So people are thinking about networks that can do caching or data replication and where that logic is expressed in P4. There's also folks building different distributed services, so a consensus protocol or a distributed locking service that can be made faster or have sort of different characteristics if you realize it in the network. There's been some work on accelerating things like database transactions using support from the network. There's some work on runtime verification, so building networks that can check their behavior against a specification. And a lot of work on kind of core topics like congestion control. So historically, congestion control works by, when a packet is dropped, the senders will adjust their sending rates and such to avoid congestion. But you can also, of course, use the network to explicitly keep track of when congestion is about to occur or has occurred. And people have used P4 for that kind of monitoring as well. OK, so let me jump down back into an example. This isn't exactly the Netflix example, but it's maybe a little bit inspired by that. Just to kind of think about how we might use a programmable network, in particular a programmable data plane, to implement some new abstraction, let's try a totally different forwarding abstraction than what the internet provides. And that is, we'll allow the receivers to subscribe to a stream of sort of published data. So on the left here, you have the data publisher. So they're going to publish a stream with some format. And on the right, you have the consumers. And of course, if all we're doing is sending the same data to everyone, this is not so interesting. But now suppose that there's either multiple streams being composed together, or the receivers only wish to receive certain kinds of data. How can we build a network that provides that service? And to make it really concrete, this is the kind of thing that happens in the finance industry all the time. The exchanges publish a feed containing the orders that are going through the exchange. And they have a protocol called MOLD that they use for doing that. It sort of puts together information about multiple symbols into a single message. And then the hosts that are potentially doing things like trying to get a view of what the exchange is, what the market has, or maybe implementing certain trading strategies, they may be interested only in a subset of the data coming from the exchange. So what we'd like is for these hosts to be able to sort of register queries, much like in a pub-sub kind of system, and the network will deliver to them just the messages that satisfy those queries. So if my host is only interested in Microsoft and their stock price, I'm not going to have to get and filter and discard any packets that have to do with other symbols. So to do this, we're basically going to take this abstraction and realize it in an in-network computing system. This is kind of the architecture of the system. So on the left, the publisher is going to have to tell us about sort of what the types of the data in the streams are. We call this the header specification. And then the subscribers are going to repeatedly tell us what queries they want, what packets they want to get from that stream. And we're going to put this into a compiler. It's going to sort of chop these subscriptions up relative to the header specifications, and then push it down into the network in order to deliver, again, just the messages that the subscribers want. I'm not going to talk about this today, but there's a whole interesting question about how you design the network topology and things like broadcast trees to minimize congestion. That's in the journal version of this paper, but I'm not going to cover that today. So if you're interested in that part, it's indeed very interesting and fun, but out of scope for this talk. So let me focus on the language that we use to describe subscriptions. This is nothing deep here. It's really just sort of predicates. So the subscribers can express predicates that are evaluated over the stream of messages. And it includes the obvious things. You can look at the values of certain header fields in the stream. You can compare it to constants. There is one thing that's a little bit interesting, which is we allow you to also express queries in terms of aggregates. So you can, for example, ask about the average value of maybe a bunch of historical terms, and that aggregate will be maintained by the network switches, and then you can use the current value at each moment in time to compare against the element of the stream. So it's a little bit more than just sort of naively predicates on packets, but not much more. Okay, so how are we going to realize this in a programmable data plane? Well, ultimately what we need to do is we're going to assume that sort of every switch receives anything in the stream that's relevant to the downstream subscribers. And then we want to filter the outgoing stream so that it just has the data that's going to the subscribers. And furthermore, we want to send the output streams going out each port on the switch to the right host. So the way we do this, building on some work from actually an ICFP paper that my group did for compiling SDN policies, is to use a kind of decision tree like binary decision diagrams, but with forwarding decisions that leaves. We call these FDDs. And so we can take a set of queries, one for each subscriber, and turn this into a tree. So in this tree, you see there's predicates corresponding to sort of atomic tests we can do on individual packets. And then at the leaves, we have sets of output ports corresponding to the subscribers that should receive that. And once we have this kind of tree, we can chop it up. So we do this for reasons of efficiency, to be able to turn the evaluation of this predicate into a pipeline. And then we decorate the tree with some additional values to keep track of where we are. And then we can basically evaluate this predicate in a pipeline of tables where each table checks sort of just one match condition. So in this example, just checking the price or just checking the shares. Okay, so pretty simple. And if you saw, earlier work in ICFP or POPL on sort of SDN programming, it's not that dissimilar. The difference is here we get to define the formats of the packets and of these tables, and we can use that to build this service. So does this actually work? Here's a couple of graphs just to show you the benefits from an empirical network perspective. So this first graph just is sort of a baseline showing you the sort of obvious way to build this kind of system would be you broadcast the stream to everyone and then let the hosts filter whatever they want. And for this experiment, we used a kind of reasonable proxy for the selectivity of the filter that you'd want. I think it was keeping some fairly low percentage of the packets. And there's two plots here showing, or two lines here showing two different packet rates. So the red line is 1 million packets per second, which sounds a lot, but it's not that much. And the green line is 8.25 million packets per second. And this is a CDF of latency. So the closer you are to the upper left, the better. So the red line is basically reasonably smooth and low latency for all the packets. But what you see is that when the data rate goes high enough, because the CPU can't keep up, we start to get queuing and congestion and things slow down. And so here, the latency, especially the so-called tail latency, there are some packets that experience 250 milliseconds of microseconds of delay, which is bad. So here's another graph that shows the same kind of plot. Sorry, the colors mean different things now. But the red, again, is the baseline. So that's that naive, what you would build today with just the internet protocols. Broadcast things everywhere and then filter at the edge. And you see, again, that the tail latency is not so good. And the green is what you get if you can offload some of this filtering work to the switches. And so, in particular, the worst case, it's not perfect. So there's still some filtering that has to be done on the hosts because the switches can't always exactly filter what's needed due to resource constraints and so on. But still, the bulk of the work is being done on the switches, and so we get a much better latency curve. OK, so that's just a taste of kind of what you could do, the new kinds of services you could imagine if you had abstractions that let you customize the network to have more than just basic best effort packet delivery. So next I want to turn to how are we going to build these programs? How do we do this from a PL perspective? And whatever you think of this P4 DSL, it has the property that it's tightly coupled to architectures. So when you write a P4 program, you program the whole shebang. You have to program the entire pipeline. And there's really no support for having multiple programs running side by side. And in code, what this looks like is a typical P4 program, if it's trying to do something reasonably complex, ends up sort of mixing and matching functionality from what intellectually are sort of different pieces. So this is a snippet from a program called switch.p4. This is meant to kind of capture modern data center switch and all the functions it would provide. It has about 45 different protocols. And what you see is this is just one table that does layer 3 rewriting. And what you see is there's a whole bunch of code snippets that have to do with IPv4 processing versus IPv6 processing versus MPLS processing. And they're all mixed together. I've colored them here, but in practice, they're just enabled or disabled by preprocessor flags. And it's kind of a mess. So another thing you can imagine doing is trying to design some abstractions that maybe would still have the essence of P4. So they'd still be a low-level data flow-ish language with bit manipulation and control flow APIs and restricted computation, but try to allow ourselves to write these complicated programs in a more modular way. So in a paper at SIGCOMM a couple years ago, we proposed what we called micro P4. And the idea was really just to do what I said. So we wanted to have the ability to compose these pipelines. And to do that, we had to decouple the pipelines from the hardware. So we proposed this idea of sort of a logical pipeline, which has an input buffer, an output buffer, and then a very simple 3-stage parse, process, deparse pipeline or mini pipeline in the middle. And the reason for this design, of course, is that, and sorry, my lines are not displaying quite like I expected. There's supposed to be an arrow going from that output buffer to the input buffer, but it's very light, so you can't see it. But essentially, you can take these pipelines and string them together in sequence or in parallel with conditionals. This also works if you have things like multicast or packet cloning going on. And basically what you can do is you can build these assemblies of smaller pipelines and therefore decompose and encapsulate the processing for individual protocols into separate programs. Oh, sorry, it's my animation, not the, not the slide. Sorry about that. Okay, so the key challenge, of course, is this abstraction makes sense. I think it's probably what many of you would have thought of if you were presented with this problem. The hard part is, how do we actually compile these things? And so the micro P4 compiler, what it does is, essentially it converts all of the different small pipelines, the mini pipelines, into a homogeneous representation. And it does this because all of the targets that are available today, they can only do parsing typically at the beginning of the pipeline. So it won't be possible to kind of do some processing and then go back and parse again. And so the strategy we used for implementing these ensemble programs was do all of the parsing at the beginning. So we need to parse deep enough into the packet to grab any of the data that we might need for one of these pipelines. But instead of populating any specific data structure, we keep it in a kind of generic sequence of bytes. And then when we do parsing in the individual pipelines, we turn those into just ordinary P4 controls that implement parsing by copying data into different headers and other data types. So in pictures, an individual pipeline might express parsing in terms of this kind of state machine. That's how P4 expresses parsing. And we're going to turn this into a sequence of these lookup tables where in each phase, we're going to capture both the control flow of the state machine and also its effects. So moving data in and out of data structures and then transitioning to the next state. So it sounds a little crazy if you're a hardware person, but does it work? So here's one of the evaluations that we did. We took as a challenge writing a modular router. So a router with support for these, I think there's 8 or 9 different protocols. And then we kind of assembled them into different specialized routers. So for example, this router supports just IPv6, P1, whereas this router supports IPv4 and IPv6. And we compiled these programs. We ran them on 2 different targets, one a software simulator and one an honest-to-God hardware switch. And then we looked at how much does this cost? So our compiler is not perfect, of course. There is some overhead to doing things this way. But if you look at the critical resource, which is how many hardware stages are required to implement these programs, and do we exceed the maximum number of stages that are available on today's routers? The answer was no. So we were able, there is some increase. In some cases, it's a significant increase, 2x or even a little bit more. But you can fit these programs into, again, a modern hardware switch. So I think this is, again, a kind of simple idea, but it shows you what becomes possible if you, take ideas from programming languages, make the lowest layers of the data plane programmable, and then start to think about building other abstractions on top. Okay, so in the third part of the talk, I want to talk now about reasoning, or precision. And there's this vision that I think a lot of people have. I even heard it in one of the workshops before POPL, that really with all the technology we have in formal methods today, we should get away from RFCs that mostly have ASCII art and English prose. And we should have these executable specifications of protocols that we can use to verify and to drive validation of implementations. In fact, this is starting to happen. So this is a slide from my former PhD student, Stefan Smolka's switch V talk at SIGCOMM. So Stefan now leads a team at Google that's doing validation of their data center switches. And their switches are not programmable. So they're not using Intel Tofino switches. And if you look at the total software that runs on a switch, it's pretty huge. So there's the chip at the bottom. There's a version of Linux. There's a bunch of other layers that implement different control plane APIs. It's pretty big. But if you look at what it actually does, it's pretty simple, right? Google doesn't need all 45 protocols that a stock switch from Cisco would give you. They only use a small handful. And they're doing SDN, so their control plane API is also pretty simple. And so Stefan's insight was, we could model this complex on the left as just a maybe 1,000-line P4 program. And it would actually capture both the data plane behavior of these some small number of protocols, as well as the control plane behavior. And we could use this to drive testing. So this is one of the uses of P4 has been as sort of a precise, mechanizable spec language for either devices, or you could also imagine doing this with protocols. So what I want to talk about is, what would be some of the things you could do that are maybe new and domain specific if you want to do this kind of reasoning about P4 programs. And I'm a little short on time, so I'm going to focus on just one aspect of a P4 program, which is sort of the hairiest aspect, which is how do you parse packets. And as an example, I'm going to take a parser for a stripped down, this is not like industrial code or anything, this is just a sort of a cartoon example for to show the ideas, where we're parsing something called MPLS, which is a kind of tunneling header that's used by ISPs, and then there's also a UDP header that can follow. So the point of this parser, expressed here as a kind of state machine, is we can parse some number of these MPLS records from the packet, and then we can parse the UDP header, which follows. And the way this works is MPLS uses a flag in the 23rd bit of each record to say when it's done. So right here, the fact that there's a 1 in the binary representation right here means this was the last record. And then it proceeds to the second state where UDP is parsed. Okay, so pretty simple example. Now, one of the things that happens if you want to run this kind of parser, say on a programmable switch, is the parser is one of the key resources that you need to write your program in a way so that it can kind of parse enough data out of the packet, or you won't be able to keep up with the line rate of the switch. If you write a parser that parses a bit at a time, it's going to be too slow. So what the compiler does is it basically tries to sort of vectorize your code. So it tries to unroll loops. It tries to make each step of processing be wider so that it can fully utilize the amount of bandwidth that's available on that parser. So this kind of unrolling is the kind of thing that the compiler, in fact, does. And so here, if you read carefully, what's going on is, on the right, the first state is actually extracting 2 MPLS records at a time. And so it's grabbing data from the wire twice as fast. Now, in the case where we have an even number of MPLS records, that's fine, right? If we just parse 2 at a time, when we're done, we go parse the UDP and then succeed. But there's this other case, of course, where we had an odd number of records, and so we parsed the last MPLS record and then realized that we'd parsed sort of some of the UDP header already, but we did it in this first state. And so the new variable here, the second record that we parsed, actually contains UDP data. And so we have to add this state here to basically fix up that mistake. We can recover from that mistake. We parse the rest of the UDP header, and then we concatenate the header that we thought was MPLS but is actually UDP together, and we end up in the same state. Okay, so these two programs can be considered equivalent, and the goal of this work that we did at PLDI a couple years ago was to do that. And the way that we did this was to actually define a language, we call it P4A, which is not literally P4's syntax for writing down packet parsers, but it's very close. And we're going to interpret it as just an ordinary kind of regular automaton. In the interest of time, I won't read through this, but this is just a notation for expressing these state machines where you can do effectual operations in some of the states, like extracting bits out of the packet. And so the first thing we have to do if we want to reason about these is we have to give them a semantics. And so we do that by essentially interpreting these as a kind of standard automaton. So here, the configuration of these automata is going to have the state we're in, the data that we've parsed so far. So there's a finite store, which corresponds to the header types that we parse in the P4 program. And then for administrative reasons, there's also going to be a buffer, which contains all the bits that we may have read so far, but we're not quite ready to execute one of these operations that actually extracts into some header field. And the final configurations here are going to be the ones where, as usual, the state is accept. And we'll then define transition structure over these configurations pretty much in the obvious way. So if we're in the accept or the reject state, then we'll define the transition function to reject if we try to read any more input. This is sort of just a convention that keeps things clean. Generally, you stop when you're in the accept state and don't go further. And then if we're not in a accept or reject state, then we have to define two different kinds of transitions. So first, there's buffering transitions, where we read one more bit, and then we add that to the buffer, but we stay in the current state. And we do that whenever we don't have enough bits yet to execute the effectful operation associated with that state, like extracting. Second, if we do have enough bits, so if after reading one more bit we have enough to actually take the effect in the state, then we do the operation, which might update the store, we transition to a new state, and then we empty the buffer. Okay, so this may not be the only way you could do things, but it's sort of one way to realize the mechanics of these P4 parsers, which can sort of do arbitrary bit parsing in a clean finite state model. So we'd like to be able to verify these things. And there's, of course, many techniques we could use, but we're going to use bisimulation. So we're going to prove the equivalence of two parsers. One could be the reference parser from an RFC. Another could be the one we've written in a program. Or one could be the program that we've written, and the other could be the output of a compiler, which is supposed to be equivalent. And so to do this, we're going to use the standard notion of bisimulation. Recall that a bisimulation is just a relation on the pairs of configurations that's closed under taking steps, and it only relates final configs to other final configs. So we'll never relate an accept and a reject state. And in fact, we can generalize this a little bit to capture facts about effects as well. For the rest of this talk, to keep things simple, I'm just going to focus on sort of language acceptance. So we're just going to look at, do the two automata reach accept in the same, on the same inputs. But again, you can extend this to do relational verification and reasoning about the effects as well. There's many ways to build a bisimulation. The one that we use in our tool is to basically build bisimulations from above, by which I mean we start by taking all of the bad pairs of configurations. So these are configurations that are final in one machine but not final in the other, indicated here by these skulls. And then we search backwards, finding any pairs of configurations or any states, if you like, that can reach these bad pairs until we're done. And the complement then is the biggest bisimulation. And so if our start configuration is in that complement, then we're happy because, in fact, the two things are equivalent. Now, unfortunately, this doesn't work because the state space is huge, right? As usual, if you just do this naively with concrete structures, you're going to end up stepping through and searching a very, very large space. For our MPLS example, there's 2 to the 128 pairs of possible configs. So we need a better idea. And the one that we used in this work was based on 2 key ingredients. The first is following the work of folks like Laura Stantoni and others to move to symbolic representations of automata and to compute these bisimulations symbolically. So rather than representing explicit pairs of states, we'll use predicates to capture sets of states. And instead of just following transitions in our automata, we're going to do something like computing the weakest precondition of the predicate that we have at each point through this algorithm, through the procedure that each state represents. So you can view this as, instead of working with points, now we can draw these bigger circles and kind of chase backwards into the end as before. So this is pretty good and helps a lot. But there's one more thing, which is, if you recall the way that we were sort of modeling these parsers, we did it by sort of working a bit at a time to fill up a buffer. And then, when the buffer has enough stuff, we take the step and actually move to another state. And so if you were to apply this symbolic weakest precondition approach to these parsers, what you get is you start with a predicate maybe that represents accepting and having nothing left. And then you go backwards to the states that are reachable from that. And then you'd have many, many, many of these sort of buffering steps, each staying in the same state of the state machine, but the configuration is subtly changing. And we'd have to track that in our weakest precondition calculation. And then finally, we would end up with the place where the buffers have enough and we can take the next step. And so it turns out that you can abstract this, you can sort of simplify this and not actually keep track of these individual buffering steps, because at the state machine level, they look very much like this, right? You're sort of taking a step until you fill up the buffer, and then you do something interesting. And so using the idea of up-to techniques from Bonnke and Poos and many others, you can define an up-to technique for these kinds of automata that lets you basically leap over all these administrative states and just get to where the action is, where you actually do something. So we implemented this. We actually wanted to do this in Coq. So we have a library that encodes P4 automata, their syntax and semantics in Coq. And we also built a push-button tactic that calls out to an SMT solver to check the validity of various first-order assertions about these predicates that we have. So the SMT reasoning is not, we don't get any kind of proof certificate for those, but the rest of the proof that either we have a bisimulation or we don't is verified in Coq. And we also verified the soundness of all the intermediate steps that we do as we take our surface language and massage it into the input for the SMT solver. I think I'll skip over, in the interest of time, a little demo, but you can get, well, yeah, I'll skip over the little demo, but it runs and it really is push button. So you just ask it to prove the equivalence and you get back a proof term. Here's one of the examples that we did to verify this. So we took a collection of data center parsers from ANCS paper by Gibb, and we took their compiler. So they have a compiler that takes these state machines and turns them into hardware pipelines. They look like this. And then we built a little back translator that takes the pipelines and re-embeds them as state machines. This is, a translation that we have to trust for the purposes of the final result, but it's a very simple translation that basically just turns this kind of table pipeline back into a state machine. And then we checked if the programmer-written state machine and the one gotten from the compiler with this back translation are equivalent. And we're able to do this for several realistic data center parsers. OK, so I wanted to step back and just kind of reflect on, there's probably been a whirlwind of sort of different topics and thinking about how programming languages and networks can go together. I'm someone who, in my career, has not stayed put. I guess, following in the footsteps of some of my advisors, people like Benjamin Pierce and Mike Gordon and others, I've been very curious about thinking how programming language ideas could be relevant in new areas. And I don't know what you do, but when I teach programming language to undergrads, I tell them, even if you have no interest in lambda calculus or semantics or things like this, you're going to go off and do systems or machine learning or computer vision, you're going to find that there's little programming languages problems everywhere. And I think this is actually true. The ideas that our community works on are really fundamental. And thinking about these things not just as kind of informal, hand-wavy principles, but actually backing it up with precise mathematical structures and theorems, that's what's so magical about programming languages. And finding ways where you can take these ideas and really import them or adapt them to new areas is really powerful. Sometimes I feel like I've gone over to the dark side. I've sometimes given talks and people introduce me as, this is Nate, he used to do programming languages, but now he does networking. And I'm not insulted by that. And it is, it's truly a big leap. To really go deep and to understand the problems and methods of another field is a pretty large investment. I found it extremely valuable, right? You can find new problems, and these are problems that have definitions coming from practitioners or other application domains. And sometimes even if their solution is something very simple, compositionality or bisimulations, solving those problems and really finding solutions that really work often leads you to develop some new twist, which can then feed back and give you some new ideas for programming languages. So at least in my work, I've always sought not to just kind of shallowly apply programming languages to some problems in networking, but to keep my eyes open and to look out for where some new method might apply that might be of interest to our community. And the last thing I wanted to say was, there's this kind of common belief that language design is hard, or at least publishing language design papers is hard. And we all know why that is, right? When you're doing a language design, first of all, you have to do the whole shebang, right? You have to figure out the problem area, you have to define the motivation, you have to design the thing, you've got to evaluate it, and there's no benchmarks or programs out there. So you're really kind of out there on your own. And doing this all in one paper, it's hard to fit it all in, it's hard for the reviewers to appreciate it, and so, I think people shy away from it. But I think, what's really special about our community is everything I said. We're precise, we're mathematically rigorous, and so on. But I think, exporting linguistic thinking to other areas or doing designs is the thing that's most adventurous in my mind and most magical. So I wish our community would do more of that, and I encourage us all to think about ways that we can adjust our publication norms and such so that we can incentivize people to do more language design. I'm really short on time, so I'll just say a quick few words about what's next. There's still a lot going on. So there's a lot of interest right now in the network edge, sort of shifting from the fabric itself to things like NICs and edge devices. There's also a lot of interest in performance. So as network verification has matured, sort of the low-hanging fruit was checking that your routers had the right forwarding tables. But now people want to have guarantees about things like performance properties, isolation, latency, bandwidth. And that requires quantitative reasoning, which is, of course, a huge grand challenge for verification. So I expect to see some exciting things in the next 5-10 years coming out of the combination of networking and performance verification. And then third, something I'm especially interested in right now is getting back to this problem of the internet. So everything I've told you today really assumes that you don't have to worry too much about adhering to standards or interoperating with other networks because, I don't know, you're running a data center or you're doing something local to yourself. But the internet remains important, and there are people thinking about new kinds of architectures, new kinds of protocols that could make the internet better, more evolvable, and more secure. And these are challenges that bring on a whole other set of concerns when you're doing things worldwide. So just very briefly, I wanted to thank you all for coming and for, again, POPL''s my home community, so I feel so welcomed to be here. I wanted to thank my mentors who have provided constant support and guidance over the years, and all of my students and collaborators. This is only a subset, but they've really made research really fun. Okay, thank you.
Okay, thank you, Nate, for that wonderful talk. We have a few minutes for questions. There will be a volunteer on this side of the room and on that side, so if you raise your hand, I'll try to get the mic over to you.
Hi, Nate, over there. Yoo-hoo.
It's Peter.
Matthias?
Peter.
Peter Sewell.
Okay.
So this is great. Anything that can tempt the IETF away from rough consensus is an amazing achievement. Most of what you talked about was about expressing in P4 enough for these network components to do their routing or forwarding or filtering jobs. Does the same apply equally to the pretty complex logic you need in the endpoints of higher level protocols, or is that a different game?
Right. So I think the answer, the first answer is no. And I think some people know, Peter had a project, what was it, 15 years ago, net semantics, studying these N-based protocols and all of their complexities as realized by different vendors in this rough consensus and running code world. And there's a whole lot more that goes on, right? There's timers and congestion control loops, and it's much more complicated than what goes on a router. Having said that, I do think that languages like P4 could be one piece of the puzzle. If I had to pick off like one thing that should be a no-brainer for the IETF, it would be, let's not write ASCII art diagrams. Let's have some sort of code description that we can run tests against, and it has a precise semantics. So that wouldn't be the whole protocol, and it might not even be the interesting part of the story from their perspective, but at least then it would lower the bar for doing, for having certain kinds of testing tools at a minimum. If you wanted to prove a theorem, you may still need to do a whole bunch of extra modeling work like your team did. So I don't claim this is the whole story, but I think it could be an important part.
And do you think the IETF could now be brought to appreciate that kind of thing?
Possibly. So there's a group I'm loosely involved with, but a bunch of formal methods people like Ken McMillan and David Basin and others are going to IETF meetings and trying to convince them that they should start to think about formal methods. And the strategy that they've been following is not to sort of say, formalize all the things, because that would be socially probably dumb, but to think about, where are the pieces that are most complicated? So, certain security protocols where, of course, there's already been lots of work by some people in this room on formalizing, security guarantees, or congestion controls, another area where there's a real feeling that sort of maybe Van Jacobson can keep it in his head, but most humans can't keep the details of these congestion control schemes and whether they're fair and whether they converge rapidly to the right values. So there, some tool support could be helpful. And I think that's the right way to go. Find these kind of problems where there's a real need and where the protocol designers are finding that they're either scared or unable to deal with the complexities, and think about how formal methods can help, and then maybe build from there.
Absolutely. Thanks.
Hi, Nate. This was a great talk. Thanks. One thing I wanted to ask is, actually, you mentioned a little on your future work about the quantitative aspects, because I've talked to networking people much less than you, but performance is one of their highest aims, and I thought recently there's been a lot of work on sort of quantitative by simulations and things like that, and I wondered if you had thought about trying to figure out the performance as well as part of the semantics.
So I myself have not worked so much on these things. I had a very brave postdoc, Mina, who's on the slide right there, who had one of these fancy fellowships and decided to work on performance verification herself. So she teamed up with some folks at MIT and Georgia Tech and started to use not quantitative bisimulations, but just using SAT solvers, a tool that could model the sort of adversarial inputs that would break some properties of a congestion control scheme. So that's the sort of early work I was referring to. I do think that, of course, there's been a ton of work in our community and formal methods on things like quantitative reasoning in many forms. And trying to apply that to some problems, I think, would lend some new insights. There would be, of course, lots of challenges to make these things scale and to find the right modeling tricks, what to abstract and what to leave in. But I think that's a very fruitful place to look.
Thanks very much for the excellent talk. With these requests for comment, when people come up with them initially, do they have a well-formed enough idea to be getting formal, or is the looseness of prose kind of useful so that the idea can be bashed about and commented back and forth before maybe investing time in really meticulously working out the detail?
It varies, and I should say I'm not a regular member of the IETF, and I should also just disclaim that I don't bash the IETF. I think what they've accomplished over many decades is truly amazing. So I come humbly as someone who thinks that some of the ideas from our community might be useful, not as someone to saying you're doing your job wrong. I think nowadays, well, let me back up. In the early days of the internet, obviously the IETF was central, and lots of these discussions were developing the design as these things were written. I've only heard stories of some recent protocols like Quick, for example, and some of the congestion control schemes and how those got pushed through the IETF. And often nowadays, at least one model is a company may have, or a group of folks may have already sort of fleshed out a design, and then for various reasons they want to get the IETF stamp of approval. Whether that's to get a vendor to build it, or whether it's to get a raise at their job, or just to sort of build a community around that protocol. So often the serious protocols, I think, often had a lot of work that go into them by the time they get brought to the standards process. There are other, if you read RFCs, they really run the gamut. There are some that are sort of editorials, and there are some that are proposals for specific protocols. But by and large, I think things are reasonably mature by the time they come to the committees.
Thank you.
Okay, let's thank Nate once again. And now there's a break, I think.
Welcome to the program analysis session. We have 4 talks, last one online. And our first talk is Solvable Polynomial Ideals by John. So take it away.
Sure. So hi everyone, I'm John. I'm here to talk about our paper, which is Solvable Polynomial Ideals, with this sort of tagline, which is kind of a pun, which is this ideal reflection for program analysis. So this was joint work with Zach. All right, so this paper is about generating summaries involving polynomials for programs, and I want to sort of summarize 2 lines of prior work within this area, sort of very vaguely and broadly. So on the left-hand side of the screen, I want to sort of consider prior work that generates summaries for sort of arbitrary programs, not really putting much restriction on the program syntax, and so you might have programs with nested loops or branches within said loops, sort of anything is fair game. So the advantages of sort of those works is, of course, they work for arbitrary programs. They'll always be able to provide some sort of information. However, the downside is that the methods are sort of heuristic. Maybe they rely on some incomplete nonlinear reasoning or something, but they're somewhat brittle and don't have very good guarantees on exactly what the analysis does. So I want to contrast that with this line of work kind of represented on the right-hand side of the screen, which I'm sort of characterizing as these works using this model of a solvable polynomial map. So for this talk, the exact details of a solvable polynomial map are not very important. But what is important is that there's this algorithm via Cowers and Zimmerman that allows you to compute all the polynomial invariants between the variables of a solvable polynomial map. So you can adapt this to program analysis to sort of get a complete method for sort of these different types of programs that have this very sort of limited syntax, though some other work have gone and generalized that to slightly more general situations. But for now, we're just kind of thinking about limited programs that fit this particular model. So what's great about that is it's complete. However, again, it's sort of limited in what they can be applied to. So ultimately, we're trying to ask, can we bridge this gap between these 2 lines of work? So the strongest bridge between that gap would be, can we create a method that produces polynomials, works for arbitrary programs, and is complete? And of course, you can't do that. That's undecidable. And there was a nice talk yesterday even about some of the different layers about when it becomes undecidable and when it does it. But in our setting for this presentation, it's definitely undecidable. OK, so we want to weaken that statement a little bit for this presentation. We say, can we generate a method that produces polynomials, works for arbitrary programs, but provides some sort of guarantee on sort of predictability and what the method does? Of course, the answer is yes. That's what I'm talking to you about. So what's the guarantee? So the guarantee is this thing we're calling monotonicity. So I want to be a little bit vague about what that means right now. But this is sort of a property of the analysis. But when I'll sort of outline how our method kind of works, and then I'll get more specific into what I mean by monotonicity. OK, so I want to narrow down a little bit more. So our method is sort of compositional. And so what that means is we're going to build up summaries bottom up by analyzing program subpieces. And then to get more complex summaries, we're going to put those together at higher and higher levels. So for example, if I had this if statement, what I'm going to do is come up with some sort of summary. And that summary is going to be a transition formula. And so in our case, what that transition formula means is it's a formula over the program variables. And for each program variable, there'll be a primed copy. And the primed copy represents the post state after that transition, and the unprimed is the pre-state. So like, y gets y times y is the same thing as like y prime gets y squared. So I do the same thing with the else branch, and then to build a summary for the whole if statement, I'm going to sort of combine them together, and in this case, it's just sort of a disjunction. And so I can do something very similar for program sequencing, and so it's not terribly interesting for this particular talk. I'm sort of taking that as background. But where it does get interesting is what do you do with loops? That's really sort of what this paper focuses on, is how do you analyze loops in this sort of compositional way. OK, so to just sort of highlight kind of what our method does and how it works. So imagine you have a while loop, and it's got some loop body. And this loop body can be sort of anything. It can have branches, nested loops, other types of sort of assignments. It doesn't really matter. So to analyze such a loop, what we're going to do is we're going to recursively call our method. to generate a transition formula that describes the loop body. So we'll use the summaries that I gave in the previous slide for ifs and sequencing, and if we get to a loop, we're recursively calling this method. So that gives us sort of an over-approximation of one step of the loop. And what we do is we take that transition formula, we feed it into our method, this loop analyzer, and we get out this starred formula, which is an over-approximation of this loop executing sort of arbitrarily many times. And in this particular case, for this paper, that should contain polynomials. That's sort of really the goal here. All right, so with this setup, I kind of want to describe exactly what I meant with monotonicity. So the formal statement for what we mean for monotonicity is at the bottom of the screen here. But sort of the informal tag is what's in the green. And it's this statement of more information in yields more information out. And so what it means, if I give you a stronger loop body formula, whether that is because of better analysis, or I'm adding assumptions, or I'm restricting the input in some way, ultimately that should be reflected in the output. My method shouldn't be heuristic, and if I give you more information, you should go wildly off and produce a worse answer. So that's really what we mean formally here with monotonicity. Okay, so let's see. Yeah, so just want to kind of break down a little bit of how our method works. I won't go into sort of the details, but we do provide algorithms and sort of the real details of the paper, what's in these orange shapes. But the main idea of our paper is we're going to utilize this new model that we introduced, which we call a solvable polynomial ideal. And what's relevant for that is it generalizes solvable polynomial maps, which is what some complete methods utilize to generate sort of all polynomial invariants. And so our method is sort of this two-step process. Once we have the solvable polynomial ideal, we have this generalization of Cowers and Zimmerman, which we can use to compute sort of all the invariants of this slightly more general object. But the difficulty there is our original loop body may not be exactly characterized by one of these solvable polynomial ideals. So we have to go through this first step of abstraction to take and over-approximate that loop body formula with one of these solvable polynomial ideals. And then we'll go ahead and summarize that, and that'll give us our over-approximation. So I want to take you through a little bit of an example. This is totally made up. It's not a very important example, but it sort of shows some of how our method works a little bit. OK, but why this example is a little bit difficult is it has polynomial assignments, and it has a branch inside the loop, and that branch even has a conditional. OK, so the first step, what we're going to do is we're going to recursively come up with a transition formula for that loop body, which is given here. I haven't really done anything particularly important. I just basically replaced that if statement with a disjunction, but everything else is sort of captured there. So then what we're going to do is we're going to over-approximate this transition formula with this solvable polynomial ideal. So the solvable polynomial ideal is the big U, and it's describing a transition over the system of variables A, B, C, and D. So you can read this solvable polynomial ideal as this set of polynomials, and you can just sort of set each one equal to 0 intuitively. So for example, I have the variable D, and so it's basically saying D gets D plus 1. And then I can use this little u is what actually determines how my solvable polynomial ideal abstracts my original program. So for example, it maps my variables of my solvable polynomial ideal to variables of the program. So for example, if I had that variable d, d corresponds to j. So the d gets d plus 1 exactly corresponds to j gets j plus 1 in the original loop. But where it gets a little bit more interesting is you might have variables within your original loop that you sort of can't precisely capture with one of these solvable polynomial ideals. So for example, in this particular case, are the variables w and z. And at least for me, I don't know how to summarize w, and I don't know how to summarize z sort of on their own. But what we can do is we can figure out how to accurately summarize the sum w plus z for each one of these, each step of the loop. So that's sort of one of the key pieces, how we're always providing some sort of approximation for these loop bodies. So then what we do is we run our generalization of Cowers and Zimmerman, and we get these invariants of U. The details of these invariants are not particularly important, but this is just sort of the infinite intersection of U across sort of many steps. And then, so once again, you can read these as each one equaling 0. So then to get an overall summary for my original loop, all I need to do is set each one of these equal to 0, and then I can use my little u, which maps my variables with big U to my program variables. And so for example, if you look and find like a C in there, C gets mapped to W plus Z. And so we're not able to capture the variables W, we're not able to capture the variable Z precisely, but we're able to capture this term W plus Z precisely. Okay, so I just want to highlight kind of at the end here, what is this key for monotonicity? And so monotonicity results really from two key features of our method. So the first key feature is that our generalization of Cowers and Zimmerman is really a generalization of Cowers and Zimmerman. It is sort of complete. Given a solvable polynomial ideal, we will compute all polynomial invariants of that model, so for any solvable polynomial ideal. So completeness of summarization, that's one key feature. And the second key feature is our abstraction method does not just produce some over approximation, it actually produces a best over approximation of one of these transition formulas as a solvable polynomial ideal. And so that's what we characterize as a reflection, which is a term from category theory. We don't make use of any category theory in our paper, but that's where the name comes from. If you're from the abstract interpretation world, it sort of can be formulated, though we didn't do it this way, as a best abstraction. So we're producing a best abstraction of these transition formulas as a solvable polynomial ideal. Those two key features together get you monotonicity. Yeah, so just kind of highlighting from back of what we did, we present a method for producing polynomial invariants. It's robust because it's monotone, and it's even complete for some loops, basically where you don't really do much abstraction in the first step. Then we're computing all polynomial invariants. But in general, we're always monotone. In the process of doing this, our method, we introduced this new model of a solvable polynomial ideal, which generalizes solvable polynomial maps. And then we provide algorithms for producing a best solvable polynomial ideal given a transition formula. And then we give a generalization of Cowers and Zimmerman for producing all polynomial invariants of a solvable polynomial ideal. And we also give more generalizations of solvable polynomial ideals that sort of give you slightly more power. You can find more details in the paper. And then finally, our method is not just theoretical. We implemented all these methods, and we ran them on some SVComp benchmarks. And so we sort of divided the SVComp benchmarks into two different categories. We sort of have these loops, which are general set of benchmarks that do not necessarily require nonlinear invariants. And so we were sort of competitive on those examples. And I'd say there's a separate set, which were these nonlinear arithmetic benchmarks that do require nonlinear invariants. So these involved examples such as like the extended Euclidean algorithm, computing the GCD of two numbers that involves like a multiplication in there. We were like a leader in those set of benchmarks. So yeah, so that's pretty much what I wanted to say. I do have extra slides if anybody wants to hear about any more of these methods a little bit more in detail, but that was just kind of the overall highlights. So.
Okay, thank you very much. Any questions, Patrick?
When you have obtained your over-approximation, could you reuse this for classical analysis to take test into account and as an upper bound bounding this classical analysis?
I'm not sure I quite understand that. What are you bounding what exactly?
Yeah, that is the classical analysis will iterate taking tests into account, but each time you bound by what you have found, and that should improve what you have done. And take, for example, because your test at the loop, it's a star always. If you put something, then you iterate classically, bound by the polynomial, you will improve it.
So if we did, so our method is not iterative, but you're saying if it was iterative, we...
First your stuff, then you reuse to improve an iteration algorithm.
So maybe I'm misunderstanding, but so like I said, our method is not iterative. Our summary is, we're directly computing that via basically our generalization of Cowers and Zimmerman involves sort of solving recurrences. So it's kind of like an acceleration technique.
Yeah, but you get a result which is another approximation on the best solution. Otherwise, you would be incorrect, so I am sure you get that. And so when you have another approximation, you see, for example, Gregg interpolation, which is the dual narrowing. You can use this to bound the effect of the iteration. And you should be able to improve using these techniques.
Okay. Interesting.
So maybe related to this question, if you go to your example, running example, right? So you mentioned that there was an if then else, right?
Yeah, it's sort of been removed here, but if you can see, it's this. There's this.
So it still appears, the conditional appears as part of the formula, or is it thrown away?
It's part of the formula, but it gets abstracted away when you get to the step.
Process of.
When you get to the solvable polynomial idea.
And I had a question about the benchmark. You mentioned extended Euclid's algorithm. Do you happen to know what property is proven about it? These benchmarks.
Yeah, I don't remember the exact example, but it's the GCD. You compute the GCD of two numbers, I think, is that. So it's or maybe I don't exactly remember, but it might be you have the UV and
right.
I don't exactly remember.
So there is what you're saying is the extended Euclid's algorithm has actually a proof that is valid over real numbers as well. The invariant is provable.
Yeah, it's this degree 2 polynomial we produce, and that's sufficient to prove the post condition.
Thanks.
They're over here.
I have a question about how long this takes. So I could ask, how long did it take to run the tests that you mentioned at the end? And also, maybe you have something about the time complexity.
Yeah, so it's not, I show you the results table. It's not very informative. Our method is sort of practically fast compared to what we compare against. Theoretically, our method is sort of exponential, so a lot of what we make use of is this idea of Grosvenor bases, and so Grosvenor bases is ultimately dominating so practically and theoretically the execution time. So we're both of these sort of USP lin, USP quad. It's not very helpful, but so the big 1130, 1750, those are our running times in seconds over the whole suites for loops in NLA, and it's sort of reasonably compares with sort of other methods like Vera-Abs and Ultimate Automizer in those particular cases.
Any other question, Patrick?
So you compute with floats or rationals?
You can be what?
Your computation, they are floats or rationals?
They're sort of, so either or is fine. So the actual logic can interpret floors, but I will say in practice, those are sort of really, it's just rationals. Sort of like we're producing rational polynomials.
And it does not explode?
No. Well, I mean, some cases it does. I'd say it's kind of at the edge for some of these examples, and like if you get a little bit bigger, it starts getting a little, quite a bit more expensive. But
quick question: the summary, I assume you start from true, the summary of the loop. You know nothing. What would the loop compute?
If we know nothing,
I'm asking.
So I mean, nothing.
This is the classic definition of summary. So am I assuming correct that that is what you're doing?
So let's see. So like if we didn't know anything about the loop, or
when you start the loop, you know nothing about the state, and you say from any given state where you would end up, right?
Sorry, I'm trying to get to the example here. So we produce like this, we're sort of always starting with some information based on like assignments and whatever. So if I'm not summarizing states, I'm summarizing transitions. between programs. So I'm summarizing how X transforms between X and X gets S plus.
My question was that can I have contextual information that would change your summary in a particular context, what it would be, rather than the general summary of the loop? So that was.
I see. Yeah, so our method does not make use of any context. You could imagine like a forward pass, which we sort of sometimes do, where you pass some information, but essentially we're assuming nothing about the inputs. So it's totally without context.
Okay, let's thank John again. And now, Andreas will talk to us about static analysis via dig reachability as soon as it's mic'd up.
Is this working? Can you hear me? 1, 2? No? Yes. It's working. Okay, good. So yeah, thanks for the introduction. This is joint work with Krishna, Shankaranarayana, Aniket Lal, and Omkar Tupe. Aniket was supposed to give this talk. It was his project. He did most of this, but visa issues, he couldn't arrive on time. Right, so this is about some form of static analysis, and okay, static analysis is some form of program analysis. We very often think of it as some sort of lightweight program analysis, some lightweight scans of the code that try to give us some information. And well, in a continuous development setting, code changes, the static analysis needs to run again and again in newer versions of the code. This, of course, means that you pay the cost of just rerunning the analysis and potentially doing some overlapping work that you'd rather avoid. We'd rather do something like this. So we move the analysis from the whole code to just the updates. Like, ideally, we would like to pay the cost of analyzing only the updates, not the whole code again. And well, generally, this might or might not be possible, or in varying degrees. There have been a few approaches to this, typically relying on some sort of memoization or caching, right? You cache some results that you obtained already. But we don't have any running time guarantees typically. So in the worst case, even if you run the analysis on the update, it might have to touch the whole code again. So this talk is about some form of static analysis that people have used, and for which we can actually provide some running time guarantees on the updates. And what does this analysis look like? Well, it's called Dike or CFL reachability. So this is a graph reachability problem, which is used quite a lot as a model. So it's a graph model of our actual program, and it's used quite a lot in static analysis. And it's a problem that we want to solve fast, and it looks like this. So you have a graph like the one on the right. You have a bunch of nodes. These might represent variables in your program or instructions. And we have these labeled edges, which have some sort of opening or closing parentheses. And what we want to capture here is reachability as witnessed by paths that produce a properly balanced parenthesis string on the way. So for example, X reaches Z by means of this blue path, because the twos match in the innermost part, and then the ones match, and then you have a properly balanced parenthesis string. And now, how fast can you solve this? Well, this takes typically cubic time in the number of nodes, and we have good reasons to believe that it's tight. There's nothing better you can do. Just to give you some flavor of what modeling power this formulation has, most commonly it's used in something called context sensitivity. So here I have some data dependence graph. So my variable X kind of flows into the abstract argument A of function f, and then that's used to compute some value, which is then returned and goes back to y in line 6. So if I just look at paths in this program, I mean in this graph, then I see some data flow propagating from x to y, but also from x to w if I ignore the parentheses. And now the parentheses are there to filter kind of invalid paths. So if I start from x, I cannot really end on w. That would mean that the call in line 6 actually returned in line 8. And that doesn't correspond to any meaningful run of the program. So calling context sensitivity is one use of these parentheses. Another is field sensitivity. So here we're capturing data flow between objects that can be composite, so they can have member variables like f here that has an x and a y. And now I'm using the parentheses to distinguish the fact that A is touching the x part of f. And now when x is read again down here on C, I have, again, some data flow, but A does not affect B because B is reading from y of f, and A is writing to the x of f. So the top path is a not properly balanced path, so it does not witness any reachability. Now, our setting is even more restricted than this. We're looking into something called bidirected graphs. So this means that basically, whenever you open a parenthesis, as you transition from x to y, you have to close the same type of parenthesis when you transition from y to x. And these have been CFL models of alias and pointer analysis. They're particularly useful for capturing mutable heap data in this kind of data flow graphs. And they also serve as a quick over-approximation of more general CFL reachability, because, of course, whatever CFL reachable path you have in an original graph, you would also have in a bidirected extension of that graph. Right, so how fast can we actually solve now the same problem on bidirected graphs? Well, it's not hard to see that the reachability relation on this kind of graphs is actually an equivalence relation. If I have a path from x to y witnessing the reachability of y from x, then the same path backwards will have the same string. So it will also witness the reachability in the inverse direction. And this gives us a very simple scheme, actually, to compute reachability. Well, this means that actually the reachability relation will partition our graph into a number of strongly connected components, which we call Dyke strongly connected components. And then the computation of the whole of these components can be defined kind of recursively. You iteratively find you find one component x that has two outgoing edges to two other components, and they're both labeled with the same closing parenthesis, and then you just merge them. You know that this will actually fall into one big component, which is witnessed by paths that start from y, take this closing parenthesis edge in reverse, so they open a parenthesis of type I, they stay in x, and then they close it, they go to z, and the two merge. Just to see this on an example, let's say we have this graph. We can apply this rule already on the outgoing edges of U to merge x1 and x2. Now we have a new component, this x component, which again has two outgoing closing parenthesis edges of type 2. So this will merge the y's, this will merge the z's, and well, the z's now will merge the x's and the y's, and this will be like the fixed point of this computation. So it has some unification closure style taking place here, and well, we know that we can solve this problem basically in time now that is only quadratic in the number of nodes. Well, the precise complexity is listed up there. So it's m plus n times alpha n. M is the number of edges, n is the number of nodes. Alpha n is the inverse Ackermann function. It's a very slowly increasing function. But this can become quadratic in the worst case in the number of nodes. And now in on-the-fly setting, what we want to do is maintain these Dyke SSEs on the fly after inserting and deleting new edges. So really, we aim this kind of analysis to be very lightweight and run while the programmer is actually typing lines of code. Right, so how fast can you solve this? Well, before I go there, let me just illustrate this on a small example. So this is, again, a field-sensitive data flow analysis. So what we have is the code on the left. We have these 3 class, and then we have some manipulation of 3 objects. And then we have our original code. At some point, we add line 12, and then we remove line 9. So our first DSCC decomposition will be the graph on the top. After adding line 1, we'll have the graph in the middle, and then after deleting the line 9, we'll have the graph in the bottom. Right, so the question is now, how fast can you do this? You might scratch your head a bit and also consider how fast could I do this in principle. You might be able to avoid these quadratic bounds, but it's kind of tricky to go below linear, because just a single edge addition can create a large number of components. So this could change the size of your output quite a bit, so that you might have to suffer a large cost, at least a linear cost, just because the size of your output changes by a linear factor. So then you might ask, can we at least do something like order n? And the answer is yes, we can. That's what we achieve here. So we can maintain on the fly these Dike SSEs in pretty much linear time, well multiplied by the inverse Ackermann function. So it's better than quadratic, and we also have some practical heuristics that in practice seem to actually perform these updates pretty much in constant time. So just to give you some very little flavor of how this is achieved, actually inserting edges is easy. You can keep track of this component graph, and upon inserting a new edge, just carry forward the fixed point computation as you normally would in the offline setting. So you would merge these two, and then do some more merging, just like we did when we had a single instance of this problem. And this would give you the bound we're after. The tricky part happens when we have deletes. So for example, here, if I was to delete this edge x2 to y2, it's not really clear how I should start decomposing my graph. Here, the x's merge the y's, and the y's merge the z's, and the z's merge the x's and the y's again. So undoing this is not easy. And under the hood, the reason why this is not easy is because there's actually no efficient union find data structure that performs arbitrary deunions. And union find is really the data structure that is used to support this efficient computation. So what do we do? In one slide, we define something we call primary Dike strongly connected components, which are defined by some relation R here. So we say that the 2 nodes x and y are related by R if it's actually the same node, or if there is another node u that is pointing to both x and y with the same closing parenthesis type. And then we take the transitive closure of this relation, and whenever 2 nodes are related by the transitive closure of this relation, then we have a primary DSCC, and that's how it looks pictorially here. So for example, x, y, and z are related because u is pointing to each of them. Z is also related to w via v. So we get all x, y, z, and w in the same primary strongly connected component. And now what we show is that you can actually maintain this quite efficiently, so in linear time. And then if you restart your computation, not from the scratch when you delete an edge, but rather from this primary DSCC decomposition of your graph, you can obtain the guarantees that we're after. So we also did some experiments on 2 static analysis, context-sensitive data dependence analysis, and field-sensitive alias analysis, again, where parentheses are used to model field accesses and calling context sensitivity. We just messed with the graph randomly, so we inserted and deleted edges, and we compared 3 algorithms, the offline algorithm, so every update would run the offline algorithm from scratch. You can also express this reachability very easily in data logs, so we ran this through a dynamic data log solver and also our dynamic algorithm. And in one slide, this is the results we get. So the dark bars are the running times of our algorithm after each update. And you can see that they're fairly negligible compared to what you would get if you were to follow any of the other 2 alternatives. So I think I have to stop here, right? Yeah, OK. So thanks for your attention. Let me know if you have any questions.
questions?
Thanks for a very nice talk and nice results. Could you just show a bit more the table with results? So you mentioned you can
Yes.
do this as you type. So these are microseconds. Okay.
Yes.
Okay, great. And so I was wondering, since you mentioned randomly generated data, do you think there would be a way to have data that corresponds to people actually typing, so that we see whether, I mean, what do people end up doing, right?
I mean, if you can sign the right forms, I think you can get those. But we didn't have the capacity to do this in the context of this project.
But you believe they exist, or you would gather them?
I don't know if they exist. I would guess that it's not so hard to get them, assuming bureaucracy goes away somehow. But otherwise,
like with telemetry data from VS Code, like tools, right?
Right. Yeah. And I also don't see a good reason why people would like to hide that, for example.
Thanks.
I wonder if you could say more about the loss in precision of this bidirectional representation rather than the when you showed it first. When I think about the context sensitivity, I mean, basically it seems like you're getting the benefits of context sensitivity, but it's with a unification rather than an inclusion style analysis. So I'm just wondering, why would I want this bidirectional graph in the first place, just for some context?
Right. So some analysis can start this way just because it provides a quick over-approximation that you can later refine. So it reduces effectively the...
Yes. Just returning to your motivation slide one more time. So let's say somebody has been working on their program all day and they made 10 changes. Are you going to process that in one go, or are you going to do them as a sequence of 10 updates?
That's a good question. The algorithm considers updates sequentially, but it's not a far distance to cover to do all 10 at once. I don't see anything that would even break the theoretical bounds, as long as it's really 10 and not the whole source code.
I have a question. How big do these graphs get in your experiments?
I don't have the data here, but I think these go into tens of thousands of nodes or even hundreds of thousands. At least last time I checked, these are the numbers we show. Especially, I mean, these are whole program analysis typically, so it's, yeah.
Any more questions? In that case, let's thanks Andreas again. And for our third talk, Marco will tell us about monotonicity and the precision of program analysis. Right, all yours, Marco.
Okay. Can you hear me? Yes. Okay. Thank you for the introduction. I'm Marco Campion at INRIA. I'm a postdoc. This is a joint work with Caterina Urban from INRIA and Mira Dalla Preda from University of Verona and Roberto Giacobazzi from University of Arizona. Okay, so I'll just start with a bit of context. We want to verify whether a program satisfies a specification using a sound program analysis. So in case so we designed our sound program analysis, and in case the analysis returned yes, then we know that the specification is satisfied. Otherwise, it may return an alarm. Sorry. The problem here is that we actually, in general, don't know if every alarm is actually a true alarm. So it may be a false alarm. This is due to the famous Rice theorem. So unless we are analyzing a trivial specification, we need to deal somehow with the false alarms. And so what people do usually in program analysis is try to modify or tune the program analysis in order to decrease the number of false alarms. And there are also like applications, real applications where the false alarms are critical. So we try to completely remove false alarm to get a very precise, a complete program analysis in this case. What we want to answer in this work is the following. We want to try to partially answer a question, which is, can we formally prove the existence of a program analysis over a program and a specification for which we are sure that there will not be false alarms, but just true alarms in this case? So can we prove the existence of this program analysis? And can we extend also this reasoning on maybe a class of programs, depending on their behavior, and a class of specifications? So we want to give a partial answer on these questions by considering program analysis, in this case, formalized by abstract interpretation. So in one slide, what is abstract interpretation? So we have our concrete operator computing over concrete properties, which may be undecidable. So the idea of abstract interpretation, the key idea is to replace the concrete computation with an abstract computation over decidable properties in order to be able to prove properties of program in this case. So for our purposes, we are going to consider a deterministic while language that we want to analyze. We are focusing on analyzing the output of a program and numerical properties in this case. So we are considered as a concrete semantics, a standard collecting the denotational semantics. And then we are going to consider an abstract semantics, sound by assumption, over an abstract domain. And we are assuming that between our set of concrete properties and set of abstract properties, we are assuming a Galois connection. So with an abstraction and a concretization function. So what does it mean soundness in this case? So here we have in the top corner, we have the inequality. So it means that the result of our abstract interpreter must be an over-approximation of the abstraction of the result of our concrete execution, which implies that if we want to verify a specification, so given a specification which is representable in our abstract domain, and we want to verify the concrete execution of a program over an input, if it satisfies that safety specification in this case, then we can run we can use our abstract interpreter to verify this inequality. And if this equality is satisfied, then we can, for sure, thanks by the soundness assumption, we can conclude, yes, the specification is satisfied. We have incompleteness when we have a strict inequality in this case. So it might happen that our program analysis returns no on the specification, but in this case, we may have false alarms because of the over-approximation induced by the program analysis. So the best scenario is when we have completeness. So when we have an equality in this case. So this means that even if our program analysis returns no, it is not satisfied, if we have completeness, then we are also sure that the actual raised alarm is a true alarm. So the specification, so the actual behavior of our program over the input does not satisfy the specification. So as you can see here, completeness is a very important property in program analysis. But of course, the problem is that it is very hard or even impossible to achieve. So it has been extensively proved in other papers that only trivial abstractions actually are complete for all programs. So it's impossible to build a program analysis which is complete for all programs and input. And we can also build, for every program analyzer, we can also construct, so build, implement a program whose analysis result is incomplete. So in this work, what we try to do in this case is to try to classify, so identify a class of specifications, so a class of abstractions, and a class of programs, and a class of inputs, for which, when we want to answer these questions on the behavior of the program, then we can formally prove the existence of an abstract interpreter, so of a program analysis over the abstract domains, over these abstract domains on this class, for which actually we have completeness. So all raised alarms are actually true alarms. And when this property is satisfied, we will say that the program P is complete analyzable for the abstract domain A at input I. So we can answer with only either yes or false or alarms, which are true alarms, on the specification, which are representable in the abstract domain A. So I'm going to show that here the monotonicity property over programs will play a central role. So in one slide, I try to resume the main result of the paper. So what is program monotonicity? When a program is monotone. So I will define monotonicity as given for all possible comparable inputs, we have that the result of the program on the inputs maintains the order. So the program preserves the order of the inputs, or for all comparable inputs, the program reverses the order of the inputs. So it is either non-decreasing or non-increasing. So the main theorem here is that whenever we are considering bounded inputs, namely inputs which have always minimum and maximum elements, and abstractions which are non-relational and able to represent intervals, so for example in two-dimensional rectangles, and the output of our program analysis is actually convex on the program, then I can show you that whenever the program is monotone on the over-approximation of the input, if we can prove the monotonicity of the program on the over-approximation of the input, then we are sure that there exists a program analysis which is complete for this abstraction and this input. So we can prove all the specification representable in the abstract domain without the false alarms. This is our main contribution. So, for example, let's consider the ReLU activation function in neural networks, which is a very simple program, returns 0 in case of negative numbers, otherwise the identity. We can see that, for example, this program is non-decreasing, so it is monotone, in this case for all possible inputs. And so thanks to our theorem, if we want to analyze the output of this program on the interval abstract domain, then we are sure that there exists actually an abstract interpreter that can answer, that is precise, which is complete. So in this case, I can also build the actual abstract interpreter, and I can show that this analyzer is actually complete for all inputs in this case. So we can prove all the interval specification on the output of this program. And we can, for example, go on like considering other activation functions which are non-decreasing, and we can conclude again which with these programs are actually complete analyzable for the intervals abstract domain. And so, for example, since monotonicity is closed by composition, so if we are composing non-decreasing activation functions with non-decreasing nodes by obtaining a non-decreasing neural network, in this case, then again, we can conclude that the output of our non-decreasing neural network is complete analyzable for intervals, for bounded inputs in this case. So what we want to do now is try to, okay, so we have a program, we have a set of variables, but maybe we are not interested in all the variables of the program, so maybe we just want to analyze a subset of the program variables. So in this case, we define what is V monotonicity. So we specify monotonicity over a set of variable V. in this case. And so we just consider the comparison between states only on the set of variables V. And we say that program P is V monotone for the set V at an input I whenever the program is V non-decreasing or V non-increasing at I. So the next question is, okay, but can we verify V monotonicity of programs? Well, we define a proof system, a sound proof system in this case, compositional on the program syntax. So we want to try to verify the predicate, this predicate, which is monotonicity over a program P, an input I, and a set of variable V. So this predicate will be true whenever the program is non-decreasing or non-decreasing over the input I for the variables V. And we are going to focus on the non-decreasing property in this case, since the non-increasing property is actually dual. So this is the set of rules of our proof system, and since I don't have enough time, I'm going to show you just the branch rule in this case to prove monotonicity for the branch rule. So the idea here for proving monotonicity of the non-decreasing property of a program with an if branch, which is actually the main program which may cause the which may break the relation, the monotonicity relation over states. Then here the idea is that, okay, let's consider that the branches at least are monotone, so are non-decreasing, sorry. If the branches are non-decreasing, then here we are, in order to prove monotonicity of the branch, of the if branch in this case, well, we can consider boundary states. Whenever we have a positive linear guard, which means that it divides the input in two spaces, then we can consider only boundary states. So we can try to verify the non-decreasing property only on the states which are exactly on the guards, and try to see, and if the states actually in the program, the two branches satisfy the non-decreasing property on the guards, on the boundary states, then we can conclude that the program, the if branch in this case, is non-decreasing. So for example, again, why we can prove the non-decreasing property of the ReLU program, because the two branches are non-decreasing, and so here the boundary state is just 0. The guard equals 0 in this case, and so we can conclude that the program is the ReLU program is non-decreasing. So by concluding, this is the specialized theorem for programs with a set of variables V. So whenever we specialize also the property of boundness and convexity. So whenever we have a bounded input on the set of variables V, a non-relation upstart domain, able to represent intervals, and a convex result on the variables V, then whenever the program is V monotone, we can conclude that the program is also V complete analyzable for the upstart domain A. So the actual proof here is just that, so I don't have enough time to show the complete proof, but the idea is that why it is possible to build a complete program analysis, because we prove actually that the best Corey approximation is complete. So every spurious element added by the abstraction is actually somehow considered by the program, and does not generate false alarms in this case. And so we have the P is actually complete analyzable. So by concluding, so we have shown that the precision in program analysis is influenced by not only by how programs are written, so by the syntax, but also what programs compute. For example, all monotone functions, we proved actually that all monotone functions, we can build a program analyzer for monotone functions and for example, some inputs and some upstart domains. So the key idea here is to try to maybe if you want to, for example, prove specification over intervals, we can maybe identify monotone components on our program for which we are sure that we can precisely analyze those components. And maybe a question could be, can we classify the extensional class of programs for which, with respect to a given program analysis, which is for which our program analysis is actually complete? And this ends my talk. Thank you.
questions for Marco.
Okay, I have a question about the analysis that comes out of this. So you say that a complete analysis exists. Can you say something about whether it runs very fast or it's very slow or it's computable or
Okay, so
just some properties of it?
Okay, so it is computable, but actually, since we proved the completeness of the best correct approximation, so we actually proved the existence, but we are not actually proved the existence of actual an always terminating program. So the theorem here is that if you want to build actually in actual a complete program analysis, then whenever your program analysis is complete, then also the best correct approximation is complete. So in order to be able to actually consider to be able to precisely prove a program, the first step is to prove that your best correct approximation is complete. And then you are sure that, I mean, it could exist or not an always terminating, but there is the possibility to build a precise program analysis. This is the first step.
Another over here.
Hey, I'm worried I might just wind up asking the same question again. So you can just go, I've already answered that. But thanks for the talk. What does this assume about the widening operators?
Okay, so we are not considering here widening because we are actually defined that, so we didn't, the proof here of the theorem is not an actual program. So it is that the function is actually, you can build the function over the abstract domain which is complete. Then the next step will be to, of course, to find an always terminating program. But we actually prove that the best correct approximation function over the abstract domain is complete, which is not an actual real program analyzer because it is not always terminating. But in order to build a program analyzer always terminating complete, you have to be able to prove that the best correct approximation is actually complete. So it is not possible to have an always terminating program analysis complete, but the best correct approximation is not complete because you have to always satisfy this inequality. So every program analyzer is actually at least as precise as the best correct approximation.
Cool, thank you.
A question here. So I'm wondering how many kinds of examples you have of programs and monotone, V monotone and abstract domains that actually satisfy your property. So you said ReLU was one, but I presume affine transformations will not be because of, I don't see how it can be. But
yeah, of course.
And so are there? Can you give us some examples of where your restrictions will be met except ReLU?
Well, you can also, I mean, a program as a whole might not be monotone in this case. But you can also, what we try to do with our proof system is try to maybe identify variables that behaves monotonically. So for example, I don't know, counters variable, many counters variable behaves monotone. So you can maybe identify those variables and you are able to prove in this case precisely some properties over, for example, intervals.
Okay, we can do one very quick question.
And there is that side. Oh. Sorry.
What I have not understood is P, because do you take the analyzer, the relation between the analyzer and P? Is it for one program you get one analyzer, or for a infinite set of programs you get the same analyzer?
For one program, you get an analyzer.
Oh.
Yes. Well, but it's not an actual real implementation, actually.
Okay.
Okay, thank you again, Marco. And our next talk is online, and I have no idea how this works, but hopefully it appears. and it's actually a distinguished paper about FLAN, a data log engine. And I also do
can
not
you hear
know
me?
who's giving the talk, so please introduce yourself.
Yep. Can you hear me?
Yes. Yes.
Okay, awesome. Yes. Yeah, thank you all for coming. And yeah, in this presentation, I'll be talking about the work we've done on building an efficient and expressive data log compiler for program analysis named FLAN. I'm Supun. I recently graduated from Purdue, and this is joint work with Angelo and my advisor, Tiak Prompt at Purdue. So yeah, so what is Deadlog? So Deadlog is a widely used language for doing iterative fixed point computations in a declarative manner. So for example, let's say we want to compute graph reachability, and let's say we have our graph represented as a relation called edge that contains a set of edges. Graph reachability can be expressed using these two data log rules. What this says is that if there's an edge from U to V, we can say that V is reachable from U. And the second rule says that if there's an edge from U to W, and we already know that V is reachable from W, then we can derive the fact that V is reachable from U. So how does these rules get evaluated? So simple rules that are not recursive are trivial to execute. You basically execute the body of the rule, derive the corresponding facts, and insert it to the relation on the head. And for recursive rules or mutually recursive rules, these are evaluated until we reach a fixed point. So for example, the second rule of the reachability example is a recursive rule, and this will be evaluated until we reach a fixed point for the reach relation. So the way the algorithm used to evaluate this is called the semi-naive evaluation. The idea here is that for recursive relations, you only consider the fact derived in the immediate previous iteration. So one of the promising applications of Datalog is doing program analysis in a declarative manner. So this is really powerful. For example, like an analysis written in thousands of lines of imperative low-level code can be written in like dozen lines of Datalog. So this sort of shows the power of Datalog in using Datalog in program analysis. So how does this work? So Datalog operates on relations. So what we do is we have to first come up with a relational representation of the program. So let's say we have this program. For different kinds of instructions, we will create different relations. And based on the program, we will populate the corresponding relation. Then once we have this relational representation of the program, we write the corresponding, the analysis logic we want to perform using Datalog. So this is for a simple points to analysis that computes like which variables would point to what objects. Once we have this analysis specified using Datalog, we can use a Datalog engine to compute the output. In this case, it will compute the points to relation, which contains the output of the analysis we want to compute. And so while like the pure fragment of Datalog is sufficiently expressive for a variety of cases, there's a growing need for extensions to support an even wider range of program analysis. So for example, this strong update analysis, if you want to do this strong update analysis in a declarative manner, you need a Datalog system that has support for things like user-defined lattices and relations that can have custom lattice columns and user-defined functions that operate on user-defined lattices. And likewise, there's a growing need for things like user-defined aggregates and support for mixing SMT constraints with Datalog rules. And in general, like being able to interpret with a full programming language. For example, like embedding some form of iterative fixed point computations in a larger program. So what all this says is that your Datalog engine should be flexible. So taking these things into consideration, we have identified three main requirements. The first one is the flexibility. That's what we discussed. And the second aspect is it should be fast, the performance. And another important dimension is that we should be able to achieve both flexibility and performance while keeping the productivity of the developers of the Deadlock engines at a reasonable level. So these are the three requirements we have identified. And first, we look at the existing sort of landscape of Datalog compilers. So in terms of performance, they are at a really good level because they do specialized code generation, and they have like index structures tailored for data log and different optimization strategies. But one of the two of the areas that they are lacking is the productivity and the flexibility side of things. So for example, some of the systems rely on stringified code templates for doing code generation. So the idea is you have like large chunks of stringified code templates that gets concatenated, and that's how the code is generated. And it's whenever you want to add new features, now you would have to modify these code templates or write these new pieces of these code templates. So it's really, in terms of maintainability, it's not ideal. And also some of these systems have like multiple levels of intermediate representation. Again, if you want to add something, then you would have to modify these multiple layers of optimization passes and like intermediate representations. So yeah, in this work, we asked the question, can we do better? So we started off by building an interpreter. So we implemented a high-level data log interpreter using high-level Scala. So this is sort of like a textbook implementation of semi-naive evaluation, implemented using high-level abstractions in Scala. So with this implementation, what we get is a system that has really good productivity, because our core Datalog engine simply has like high-level textbook style Datalog interpreter like code, and there are no multiple intermediate representations, no stringified code templates. But the problem is the performance is significantly lower than like the compiled counterparts. This is because there's going to be a significant interpretive overhead. It could be in terms of like because of the fact that we use generic data structures and other overheads. So to address this performance gap, we look into an existing body of work that shows the connection between interpreters and compilers. Specifically, the first program projection shows how to derive compilers from interpreters via specialization. So specifically in our case, we use this framework called lightweight modular staging, which performs this specialization via types. So let's say, I'll give you like a simple example first. Let's say we have this power function which computes n to the power b. So this is like a simple implementation in Scala. And let's say we want this function to be specializable with respect to different values of b, right? So we can do this in LMS by annotating this n as a rep type, which says that this is going to be a part of the generated code. So this is basically, this does not get specialized, and any like normal variables like ints will get evaluated and will be specialized with respect to these variables. So as an example, we have this annotated program, and let's say we want to specialize this with respect to b equals 5. We can use LMS to automatically do this specialization and generate the corresponding specialized function. So what does it have to do with Datalog interpreter we had? So what we should do is we have this interpreter, and so we basically specialize, we make the necessary updates to the types so that this Datalog interpreter can be specialized with respect to a given Datalog program or a given set of Datalog tools. And so we can do this by changing the type annotations as we saw before. And now we can use our specializer LMS to generate specialized code. And so this will be equivalent to code generated by a Datalog compiler from a high level. And so where do we stand? Yeah, so in terms of productivity, we still preserve the productivity levels because we still have the same high-level interpreter style code. And now the performance is improved because we do not have the interpretive overhead we had, and because we are now generating specialized code. Yeah, so due to the interest of time, I'm not gonna go into detail. In the paper, we discuss how we improve the performance further by having fully specialized index structures and like having multiple join strategies and optimizations to index structures. And the key here is that all these implementations and optimizations can be done with minimal sort of like turnaround time because our code is simply like an interpreter style high level Scala code, which can be easily maintained. So one of the aspects that is still lacking is the flexibility side of things. For example, let's say we wanted to add parametric rules or high order relations. So if only we had the textual front end, we would have to implement all these features ourselves, which pretty much boils down to building our own language. So instead of doing that, what we do is we come up with an embedding in Scala. So on the left, we have the typical Datalog syntax. And on the right, we have the same program written in our Scala embedding for Datalog. So we use functions to represent relations, and we provide these different kinds of operators to write rules. So what does this give us? So one thing is Scala's type system now will check for simple things like proper variable use in Datalog rules. And now, since this is fully embedded in Scala, you have the interoperability with Scala. And then, most importantly, we can use Scala infrastructure for things like polymorphic Datalog programs, higher order relations, user-defined lattices, and so on. Yeah, for example, if you wanted to do a version of reachability program, reachability that is polymorphic, yeah, we can pretty much use Scala infrastructure for that. So we can have like an int version of this or string version of this. Also, we can have like, in this example, this edge relation is left abstract. So we can have a subclass that provides edge as an input, or we can have another subclass that provides this as a result of another computation or another rule. So yeah, so what we get is a performant, flexible system that is still having the developer productivity we desire. So I'm short on time, so I'm gonna quickly go over the performance numbers. So we evaluated performance against state-of-the-art systems on 3 benchmarks. One is a simple call insensitive field sensitive points to analysis. And then on one of the Dupe benchmarks, Dupe is a Java points to analysis framework. And then the strong update analysis we saw before, which uses lattice semantics to express the logic. So for single-threaded, so in our system, we have like different variants of index structures and like join strategies. Again, this is possible because it's easy and it's like faster turnaround time for different kinds of implementations. So for this particular benchmark, our fastest performing variant is 7.5 times faster than Souffle and 2.1 times faster than Ascent. So yeah, so this demonstrated the effectiveness of our generated specialized code, index structures, and join evaluation strategies. And yeah, so here we evaluate the parallel performance. Yeah, so our system remains fastest in absolute terms across the number of threads. Yeah, since I'm running out of time, I'll quickly go over this. Yeah, this is for the strong update analysis. Again, here we see that because our system is capable of pushing the specialization further, we see significant speedups compared to other systems. Right. So in conclusion, we have identified that building Datalog engines that achieve performance plus flexibility while maintaining the developer productivity as a challenging problem. And we show that we have demonstrated that our approach allows maintaining the flexibility levels of interpreters while achieving the performance of deadlock compilers. And we have shown that our Scala embedding allows the additions of a variety of features with minimal effort. And yeah, so in terms of like limitations and future work, right now we only do like very limited amount of like query planning. So we have plans to extend this with like proper query planning mechanisms, like cardinality estimates and stuff like that. Yeah, so thank you all for listening, and
thank you.
Yes.
We have a bit of time for questions.
Hi, can you hear me?
Yep.
All right, thanks for the talk. So if you have to specialize the entire data log engine every time you have a new set of rules, I'm curious about the impact on compile times and the development loop. So do you have a sense, for instance, if I add a new rule, like how many milliseconds or seconds am I waiting for the next version of the engine to be ready?
Right. So yeah, first of all, we sort of deploy this in sort of like a ahead of time manner. So what we do is we write the analysis using Datalog. We use our system. It'll generate like a specialized version of C code specialized to that particular analysis. And then we would run this code on like hundreds of different programs that we want to analyze, perform this analysis on, right? So with regard to this, like this compilation does not happen in the critical path of the execution or the hot path of the execution.
Oh no, I understand. I'm saying when you're developing the data log rules themselves, like how.
Okay.
Yeah.
Right. Yes. Yes. So for the experiments, like for these three, I think the maximum time of compilation was like 50 something seconds. If I remember, like, yeah, it's always like less than 100 seconds for at least for these cases. Yes.
Okay, thanks.
But yeah, so another thing is when developing the deadlog rules, we could alternatively use the interpreter itself because the performance is not critical. Like you can have like a sample data set, and then you can do your debugging on the sample data set, if that makes sense. Yeah. Thank you.
Another question now from Andrew.
Hello, this is Andrew Appel. What about your interface to the garbage collector? Which, if you're using Scala, I presume it's a sort of Java virtual machine garbage collection interface. And one thing I noticed about Datalog systems is that the demands of Datalog in its interface to the collector sort of work differently than the functional programming languages or object-oriented programming languages might work. And I wonder if that's a performance impediment, that you're using a garbage collector interface tuned for this, the virtual machine that Scala uses, which is not the same, which doesn't provide the same affordances that sort of native Datalog garbage collector interfaces might have provided.
Right. Yeah, I think I missed, I didn't explain it properly, but the way it works is we have the implementation in Scala, and the specialized code we generate is actually going to be C code. And this is executed completely outside of the Scala runtime. So we generate specialized C code from our Scala interpreter, and then we can compile this and run this independently. So yeah, we are not interfacing with the runtime of Scala.
Okay, thank you. I'm afraid that's all the time we had for questions. So thanks again, Supun.
Yep, thank you.
And we're off to lunch. Quick announcement, the women's lunch is upstairs in the Riverside room. Everyone else stays downstairs, please.
For the slight delay, everyone. So welcome to Types 3. And just as the AV switches over, the first talk will be given by Lionel Parot. And the title is When Subtyping Constraints Liberate, a Novel Type Inference Approach for First-Class Polymorphism.
All right. Hello, everyone. Welcome to my talk on subtyping constraints liberate. So let's first talk about polymorphism, and in particular, the classical pre-next polymorphism of ML and how it compares to first-class polymorphism. So you all know what's the type of the identity function, right? Whoops. Okay, so this function has a polymorphic type, right? For all A to A, and this means you can use it in several positions which expect different types, and every time you use it, you're free to substitute the type variable A with whatever is required at the call site. Okay? And now, how about this term, which puts the id function inside a singleton list constructor? So what ML says is that this has type for A, a list of A to A, but we can also make it list of for A to A, which requires more advanced type system than ML, but is also more precise because the type of this list is the type of a list that contains polymorphic functions, right? Whereas the elements of the list in the other type are monomorphic. So in order to achieve this other type that I showed, we need to be able to substitute type variables with polymorphic types. So the singleton list constructor has type for A to list of A, and we want to instantiate it by substituting A with for A to A. So I should have picked another variable name, but this is not the same A, right? And when you apply it to the identity function, then you get list of for A to A. Okay, well, why do we want to do these kind of things? It seems a bit not very useful, but actually there are many applications of such type systems with data structure fusion, encapsulation, existential types, etc., etc. And more importantly, we need the full power of first-class polymorphism to be able to abstract over all of these use cases. And these things are actually pervasively done throughout the Haskell ecosystem. So it's a quite important thing that we want to have. So what's the type of the following function bar, which takes two parameters. It tests whether the first parameter is true, in which case it returns its second parameter, otherwise it returns it. And it seems we have to choose between two types. The first type is a type where the quantification appears on the outside, where you instantiate the type of id here. And so you get the for A on the outside of the function type. So this is the type that ML will tell you. And with first-class polymorphism, we also have other types that are possible. And so in this case, we can also say that this is a function that takes bool and returns and a polymorphic function and returns a polymorphic function. And so neither type is more general. You can see that using bar with these two examples works only with one of the other type. Okay, so we're kind of stuck because we don't know which type to pick, right? We don't know when to generalize and when to instantiate type variables. And so let's use an analogy to explain what's happening. So you're probably familiar with finding the roots of polynomials. And here's an example polynomial. And you probably know that we can solve these polynomials in the real and imaginary domains. But when you solve it in integer domain, it becomes very awkward, right? Because you have to make discrete choices. Integers are much less fluid than real and imaginary numbers. So using imaginary numbers, you can have one solution, and these numbers are much more fluid and they smooth over the rough edges of integers, right? So the question is, what are the imaginary numbers of type inference? And I argue that subtyping plays this role. Okay, so let's look into subtyping with first-class polymorphism. And you may have byte memories of subtyping from university, where they teach what I like to call AKOP, or Animal Kingdom-oriented programming, right? But that's not the only thing you can do with subtyping. So I hope that by now, thanks to the other talks, you're convinced that subtyping is more than that. And in particular, in the context of a first-class polymorphism, you have a natural subtyping order between polymorphic types. So for example, the polymorphic identity type for A to A is a subtype of int to int because it can be instantiated to int to int. Okay? And you can enrich this subtyping relationship with more rules such as distributivity, which allow you to close the typing under eta conversion. So here's an example where we add a subtyping rule to distribute the outer quantification inside the inner function type. Okay. And so basically what I'm trying to say is that subtyping makes sense for a first-class polymorphism, and it allows some flexibility. It allows an expression to have more than one type and no longer be limited to one type. And as the example, let's go back to bar. So the function bar we saw before we can actually give it a type that uses subtyping. So in this case, we use the least upper bound of the subtyping relationship, which I denote using this union symbol, right? And it turns out this is the principal type of the bar function. So bar is now a function that for all A takes an A and returns either A or the polymorphic function identity function type. Okay? And so it turns out we can simplify this type to something that's a bit less ugly, but this is another topic. So this allows to call both bar of true and sucks and 0, which gives you an int on the output, and bar of true of id, which gives you a polymorphic function type as the output. And it's not surprising because, as I said, this is a principal type. So you no longer need to make premature polymorphism decisions, such as do we need to instantiate, do we need to generalize when you have subtyping, because you can basically encode the control flow of the program using subtyping. So let's talk about type inference using this subtyping relationship. And type inference isn't that hard, right? Source? Well, done right. A compiler should be able to figure out types automatically. It's not that hard, right? So let's see, what are the actual challenges that you have when you try to do this? Consider the following function. Foo of f makes a tuple of f of 1, 2, 3 and f of hello, so it applies its argument function to two incompatible types, and this is not typeable in ML. But with first-class polymorphism, it becomes typeable, and here's an example of a type you can give to foo. It's a very specific type, right? Here we decided arbitrarily that the function will return an option of the input, okay? And so this means that if you're able to infer these kind of things, this should work. You should be able to define foo and then use it in your program with functions such as fun of x to sum of x, because foo can be typed using this compatible function type, okay? And so how do we achieve this? How do we find a type that's good in general, instead of specifically picking one particular possible type? So this is a hard problem. Simon Pittenjohn himself, one of the most important person in this field, said that he tried to solve this for 15 years, and at the end ended up with a system that still rejects this program. And he also mentions MLF, which is the undefeated champion in first-class polymorphism type inference so far. But even MLF fails to type check this example. It's a bit unsatisfactory, right? Because this is just an abstraction of the example using the identity function that I showed at the beginning. So the problem is that we're looking at this type, and we see that the function is applied to two incompatible types. So intuitively, we are like, okay, so the function should be polymorphic, right? So it should be for A to something else. But what is this something else? It could be many things. It could be for A to A to int, A to the list of A, etc., etc. And so our approach, which is done in SuperF, a new type inference system using subtyping, is to infer an intersection type, right? So here we are using the same function in two different positions, and that gives rise to an intersection. So the function type, the type of the argument function is now required to be both a function that takes ints to some a and strings to some b and returns a tuple of a and b. And this, again, is the principal type of this function. We can actually demonstrate it. And so this way you can call foo with all sorts of functions that return different things and get the expected type, right? So foo of the identity gives you int and string, and foo of the sum constructor gives you option of int and option of string. What are intersection types? Intuitively, you can think of parametric polymorphic types, such as for A to A, as an infinite intersection of all the possible instantiations of this type, right? So in this context, it's clear that assigning to the f parameter of foo an infinite intersection type is overkill, right? Because actually it applies its argument to two specific types. It doesn't need to have this full infinite type. And so that's why we can use this type in this case. Okay, but I've actually lied a bit because the core language of SuperF does not use unions and intersection types. These are actually syntax sugar that are presented to users because they are intuitive and nice to read. But actually, what we use is called multi-bounded polymorphism. And so it means that polymorphic types include a set of bounds. So a bound can be an upper bound on some type variable alpha or a lower bound on alpha. And so this signature that uses an intersection type is actually the same as the following signature that uses an additional type variable C with two upper bounds, one from int to A and one from string to B. And similarly, the union type we saw before is actually equivalent to a type that quantifies over some extra variable B with two lower bounds. So this precisely encodes unions and intersections when they are restricted to positive and negative positions. And so basically this follows the idea of algebraic subtyping, which we reformulated in terms of upper bounds and lower bounds in previous work. Okay, so what are the challenges of implementing SuperF? There are many challenges. There are some risk of non-termination if you solve constraints in a naive way. And there's a risk of polymorphism extrusion. It's not clear how to do type check annotations. So actually, I don't have time to explain how all of these are solved. So look at the paper if you're interested. And first, let's talk about the limitations of SuperF, which is very important to talk about. Because no matter how you slice it, type inference for first-class polymorphism is undecidable. Most problems are undecidable. And so it should be expected that we have to make some concessions. And the concession we make in the case of SuperF is that there's a heuristic for termination, which looks at the subtyping constraints that are being solved at the current point. And if it sees something that looks recursive, it just aborts constraint solving and type checking fails. So this happens for the big omega combinator that you see here. It's an infinite loop, and it actually makes type checking infinitely loop, right? Because type checking in this case stays very close to the term and ends up basically simulating the term. So this doesn't actually trigger in practice very often, as long as you type recursive functions monomorphically. So you can type most ML programs. We actually conjecture that all ML programs are typeable in SuperF. And so it does make type checking incomplete theoretically, right? And the other restriction is on the syntax of type annotations. So the users can write type annotations in their programs, but it's very hard to check these annotations if they use bounds. And so we restrict the syntax of type annotations to systemf types, so that users cannot use actual bounds in their type annotations. And we argue that this is fine because functional programmers don't actually care that much about bounds in their polymorphic types. In Haskell, for example, there's no bounds, but there are many uses of first-class polymorphism. And you can intuitively think that systemf types with subtyping are like real numbers. And you need a bit more flexibility to infer types. So SuperF types with bounds are like imaginary numbers. And so they are non-denotable types that are here just for type inference. But at the end of the day, what you care about and what you end up with and what you use in type annotations are systemf types. Okay? So the SuperF is implemented in an existing programming language, and it's evaluated on many test suites that we extended. And for example, we also ported the OCaml list module. And it turns out that SuperF can handle, without any type annotation, all of the examples that were previously considered in the literature. So if you look at the blue columns here, SuperF has all the black circles, which means it type checks the programs without any problem. And so this is the first. Actually, the examples are too trivial, so we made the examples a bit more complicated. We added more complicated examples and to better exhibit the limitations of SuperF, but SuperF still does better than other approaches. Okay, I don't have time to talk about the soundness of SuperF. It's based on the soundness of system FCC by Crétin and Rémy from 2014. And yeah, let's keep this. Well, I don't have time for future works either, but my conclusion is that unification is dead. Long live subtyping, okay? And the end. Thanks for listening.
Thank you, Lionel. So we have time for questions.
Hi, thanks for a really nice talk. I'm wondering if there are situations where your constraints solving would loop, but somehow, but otherwise make something which you would consider to be progress, and whether, if that's the case, you could leverage some techniques from, say, the size change termination world or checking infinite descent in cyclic proofs to kind of work out when this is the case and so know when you could have a solution in those situations, as opposed to situations which are just true looping, like the omega situation you showed.
Right. I think that's correct. You could refine the heuristic to include some more advanced heuristics to determine whether the thing will eventually terminate or not. Because currently we abort constraint solving as soon as you have something that looks recursive, right? So we could refine this using the usual termination heuristics. We could. There are also other things we could do. For example, we could, instead of aborting constraint solving, we could undo polymorphism decisions that were made earlier, and that would allow to type check the big omega combinator. So that's yet another approach you could take to make things better. Or you could move to impredicative version of SuperF, which would probably give you completeness.
All right, thank you.
Hi, nice talk, thank you. So when we're programming, we do more than just type in code and watch it run. We have to interact with it. There's documentation systems that get generated. There's, you can query the type of something in some interactive system.
Right.
Have you thought about how these types might get presented to users, especially if they can't write them?
Yeah, that's a good question. So these bounds that we infer are actually a reflection of the control flow of the program. And we do generate type errors that understand this data flow of the types and explain things not in terms of bounded types, but in terms of which piece of type flows in which other position. There's a web demo that you can try that shows the system, and you can see that it gives good errors usually. So, for example, maybe if you write something like this, it will give you an error that traces the flow of the value and tells you exactly what failed during type inference.
That looks very cool. Thanks.
Thanks.
I'm willing to live without bounds, but I really like my intersections and unions. So,
right.
Can we extend this to algebraic subtyping, which has intersections and unions?
So the original algebraic subtypings doesn't really have intersections and unions any more than this system. It's just data flow types, basically. We did extend algebraic subtyping with proper first-class unions and intersections in a previous work, which is implemented in ML script. So you can actually do this in ML script. You do have access to unions and intersections, although you cannot use intersections to implement things like overloading, because that would be a bit too hard to do constraint solving and too expensive.
Mm-hmm. Thank you.
We also have a question on Discord. Your bounded polymorphism examples had only upper bounds on a variable or only lower bounds. How do you present them to the users when a variable has both upper and lower bounds?
So actually, what we present to users is usually unions and intersection types. So we don't actually present bounded types to users unless the type is recursive, in which case we will just write for all A and then list the bounds of A. So A is less than something and greater than something else. We just list the bounds, right?
Okay, could we get the AV for the next one ready while we take one more question?
Hi, so one thing you didn't talk about is like the algorithmic complexity of this kind of type checking. And like, I mean, what I remember from the works in the 90s about inference with subtype bounds, they tend to explode. So what's happening here?
Yeah, that's a good question. I don't have a very good answer to it. It's probably expensive. So the basic system, algebraic subtyping, is cubic, not considering checking things against a signature, which is actually exponential. Since our type inference approach checks, essentially has to include checking things against their signature because of first-class polymorphism. So it's for sure exponential to infer things in the general case. In practice, it's not that bad. If you restrict yourself to normal ML-style data types, as you can see in the web demo, you can experiment with it and see that it's actually very fast to update the results, right?
Okay, thank you.
Thanks, that's all we have time for on that one. So we could thank Lionel again, please. And the next talk is a pre-recorded video, and it's Henry de Jong will be presenting on the subject of parametric subtyping for structural parametric polymorphism.
Hi, I'm Henry de Jong, and I'll be talking about parametric subtyping for structural parametric polymorphism, which is joint work with Andrea Mordillo, Frank Bettig, and Ankush Das. Recursive types, parametric polymorphism, and subtyping are ubiquitous in modern programming languages. For example, the type stack alpha uses the first two of these features to describe stacks of elements of type alpha. In other words, a stack is an object that offers push and pop methods, where the pop method uses the auxiliary constructor maybe kappa to account for the possibility that the stack may be empty. Sometimes we might wish to ensure that a stack is used according to a specific protocol. For example, when implementing a queue with two stacks, all pushes should occur before all pops. This protocol can be described by the pushes beta and pops gamma type constructors. Whenever the first pop from a stack of type pushes beta occurs, the remaining stack has type pops beta, which does not offer a push method. According to the usual rules of structural subtyping, stack alpha is a subtype of pushes beta whenever alpha and beta are mutual subtypes. The direction of this subtyping holds because any stack that implements all of the operations can always be used in the specific context where a client expects to use only the operations described by pushes beta. Similarly, stack alpha is a subtype of pops gamma whenever alpha is a subtype of gamma. In other words, these two inference rules are admissible. Unfortunately, the combination of recursive types, parametric polymorphism, and subtyping is difficult to manage. Prior proposals include the material shape separation and the prohibition of contravariance. In this paper, we propose an alternative, a notion of parametric subtyping. The slogan for parametric polymorphism, in the style of Reynolds and Girard, is that related arguments are mapped to related results. Inspired by this, we propose parametric type constructors that follow the modified slogan related type arguments are mapped to related type results. Parametric subtyping is then the fragment of structural subtyping based on these parametric type constructors. It has several advantages, including its decidability and it being intuitive, having a relatively simple declarative characterization in terms of infinite derivations. That's the essential idea, but we can look at some specifics. It's helpful to first review a saturation-based decision procedure for structural subtyping of recursive types without parameters. Even and odd natural numbers are a simple example where even and odd should be subtypes of NAT. To verify that even is a subtype of NAT, backward proof construction would usually be used. But here we will use saturating forward inference because that's what will generalize to parametric subtyping. We will assume that even is a subtype of NAT and try to find a contradiction by inferring more and more consequences of this assumption. If we've reached saturation by inferring all of the consequences that we possibly can, and we still haven't uncovered a contradiction, then we will know that even is indeed a subtype of NAT. Expanding the definitions of even and NAT and appealing to inversion on the structural subtyping rules, we arrive at the consequence odd subtype of NAT. We can add odd subtype of NAT to the database because it involves two type names. And then we can consider it once more expanding and appealing to inversion, inferring the consequence even is a subtype of NAT. However, this even subtype of NAT is subsumed by the existing one. So at this point, we have reached saturation. No new consequences can be inferred, and because we still haven't uncovered a contradiction, we conclude that even and odd are indeed subtypes of NAT. Stated differently, even is a subtype of NAT, and odd is a subtype of NAT are admissible subtyping rules. Here, saturation is guaranteed because a given program uses finitely many type names. Notice in particular the property that no pair of type names was expanded more than once during this algorithm. Unfortunately, once we have recursive type constructors, we can't just use this same algorithm to decide structural subtyping. Saturation isn't guaranteed anymore because constructors make it possible to infer infinitely many pairs of types, such as T of NAT is a subtype of U of NAT, T of NAT is a subtype of U of NAT, and so on. In fact, we proved that structural subtyping is undecidable for recursive type constructors by a reduction from the simulation problem for basic process algebra. A related proof for a different problem has been given by Padavani. What can we do? One option is to impose a bound to cut off forward inference and force termination when the bound is reached. A major disadvantage of this approach, however, is that the accepted subtypings would then depend on the vagaries of the algorithm, making it very difficult for the programmer to understand and predict what are the accepted subtypings. It would be much better to find a fragment of structural subtyping that has a relatively simple characterization and is decidable. This is where our notion of parametric subtyping comes in. Recall the admissible subtyping rules from the stack protocol. The key observation is that these rules are parametric. in the sense that related type arguments are mapped to related type results. For example, this rule is parametric because it maps related type arguments alpha and beta to related type results, stack alpha and pushes beta. Thus, parametric subtyping is the fragment of structural subtyping in which the accepted subtypings are exactly those that hold parametrically. As a non-example, a monomorphic type NAT stack would not be a subtype of pushes beta under parametric subtyping because it would necessitate relating a type argument beta to another non-argument type NAT. This means that parametric subtyping has the flavor of a subformula property. Even though structural subtyping is undecidable for recursive type constructors, parametric subtyping is decidable. The decision procedure consists of two phases. The first phase is saturating forward inference to derive admissible subtyping rules, much like what we did earlier for even and odd. The second phase will then use backward construction of derivations from these admissible rules. To demonstrate, we will verify that stack alpha is a subtype of POPs gamma whenever alpha is a subtype of gamma. As before, we will make an assumption about stack alpha subtype of POPs gamma, but this time, instead of assuming stack alpha is a subtype of POPs gamma outright, we will progressively refine a set of constraints on alpha and gamma imposed by stack alpha subtype of POPs gamma. Initially, the constraints are trivial, represented by top. Forward inference here leads us to deduce that maybe alpha cross stack alpha is a subtype of maybe gamma cross POPs gamma. At this point, parametric subtyping means that we don't expand, but we instead consider a new parametric question about maybe kappa and maybe kappa prime. Forward inference here leads us to kappa is a subtype of kappa prime, and we add this constraint to our set of constraints. Returning to the postponed judgment, we apply the information learned about maybe and infer that alpha is a subtype of gamma, and stack alpha must also be a subtype of POPs gamma. Alpha subtype of gamma is a new constraint that we add to our set of constraints, and then we can recursively apply this rule to the remaining stack alpha POPs gamma, which yields alpha subtype of gamma again. But this is subsumed, and we've reached saturation. Because we've saturated, the totality means that these constraints are also sufficient, and we have derived admissible subtyping rules. Once forward inference saturates, phase 2 involving backward construction begins. For example, suppose that we want to decide whether stack maybe even is a subtype of POPs maybe NAT, because there is at most one admissible rule per pair of constructors. We can build a derivation, and this algorithm is guaranteed to terminate. Forward inference in phase 1 terminates because there are finitely many parametric subformulas. Backward construction in phase 2 terminates because it is inductive on the structure of the types. As a further example of parametric subtyping, we can look at serialized binary trees. In Haskell, we could define the type of ordinary deserialized binary trees like this. The serialized form of binary trees would then be described by the non-regular type S tree alpha kappa. We can also define the types of spines and serialized spines as spine alpha and spine S-spine alpha kappa. Spines are particular trees, and serialized spines are particular serialized trees. Our algorithm verifies this in terms of these admissible subtyping rules. To summarize, the main contributions of this work are to prove that structural subtyping for recursive type constructors is undecidable, and to propose parametric subtyping as a fragment for structural subtyping of recursive type constructors that is intuitive, decidable, and practical. We have implemented the decision procedure and have made it available online. Possible topics for future work include extension to Curry-style polymorphism, bounded quantification, and subtypings due to the uninhabitedness of certain types. It would also be interesting to see if this might be useful at higher order kinds and to see whether parametric subtyping can be integrated with intersection and union types. Thank you very much for your time.
Subtyping of session types, and we explicitly designed the system that it would capture that. And as you can see from the serialized tree example, this is actually a session type example that we reformulated in this style, because when you want to send a tree across a network, you serialize it, and then you deserialize at the end. And with these types, you can, the linear version of these types, you can type check this session type program.
Just following up from that question, I wonder if, in your experience, did you run into any obstacles based on the restrictions you have to be parametric? Were there any examples of protocols where you really wanted something more?
So there's two situations which come up in practice which you can't handle. So one example, if you have a type abbreviation, if you will, which is not recursive, so you might say an int pair is a pair of two ints. So you usually want to expand the type definition when you do type checking or subtyping rather than trying to treat it with this algorithm. And the other one is you have a very specific type like natlist, and you compare that to a list of alpha, which means your program was originally insufficiently general. And so usually in that case, you would refactor your code and you rewrite it in that style. So beyond those two kind of situations, we haven't really run into much that would be a problem.
Thanks.
We have a question from Discord. Can phase 1, the forward phase, be computed at time declaration time rather than at time usage time? Would that pre-computation be a good idea?
Yeah, so we don't pre-compute it. What you do is you compute it lazily. So when a given subtyping question is asked, you compute it and then you memorize it. So if the same question is asked later in the program, you have it there. Otherwise, you would pay order n squared essentially, or n cubed, if you do everything ahead of time. But you don't need to. You just memorize those that are actually asked, and then you go from there.
Okay, I think that's all we have time for. So let's thank Frank.
Okay.
One quick note, because the people sitting by the aisles, please move a bit inside because we have more people coming in and then they can find a seat without disturbing the talk. Thank you so much.
Okay. Yep. So should I go ahead now?
Okay, so the next talk is by Gabriel Scherer, and he will be speaking on the subject of constructor unboxing, or how CPP decides a halting problem.
Okay, thank you. So this is work on a low-level data representation feature for the OCaml programming language that led to a theoretical question that I found surprising. So the feature was designed and suggested by Jeremy Yallop over there. Nicolas Chatin was my master intern working on implementing it. I did some work with him and also on the theory side. And then Stephen gave a lot of excellent feedback that influenced the work in interesting ways. So first, let's talk about what's already available in OCaml without our work. So let's say you define a type ID that has a constructor ID carrying an int parameter. So maybe you have a list of size 1 whose first element is ID 42. Okay, and the constructors, this algebraic data type, they are used for the constructors are used for two things. The first is, well, they mediate between the type ID and int, which are different, and this is useful when you program. And they also, at runtime, let you know which case you are in when there are several cases. But here there is only one case, so maybe at runtime you don't need to know which case you are in. You are in the unique case. So since 2016, we support this unbox annotation that says, well, at runtime you don't need to care about ID. So in the source you still write the same thing, but in the data representation, the ID constructor is erased. And you can give a sort of space cost model for ML data types, where to store a value, the constructors with parameters cost 2 words, and a constant like 42 and nil cost 1 word. So you can see that you are going to pay 4 words to store this instead of 6 if you remove the unbox annotation. And you could ask, well, why is it this unboxing not an automatic thing that happens? The answer is that would break foreign function code that produces value using directly low-level representation, so you cannot change the low-level representation without telling anyone. Okay, so this is already around, and then Jeremy said, well, you know, we only know how to do this when there is a single constructor or a record field with a single field, but maybe we could do better. So we could have several constructors, and we could allow to unbox one or several of those. So here is the killer example, a big num type that is either a small integer, OCaml uses machine size integer, or a big number as implemented by the GMP library. And it's useful to have these two cases because GMP has still a fair amount of overhead, it's very fast, but still, compared to machine integers, it's slow. So as long as your computations stay within the bounds of the machine integer, you want to stay in the small case. But then, if you don't have this unbox annotation, allocating the small constructor and dereferencing its value costs a bit. So if you can allow user to unbox it, well, on a given micro benchmark, we saw a 20% time speed up. And then if you have a large program that is memory hungry, using less memory is going to be beneficial in more diffuse, interesting ways due to locality. Okay, disclaimer, for most programs in real life, you will not see any difference if you add unboxing annotations because functional runtimes are just very fast at allocating stuff, and the reference is not that costly when you have good locality. So in most cases, it's not so useful, but in some cases, an expert programmer can add this unbox annotation to speed up the program. But then you cannot just unbox everything. So maybe you extend your type T with ID, and you add an error case, and that carries an error code that is also an integer. So if you allow to remove both the error and the ID constructor, then at runtime you see 42, you don't know which case you are in. So that's a problem.
So if you try to do this, the compiler, the experimental version of the compiler that we worked on, will stop you and say this declaration is invalid, some unbox annotations, introduce overlapping representation. So how do you implement this static analysis? Well, we propose to do it in 2 steps. First, you design an abstraction of the set of values at a given type that we call head shapes. So this is a design choice that you make. You choose an approximation or an abstraction as a syntactic object. So you can think of this as abstract interpretation if you want. And then to check this declaration, you compute the head shapes of the unbox constructor, and you check that they are disjoint. And this abstraction that you design, you have to make trade-offs. So you could abstract all the types by just it's a type, and then you would reject all the unboxing constraints because 2 types have the same abstraction and they are not disjoint. So if you pick a more precise notion of shape, then you will allow more unboxing requests and you will make your user happy. But then what you have to teach them so that they can use your language becomes more complex because they need to understand what these head shapes are and what their meaning is. So there is a simplicity trade-off. And finally, portability. So if you give too much details in this abstraction about the low-level representation of your implementation of the language, maybe you will not be compatible with another implementation anymore. So in particular for Camel, we want to find an abstraction that works well for the upstream bytecode and native compilers, but also for the JavaScript backend. And this approach could be used in other languages to support the feature. Any ML family language or could use the same approach. And they would pick their own specific abstraction. So then, okay, so we have this idea. How do you compute the head shape of a type to check? So here is an example. I have a type of NRE trees, which are nodes of, well, a sequence of children and a value. So each child has a value attached to it, whatever. And then you have this type of sequences, which are either empty sequences or func that will on demand return you the first element of the sequence and the rest. And then you have some type foo that contains an integer tree with an unbox annotation. So to check that, the compiler needs to compute the shape of the data type in tree. So you say, oh, what's the shape of a tree? Oh, it has a single constructor that is unboxed. So the shape of that is actually the shape of the constructor argument. So you expand the definition, replacing alpha by int. And then, well, the shape of sec, well, that's either a nil constant constructor or the shape of a function. And this, simplified in our language of shape, you would say it's nil. The shape is an immediate value 0. And the function, let's say it's a block whose tag is closure tag. So that's easy. And that's easy, and what we did is to pick a definition and replace its formal parameter by its actual parameter. This is called beta reduction, okay? So actually what we did is to compute a normal form, head normal form, in, let's say, call by name. So in other words, you can reformulate this computation by first compute the head normal form of your type, and then it's easy to compute the shape from that. So you compute the head normal form of a type expression. This is nice. So you can represent this as a term in lambda calculus, okay, with flat rec. So above we have type declarations, and I'm reformulating them at the level of terms, okay? Well, you can see above we use the W's ML syntax where the parameter is on the left of the type parameters type, and below we use the standard lambda calculus syntax tree int. So this is just normalization in the lambda calculus with recursion. But of course, you can have recursive definitions of types, which translate to recursive term definitions that may not actually have a normal form, okay? So the problem is you don't want the OCaml compiler to loop indefinitely when you write a erroneous type definition. So how can you have it, well, compute the head shape but not loop indefinitely when there is no normal form? So this is the simply typed lambda calculus with just functions, no booleans, no sums, no integer, whatever. You have let rec, and actually we're in the first order fragment because in ML, the parameters of data types are not themselves used in function application in the definition. So quick show of hands. How many of you think that this, the problem of deciding termination in this fragment is decidable? And how many would say that is undecidable? I can give you a hint. So it's the first order restriction does not matter. It's the same in the higher order case. Okay, so many people are sleeping and they don't want to use the hand. Or they think it's dangerous to give so the first thing we said is, well, maybe we can make the problem go away by forbidding cycles, but in fact we like recursive data types and we want to be able to inbox them, so this is not good enough. And then we said, okay, let's just reduce the type, and if you see the same types occurring twice in the reduction sequence, well, you are cycling and you stop. This is not good enough to prevent termination because you can use so-called non-regular recursive types, like bad A is bad of prod AA, and this, if you start from bad int, will reduce to an infinite sequence of types that are all different. Then you say, well, okay, the problem was the type is always different, but the bad head constructor is the same. It shows up again and again. So let's stop when the head constructor shows up twice. So the problem with that is that there are perfectly fine definitions like this. Identity of A is A, and foo is ID of ID int. Well, first you reduce foo, and you haven't seen any head constructor yet. So you reduce that to ID, ID int, and you remember that you reduce foo. And then you reduce ID, so you get ID int, and you remember that you reduce foo and ID. And there, the algorithm stops you and say, well, you already reduced ID, so there might be a loop, stop. And this is not good enough. There are type declarations where this kind of pattern shows up in practice, and you don't want to reject them just because you should have used fuel instead of trying to be principled about this. Okay. So the last iteration of this ID is the one we used in the end. The idea is to track not just the head constructor that you expanded at the top level of the term, but for any sub-expression in the term. So I changed the example just a bit. So delay of A is ID, ID A, and foo is delay of int. So you start with foo. Can I use function pointer? Yes. You start with foo. No. Okay, let's not do that. You start with foo, and then you go to delay of int. And these two terms, so the int as a subterm and delay of int as a subterm, they appeared in my term when I expanded foo. So I use the trace foo for both of them. And then you expand delay. So all the ID subterms that occurred when I expanded delay. So in that trace, I have foo and delay. But the foo int argument of the delay, it was already there before, so its trace does not change. So you get ID, ID int with these traces, and then you reduce the application of ID, but ID does not create any new subterms. It's just returning its argument, so the argument has the same trace as before. And then you can reduce ID again, because in the trace of the ID int term, you never reduced ID yet, so you can reduce it again, and you get to a normal form. So this algorithm, it works in practice. It accepts all the examples that we wanted to accept. It rejects all the cycles that we thought of. So we were very happy with that. And we were hopeful that it was actually guaranteeing termination. And Steven remarked that this is similar to the way an obscure algorithm from the 80s has been proposed to check termination of macro expansion in the C preprocessor. Okay. So we proved that this algorithm is sound, that it ensures termination, and it's complete in the first order fragment, which is the fragment we care about, in the sense that if it rejects an input, or if it stops before reaching a normal form, then actually there would have been a cycle, a loop in the definition. So, okay, is this problem actually decidable, if we can have a sound and complete decision procedure? Answer is yes. So when you are surprised by something and you don't know why it is the case, you can ask types list about it. So I did that, and we got excellent replies by Pablo Barenbaum, Martin Leston, Gordon Plotkin, and Sylvain Salvati, who said, oh, but this is a well-known thing. Simply typed angular calculus with just functions, and LETREC has decidable halting problem. Okay, so well-known by not me. Actually, there is a whole scientific community working on higher order model checking, which are harder versions of this question. And there is a paper by Gordon published in 2022, but it says that that it's actually notes that were written 40 years before that explain that in a fairly readable and understandable way if you are not familiar with tree automata and MSO and whatever. Okay, so one thing that is interesting to be said about this is that we looked at, for example, the bound, the bound on the normal expansion that is implicit in the proof of Gordon, whether that is clearly explained. It's the height of a lattice, and we compare it to our algorithm. And in general, our algorithm reduces less before it stops and say, oh, there is a cycle. So it's more efficient on the first order fragment than, let's say, Plotkin's algorithm. And we don't really understand yet whether, well, there is a better algorithm that people already know in this community that coincides with ours, or maybe ours is specific to the first order case, or maybe we could sort of generalize it to a slightly more efficient high order algorithm. I'm done. Thank you.
Great, so we have time for questions. Caroline, there's one on this side.
I'm afraid I have a very simple, dumb question. So one thing I just didn't understand earlier on. So if you unbox a data type with two constructors, and you're saying you're allowed to do that if they're different types, they have different head shapes, how does the implementation then do that distinguishing without having a tag to look at in the runtime?
So the language of head shape that we picked has two properties. First, we can decide non-disjointness statically. And then the reason why two things are distinct is easily checkable at runtime. Because the approximation that we use is basically, well, look at what's the header in the value, whatever. So the pattern matching compiler that has to make this choice at runtime can well, check disjointness dynamically by looking at this information.
Okay, so like an int and a float wouldn't be distinguishable or something like that?
So in upstream OCaml, yes, you can. In JavaScript OCaml, no, you cannot. So probably we will want to forbid you from forbid the inboxing checking from assuming that you can distinguish them to get portability.
Okay, awesome, thanks.
Thanks for the nice talk. So I was wondering if you could say a bit more about what types you can now actually represent unboxed and how that compares with other languages that do at least superficially similar looking things. Like Rust has all sorts of enum layout optimizations, and option bool can be stored in a single byte and things like that. And maybe that's something OCaml could already do before that. I'm not entirely sure there, but like what does this look like now?
Yeah. So there is a discussion in the paper about niche filling and whether you can see niche filling as an instance of this with a well-chosen abstraction. There is some related work by that was at ICFP on data layout description language that was instantiated with both OCaml and Rust, and that you might have heard of, and that is maybe going more in this direction. One thing I want to say is that no, OCaml does not let you unbox the option type because of this very compositional compilation approach with uniform representation and no separate compilation. So we do not monomorphize or specialize aggressively. So that restricts a lot the things you can do. But this unboxing question is sort of orthogonal in the sense that if either you are in a language where you are more aggressive with your specialization, or you allow yourself, when you have a type parameter, to add sort of constraints about, oh, I assume that the shape of this parameter will be this and that, then you can unbox more. Okay, so they are sort of orthogonal.
We have maybe time for one short question, Neil.
So are the unboxed things all still one word? So if you unboxed a record, it would still be a pointer, or does it lay it out as multiple words?
No, you can only unbox if So for variants, if there is a single parameter, and for records, if there is a single field. So in each time you have one word, yes. Because OCaml values goes back to the uniform representation, they always fit in one.
Oh, okay, so that's to make polymorphism efficient. Okay.
Okay, let's thank Gabriel again. And the final talk of this session is going to be given by Michael Laurent, and it is on the subject of polymorphic type inference for dynamic languages.
Thank you for the introduction. So this is a joint work with Giuseppe Castagna and Kim Nguyen. So let's start with some motivation. I have written here a function in JavaScript. It simulates the behavior of the logical OR. So it takes two parameters, x and y. First, it converts x to a Boolean. If it results in the value true, then it returns x. Otherwise, it returns y. What we want is to type this function. But first, let's focus on toBoolean. So toBoolean is a function that takes a parameter. If it receives the value false, null, 0, the empty string, or some other values, it returns false. And for any other value, it returns true. What we're going to do is to give a name to the set of values that converts to false. We are going to call them falsy. And the other values, we are going to call them truthy. And now we can give a type to toBoolean. We can type it with the following type: falsy to the singleton type false, and truthy to the singleton type true. So here we have an intersection in the type, and it is used to capture the overloaded behavior of toBoolean. The first branch, falsy to false, describes its behavior when we give it a falsy value, and the second branch, truthy to true, when we give it a truthy value. So now we can try to type the logical OR function. The type we want to give it is the following one. So this type is both polymorphic and overloaded. The first branch describes the behavior of logical OR when the first parameter is a truthy value. And in this case, this type says that it returns exactly the first parameter. And the second branch corresponds to the case where the first argument is falsy, and in this case, it returns the second argument. If we want to be able to derive such a type, we have to overcome some challenges. First, we have to perform type narrowing. Indeed, when we type the first branch of the type case, the return x, we should assume that x is truthy. It is the case because if x was not truthy, then it would have taken the second branch. In order to implement that, we will use union types. We will see that later. Also, we want to capture overloaded behaviors. And as we have seen, we do that using intersection types. And also, we want to capture genericity in order to be modular. And for that, we use parametric polymorphism. Okay. So now let's define our types and language. We will use what we call set-theoretic types. So set-theoretic types provide the usual construct. So we have the base type, the singleton type, the integer, etc. Then we have the type variables. We have the arrow for function and the product for pairs. But they also provide a way to express the union of two types, the intersection of two types, and the negation of a type. Also, we have the special type empty that has no inhabitant, and its negation any that is the type of all values. We can define the subtyping relation on these types. It has been done in prior work, so we will just assume that we have such a subtyping relation. Now for our language, we will use the usual call by value lambda calculus with an additional construct for type cases. The semantics of type cases is as follows. First, we reduce the test expression. If it results in a value that has type T, then it reduces to the first branch, and otherwise to the second branch. So now let's build the type system. We start with some usual rules. So we have a rule for constant, for variable, for lambda abstraction, and for application. Also, as we have subtyping, we have a subsumption rule. Now we are going to add some more rules in order to increase the expressivity. So these rules are from the natural deduction logics. The two first are used to implement prenex polymorphism and come from in-the-Milner systems. The third one comes from intersection type system, and the last one from union type systems. So none of these rules are new. They all exist from prior work, but our work consists in combining them into a single type system. So let's see that in more detail. For polymorphism, we have two rules. A gen rule that allows to generalize type variables of top-level definitions. And then we can instantiate them with an instantiate rule in a later definition. Then we have the intersection introduction, which states that we can derive the type T1 and T2 for the expression E, if we can derive the type T1 for E and the type T2. And lastly, we have the union elimination rule. Given an expression E, this rule allows to select any subexpression E prime and to decompose its type into a union, S1 or S2, and then we can treat each case separately. So first we type E by assuming that this subexpression has type S1, and then we type E again, but this time by assuming that this subexpression has a type S2. This union elimination rule allows to perform type narrowing and to type cases. The idea is as follows. We combine this rule with two simple rules for type cases. The first one corresponds to this special case where the test is always true, and thus we need to derive the first branch, to type the first branch. And the second one is the opposite case. When the test is always false, in this case, we only need to type the second branch. Of course, these two simple rules alone do not capture the general case, but in combination with the union elimination rule, it does. We can see that with an example. Here we have a simple function. It takes a parameter x. It tests whether x is an integer. If it is the case, it returns x plus 1. Otherwise, it returns false. So we want to type it for the domain any. So we enter in the lambda with the rule for lambda abstraction, and we assume that x has type any. But no, we cannot type the type case directly because we are not in this special case. So instead, we apply the union elimination rule in order to study separately the case where x is an integer and the case where it is not an integer. And so for the case where it is an integer, now we can type the type case using the first type case rule. And note that the first branch is typed under the assumption that x is an integer. And then you can treat the second case where x is not an integer. And this time we type it using the second rule for type case. And in the end, we are able to derive the type any to int or false for this function. But actually, there is another way to derive the type for this function, this time by using the intersection rule. So we are going to type it again, but this time we just want to type it for the domain int. So we enter the lambda and assume that x is an integer, and we can directly conclude with the first type case rule. And it yields the first type for this lambda expression, the type int to int. And now, independently, we are going to type it for the domain not int. And here, again, we can conclude directly with the second type case rule, and it yields the type not int to false. And as we have two types for the same lambda abstraction, we can combine them by applying the intersection rule. So, as we have seen, there are several possible derivations which may yield different types. And this is an issue because we want an algorithm. Actually, there are several sources of non-determinism. First, some rules can be applied on every expression, making the system not syntax-directed. This is the case of the union elimination rule, the intersection introduction, the instantiation, and the subsumption. Also, in some rules, some premises cannot be guessed from the conclusion. This is the case, for instance, in the union elimination rule of the type decomposition, or it is the case when we have a lambda abstraction, we have to guess the type of the parameter, or in the instantiation rule, we have to guess a substitution. So now the challenge is to make the type system algorithmic. In order to do that, we have to choose a strategy. What we choose to do is to apply the union elimination rule once on every distinct sub-expression. And by doing that, we do not lose any generality. In order to help us to implement this behavior, we are going to transform the expression we want to type into what we call the maximal Turing canonical form. It is a form which gives a unique name to each distinct sub-expression. So for instance, for the pair f of x, we first define f of x and bind it to the variable u. And then we define the pair u and bind it to the variable v. The advantage of this form is that now we can just apply the union elimination rule once on every bind expression. Okay, but still we have to guess a type decomposition out of nowhere. And for lambda abstraction, we also have to guess the type of the parameter, etc. So in order to solve this issue, our algorithmic type system is going to take an additional input. So in addition to the maximal Turing canonical form, it is going to take an annotation tree, and both together, these two elements will uniquely encode a derivation. So here, for instance, we have on the left the maximal Turing canonical form consisting in a binding, and on the right we have an annotation tree which says which type decomposition to perform, and so it yields the derivation below. But now we have only moved the issue because now we have to infer these annotation trees. Okay, so I'm just going to cover the main ideas. So we have to infer the type decomposition to apply when we apply the union elimination rule. And for that, we will look at type cases. When we encounter the type case z in true, then x else y, what we're going to do is to backtrack to the definition of z and to split its type into true and not true. Okay. And also, we have to infer the type of parameters. And for that, we will use what we call tallying. And basically, it is like unification, but with subtyping constraints. So for two types T1 and T2, we want to find all substitution sigma, such that T1 sigma is a subtype of T2 sigma. It is decidable. We can compute the solution, and the solutions are characterized by a finite set of substitution. So let's see that with an example. It is the example from the introduction, and we want to infer the types of the parameter. So first, we start by typing x with alpha and y with beta. And then we want to type two Boolean of x. So for that, we generate a tallying instance that encodes the fact that this application is well-typed. And then we solve this tallying instance. And in this case, the solutions are characterized by two substitutions. The first one that suggests that alpha should be substituted by alpha prime and true phi. And the second one that suggests that alpha should be substituted by alpha prime and false. And so now what we do is we backtrack to the definition of x, and we treat each case separately. So first, we type the body again, but this time by assuming that x has the type alpha prime and true phi. And in this case, we can type it until it yields the type alpha prime and true phi. And then we type the body again by assuming that x has the type alpha prime and false. And in this case, it yields the type beta. And so we have two types for this function. We just take the intersection, and we have inferred the type from the introduction. So in conclusion, we have defined a declarative type system that mixes union type, intersection types, and polymorphism. And we have proved some type safety theorem for it. Then we define an algorithmic type system that is sound and complete, but that require annotations. And so then the last part is to infer this annotation. And for that, we use tallying and backtracking. So our inference algorithm is not complete, but it is terminating. But as it is not complete, sometimes we might need some user type annotation to help it. It has been fully implemented in OCaml, and you can test it online. No need to install anything. And to finish, I want to highlight some ongoing work. We are working on supported side effects because in this work, we assume that our language is pure, because if the language is not pure, the use of union elimination must be restricted in order to be sound. Also, we want to add how polymorphism for records, to type records, because records can be used to encode objects, so it is useful, and we want to type them precisely. And lastly, we are working on applying it to real-world languages, such as Elixir or Python. Thank you for your attention.
Thanks, Mikhail. So we have plenty of time for questions.
Thanks for the talk. I have two small questions. The first one is about complexity in general. It seems that even just checking subtyping should be maybe exponential.
It is. So yes, we have no theoretical guarantee for complexity. So yes, even just the subtyping is exponential. So in practice, we don't want types that are very complex. We don't want types that has many overloaded intersection. I think it's not readable for the user. And so the challenge, we have to find the sweet spot to keep type as simple as possible, but still sometimes we will need some intersection, but there is a sweet spot to find in order to have good performances.
Thanks. Are you using SAT or solvers or specialized procedure, or just something that in your actual implementation to decide?
We do not rely on any external solver. Actually, we use, in my prototype, use an implementation of set theoretic types that has algorithm to decide subtyping. So I just use this library to decide subtyping, and otherwise there is no dependency.
And secondly, do you know if your type system has the property that every expression always has the smallest type? Is your lattice of types complete in a sense?
We do not have type principality. So for some expression, yes. For instance, if you want to type the map function, you can say that just it takes a function from alpha to beta and then a list of any number of alpha, and it returns a list of any number of beta. But you can also say that if you give it as second argument the empty list, then it returns the empty list. And you can also say that if you give it a singleton list as first argument, it returns the singleton list as second argument, etc. And you can do infinitely many intersections. Each time you have a more precise type. But so we don't have type principality because we would need infinite intersection.
Makes sense. Thanks.
So I wanted to ask you again, maybe a related question about the performance of the intersection and union types, because your type inference algorithm has a lot of backtracking in it. So when you've used it, have you found that like it's very sensitive to the order you write the unions in, or things like that?
It is not sensitive to. So the types used are not syntactically defined. It is set theoretic types. So the subtyping is semantic subtyping. So the order of things, it might impact the performance, but I do not really have the very much control on it. We always reason modulo semantic equivalence. So then it's the set theoretic types library that should try to optimize it as it can. And yeah, for the performances more generally, it works well as soon as it can really take a lot of time to infer sometimes if we have, for instance, recursive function with a lot of first order parameters. In this case, the inference tries to do too many branches. It is, and so it will not terminate in a reasonable type. But then the user can help it and add type annotation. And in this case, it cuts a lot of branching and backtracking. And in the end, if the user annotates every parameter, the performance are good.
Okay, thank you.
So if there's one more quick question, we could take it.
So in Erlang or in Elixir, this notion of a hot code swap,
where you compile some program at runtime and switch a module, right? Is there a way of typing such a thing? Let's say, okay, I'm going to compile the program, it has type any, and I mean, at the moment, there's this tool called Dialyzer that will sort of success type an Elixir program. But
I'm not sure to understand. Can you reformulate, please?
Yeah. So I receive a term, right, from I wrote a distributed program. I receive from a different machine a term, right? I cannot know the type of this term. And sort of Elixir programs can compile other Elixir programs at runtime. So then, can I give this new program type any?
Yes, you can type. You can type any program. I mean, there is the typing of values. There is two different things: the typing of values and the typing of expression. So for determining when we have type cases, and we test whether a value has the type of the type case or not, it uses a very simple typing. We just basically type any lambda abstraction with empty to any. And so for runtime checks, it's a very basic type system where everything can be typed with any. But if you for expression statically, we cannot type anything with any because a lambda abstraction must be well typed in order to be typable. But we can add graduate typing. This has been done. I have not integrated it in my prototype, but you can add graduate typing with a joker type that allows to type anything with this joker type and then or dynamic type. It depends on how we call it.
Thank you.
Okay, let's thank Mikael again. And that concludes the session.
Hi, everyone. Welcome to the session. We're going to be kicking it off with efficient CHAD. I'm going to turn it over to Tom, who's going to tell us all about his work.
Yes, thank you. This will be a talk about automatic differentiation, in particular about the algorithm called CHAD. So in this idea of automatic differentiation, which I will be shortening to AD because the name is kind of long, and specifically in reverse mode AD, we're interested in a program that takes in a number of real numbers and returns a single real number. So we're considering this as a normal mathematical function, right? A thing that takes a bunch of reals and returns a real. We might be interested in its derivative, specifically in its gradient. This is a function that takes in the same kind of input and returns a value in Rn, which is the gradient of this original function, considered as a mathematical function. It just happens to be implemented as a program. And reverse mode AD refers to a family of algorithms that tries to produce gradient programs that compute these derivatives efficiently and in a way that is numerically stable. And for these reasons, reverse AD algorithms are very useful in a variety of disciplines. It is this idea of efficiently that I will be talking about more in this presentation, specifically about the computational complexity of this gradient algorithm. So as the PL community, when we think about reverse AD algorithms, a number of things that we might be interested in is asking whether these algorithms are correct, so whether we can reason about them. For that, it also helps if the algorithms are compositional, because then they're easier to think about, they're easier to extend. And if you want to extend these things, you're probably also interested in thinking about whether they are flexible, whether they can handle a variety of interesting input languages that have various kinds of, well, interesting language constructs. Moving down the list to more practical concerns in a certain way, we're also interested in these things having correct time complexity, and what exactly that means I will be elucidating a few slides further on. We're interested in whether these things are parallelism preserving, because in many applications of AD, you're interested in situations that have lots of data, you have programs that are parallel, and you want their derivatives to be parallel as well. So we want to preserve the parallelism when differentiating programs. And finally, of course, you want, well, the programs to be practically efficient as well, which is, I guess, a very practical concern. So there is this CHAD algorithm, which has a variety of nice theoretical properties, but so far it did not have the more practical properties on this list. And in this work, which is called Efficient CHAD, we tackle these two, which are about the correct time complexity and about the parallelism preserving aspect. So this part, where the time complexity is preserved, we have proved this formally in Agda, and you can see the details about that in the paper. This part is future work, but the fact that we want this to be practically efficient as well is always in the back of our minds when thinking about the transformations that we apply. So let's look a bit about CHAD and see what it means, right? So we had this situation where we're thinking about a program, and we had this gradient program that we wanted to get out. In order to make this compositional, we have to generalize this a little bit. In particular, instead of immediately producing this gradient, we want there to be an additional argument, which is sort of the derivative of the function result. And we want to push this backward through the function to get back at the input, which is then the derivative of the input, which is the gradient. So now that we have this separate argument, we can generalize this a little bit. And now we can handle functions from Rn to Rm, which is already a bit better. Now, unfortunately, well, not sure if it's unfortunately, in AD, what you're doing is you're applying the chain rule many times over and over, and in the chain rule, it turns out that you need the original value of all the intermediate points in the program. So in addition to this backpropagator, this function from Rm to Rn that we return here, we also need what's called the primal value, which is the original value of the program at this point. So we return a pair here. And then we can generalize a bit further. We can generalize the domain to sigma. We can generalize the codomain to tau, where these primed versions are their derivative types. And now we basically have arrived at the type of CHAD. So the only thing we need to do is generalize this sigma to the context gamma. And then we have CHAD, which takes in a term in the context gamma and of type tau. And then the code transformation returns a new term in the same context, which produces a pair, which is the original function value and this backpropagator. And this D2 type transformation is a mapping from types to types, which produces sort of the type of derivatives of this type. So what do I mean when I talk about the correct time complexity? So in the imperative world, this is a concern that is relatively easy to express. If you have a program which consists of a number of steps, then the derivative program will also consist of a number of steps. And first, you're just going to do the steps of the original program in order, saving the intermediate results. And then afterwards, you're going to do the steps in reverse order, the derivatives of these steps, which are going to reuse earlier results, right? And so because of the properties of how large these steps are, you can see that the size of the program on the right is proportional to the size of the program on the left. So the time complexity is like you have a constant factor overhead from this transformation. This is something that you want, but this doesn't at all translate to the functional world because contrary to this, we're not interested in sequencing things, we're interested in nesting things. That's what we do when we talk about functions. So what happens when we look at something like chat? This is a type of the chat program transformation again. So let's look at one of the rules. This is the one for variable references. If we have a variable reference x of type tau, then the transformation of this is, of course, a pair, because we need to produce a term which is of pair type. The primal of this is simply a variable reference again. And the backpropagator here, the dual, is a function which takes in the derivative with respect to this variable reference. And it needs to produce a derivative with respect to the context, which in this case is simple. It is a one-hot vector. It is a vector that contains this value d at the place that corresponds to x and zeros everywhere else, abstracting a little bit over how exactly this d2 of gamma is represented. The second thing that we can look at is the derivative of a pair projection. So first, in this case, so we first compute the derivative of the term t, which produces this x, which is the pair, and this f1, which is the backpropagator of this pair. And then what we return is a pair consisting of first x, which is the primal value of this term. And we return a backpropagator, which takes this derivative d with respect to the first component of the pair, then builds d comma 0, which is the derivative with respect to the entire pair, and then passes that thing to f1. This is all well and good, it seems. And you can look at the rules for many of the other constructs as well, but I will not go into those in detail. The things that I want to highlight is that in order to get some kind of inductive proof of this time complexity property here, we would like the right-hand sides to be proportional in time to the left-hand sides. And is this true? Well, not quite. There's a bunch of things here which are too expensive. So what we would really like here is if, apart from all of the subterms, right, the transformed subterms only occur once on the right-hand side. So you really want all of the other work that happens on the right-hand side to be proportional to all of the other work that happens on the left-hand side. And it happens to be all constant time, so you want all the other work to be constant time on the right-hand side as well. Is that true? Unfortunately not. There's a bunch of operations that are not. For example, these one-hot vectors that I was talking about, they are much more expensive now, or at least in a naive representation of things. You have a variety of zeros that you need to create, both of normal derivative values as well as for environment derivatives, these d2 of gammas. You need addition of a variety of things. You need addition of normal derivative values and also additions of environment derivatives. And both of those are fairly expensive. And finally, here at the bottom, you also need to split an environment derivative in the derivative component that belongs to the thing that you just bound, for example, in a lab binding, and the rest of the context. So you need this for scoping operations. All of these things are now expensive, or most of them are, and we need to make them cheap. Thank you. So on the right top of the slide, you see a list of operations that we need to make relatively efficient. So the first thing that we're going to do is we're going to look at the zeros. And to tackle the zeros, to make them efficient, we need to add sparsity to our definitions. So far, the derivative of a pair was simply a pair of derivatives, which means that if you have a sparse derivative of some relatively large product structure, it looks like this. There's a whole bunch of zeros in there. And what you actually want is you want to represent that sparsely. For a whole subtree that is 0, you just want to cut that away and prune that and say that it's 0. So in effect, what you want is you want this. You want to stick a maybe in between this layer of the tree and the rest. So in essence, you're adding a point to this derivative type, which represents a 0, so that you can sort of inject a 0 somewhere cheaply. What this does, right, and then the other thing that you want to do is you want to do the same thing for environment derivatives, which are essentially large products, right? It's a vector, it's a large product of environment of derivative types. You can represent that sparsely as well by using a map data structure, which is essentially a sparse vector. So what you get from this is you get that zeros are now constant time. Yay, we've done 2 out of 6. And also it turns out that one-hot environments and splitting environments is also constant time, so we're actually 4 out of 6. We're well on our way. Second thing that we're going to do is we're going to eliminate all uses of environment vector addition. How are we going to do that? We're going to do that by state passing. So instead of creating lots of environment derivative vectors in a variety of places in our derivative program, we're going to create one at the beginning of our derivative program, in the beginning of our first backpropagator, so to speak, and then pass it through the program, adding individual contributions to it as we go, and then in the end return the result. So we can do this by lifting the backpropagators to monadic code, and all that changes is, well, a lot of the program transformation doesn't change, and in the backpropagators we need to lift that to monadic code. But we know how to do that as PL people. There's nothing really interesting going on here. There are a few individual operations that you have to reformulate into something else, but those are local changes, and the only global change that's happening is lifting to monadic code. That's it. What do we get? Well, we don't have environment addition anymore, so yay, I guess. And then the final thing is that we still have additional derivative values that we have to fix, but I am claiming that we don't have to fix that, because this slide says complexity proof. So let's just go through this, and we'll see where it ends up. So if you want to write a complexity proof for this, you need to have a cost model relative to which you write this complexity proof. So in the formalization, we wrote an interpreter of our simple extended lambda calculus that also returns the number of steps that were taken in evaluating the thing. And then we have a very conservative, simple cost model that does the job. You try an inductive proof, which is, of course, the thing that you want in this setting. It doesn't quite go through because you need to generalize the induction hypothesis a little bit. This is usually not surprising, but the way that we do this here is slightly finicky. It turns out that there's a fairly subtle argument that you can give, well, whether this subtle may depend on subjective preferences. There's an amortization argument that you can give. In particular, you can amortize the addition of the environment of derivative values against their creation earlier in the program. And just for the experts, this happens to work because you're passing those around linearly in a certain sense. So the amortization argument does end up working. This is the reason why I wanted to formalize this, because this felt tricky. So that means that basically without work, we have made the last operation efficient because we could amortize its cost away against other things. Finally, the last thing is that there were a bunch of logarithmic factors in the complexity that we accumulated because we chose a sparse tree value as the representation of environment derivatives. So we replaced those with a mutable array, for which we, again, don't need to change the code transformation because it is already in monadic form. We just extend the monad a little bit. And then we are done, and then we're happy. Yay. So this is my final slide. There's a bunch of things that did not fit in this presentation, but that we do have in the paper. For example, we have coproducts and the dynamic control flow in the paper. We have arrays and parallel programs. And we have higher order programs, which you can make efficient by closure conversion for the chat enthusiasts. where I unfortunately have to note that the active formalization of the proof is only the base language, including co-predicted conditionals, and it does not extend to arrays and higher order functions yet. And in ongoing work, well, we might want to extend the proof, and there's also a list of other things that we might be interested in. So thank you.
Great. We have some time for questions. Does anyone have a question? Yeah.
Thanks for the talk. At the beginning, you make it sound like sparsity is important, but then in the end, you replace the sparse tree with a mutable array. So could you tell the whole story without mentioning sparsity at all?
I see. Good question. No. Sparsity is important. And in particular, for simple product types, we keep the sparse representation. You do need, well, so there's a tension here between wanting a representation that you can in constant time add stuff to, and specifically for environments that you also need to split elements off, right? So you can have sort of a free you can have a free monoid representation of a variety of things. And that works for most things except for the environment derivatives, because you also need to split stuff off. And that's why we need a mutable vector there. For arrays, you do end up with sort of free sparse things.
Great. So there's a formulation of this work where you don't have explicit environments, but where you do with point-free notation instead, and then you basically implicitly thread the environment through. Would that make any change to how you would reason about complexity?
So you're thinking about the combinator representation of
this?
Yes. Yeah. I haven't looked too closely into that, but the first thing that I concluded when looking at the combinator representation of this algorithm is that the translation from lambda calculus to combinators is not complexity preserving. And at that point, you've sort of already lost. So I looked at the lambda calculus version only.
Thanks.
Any other questions? I have one quick question maybe for you. So this is a beautiful result that kind of is very deep and very technical, right? It's showing that, that you've actually preserved this complexity of the reverse mode differentiation. And I'm curious, do you see a pathway for this into potentially tools, right? I'm asking you a very hard question here, but I'm curious just to hear your high-level viewpoint on this, to just kind of see where you think it's going, right?
Yeah, I hope that later in my PhD I will be able to write exactly that paper, but who knows, right? No, there is, the things that I'm presenting here are very much fixing the complexity of this algorithm, but are not necessarily super efficient. So I should definitely add a disclaimer that there are, of course, lots of practically efficient reverse ID algorithms that are used in practice. And the reason that I'm not looking at those is because this one I can actually understand as like a single person. I don't need 100 Google engineers to understand the algorithm. So how I think about this thing being maybe at some point practically efficient. So the first thing that you have to do is there is this here. If you look at the rules, there's lots of lambdas here. You want to get rid of those lambdas because you're introducing higher orderness where there was none. It turns out that you can, so that's good. You want to partially get rid of the sparsity, like locally, because adding lots of maybes is probably not a good idea. I hope that a compiler pass will help there. I have some other ideas, but it's a bit fuzzy so far.
Perfect. Thank you so much. Let's thank the speaker again.
Do you need it? Yes.
All right, great. Our next speaker is Zhonghui. He's going to be telling us about ReLU hole approximation.
Hello, everyone. I'm Zhonghui Ma, and I'm a PhD student from the University of Queensland. I'm very glad to be here and talk about our research about ReLU hole approximation. Neural networks have been a critical technique in many fields due to their high performance. However, like programs, they face a great security threat. For example, adversarial examples. For humans, these adversarial examples just have some noise when compared to normal examples. But for models, these adversarial examples cause wrong results. Because testing can only check finite samples, we need verification. So what is neural network verification? Verification mathematically guarantees the correctness of models. A typical property is local robustness, which means a sample with a tiny perturbation should keep the same result as a sample without perturbation. However, neural networks verification has two main difficulties: non-enumerable perturbation and non-linearity of neural networks. To resolve perturbation, constraints are used. The exact approaches takes the two linear pieces of the ReLU function as two cases. For example, the exact approaches utilize SMT or MILP. So they are often low efficient when resolving large networks. Approximate approaches utilize linear constraints to over-approximate the behaviors of neural networks. Our work is based on the combination of bound propagation and linear programming. The goal is to verify the lower bound of the target label is always bigger than other labels. Then, how to construct linear constraints? A basic idea is to construct linear constraints by considering the nonlinear activation function with its input and output variables. The single neuron constraints only construct the constraints involving one neuron. In this work, we consider the relations among multiple neurons, that is, multiple neuron constraints. Today, we specifically talk about the case of the ReLU function, that is, how to construct the convex hull of the ReLU function. We call it a ReLU hull. We name our approach ReLU hull, meaning that wrapping the ReLU hull. The problem is to calculate the constraints of ReLU hull approximation with the given input polytope. Our insight is to utilize the linear pieces of the ReLU functions as lower faces and construct the upper faces, which are adjacent to the lower faces. We will construct the upper faces by the edges and vertices of the lower faces. The lower faces mean they provide a lower bound to the output variables. The upper faces mean they provide an upper bound. We gave the following example to show the process of calculating the ReLU hull in 3D space. Note that the two linear pieces of the ReLU function are important, and we use them to find other faces. First, we obtain two lower faces P1 and P2 by two linear pieces of the ReLU function. Then we identify their edges and vertices. We will try all combinations of edges and vertices to determine the upper faces, which are adjacent to the lower faces. We utilize a function to represent a plane crossing an edge, and this plane determines one upper face. We begin with f1 and try each vertex to calculate the beta value. There are 4 cases of different beta values. Just look at this precise. We found the upper face based on the minimum beta. Here it's 2. Similarly, for f2, f3, and so on. We will get 6 planes. After removing the repeated ones, we get 3 planes. Finally, we convert these 3 planes to constraints plus 2 lower face constraints. y1 is greater than 0 and y1 is greater than x1, which are the 2 linear pieces of ReLU function. So we get 5 constraints of the convex hull. In this example, our approach is exact, but our approach can resolve high-dimensional cases. In high-dimensional cases, we cannot guarantee the exactness of our approach. We have proved the general high-dimensional cases are the same as this running example. There are 2 types of faces, lower faces and upper faces. The lower faces can be directly obtained by the ReLU function. For the upper faces, we build a function and calculate the parameter beta to get the minimal beta and determine an upper face. Furthermore, we introduce 3 innovations to obtain efficient calculations. First, we calculate one dimension at a time and calculate the following functions step by step, because all upper faces have the following forms. Second, we exclude those vertices that cannot determine an upper face. We have proved only the vertices of the input polytope are necessary. Also, we filter vertices when calculating different constraints. Last, the third innovation, we calculate an approximation that has a stable number of constraints. The number of upper face constraints is the same as the constraints number of input polytopes. For the evaluation, we first compare our algorithm with other algorithms, including the exact ReLU hull method and approximate methods like SBLM plus PDDM. The triangle relaxation is the naive method, and it only considers the most simple constraints. From the results, we can find our method gets the best balance between precision and efficiency with fewer constraints. Furthermore, we have implemented our approach into the SODA framework Prima. Note that it groups neurons with a small size in a layer, and we use ReLU to approximate the ReLU hull of each small group. From the evaluation, our approach is beneficial to verify more samples with less runtime and fewer constraints. Also, our approach can resolve the higher dimensional cases, and the SODA approach doesn't support the higher dimensions. Lastly, about the future work, we claim that our approach can be generalized to other functions like max-pool, sigmoid, and tanh functions. For convex and piecewise linear functions, the approach is similar to the case of the Rilo function. For other general functions, we will use the piecewise linear lower and upper bound to approximate the convex score. That's all. Thank you for your attention.
Great. We have plenty of time for questions. If anyone's following along on the stream, by the way, and you want to ask a question on Discord, we can take your question as well. Does anyone have any questions in the room? Yes, please.
I was actually wondering, could you, and thank you for the talk, could you expand on how the value hole can be applied to verification? Because I guess that didn't come up in the talk.
Actually, first we will construct some linear constraints and we will get a linear programming problem and we verify the neural network by solving the linear programming problem.
Oh, I see. So, okay, thank you.
Any other questions in the room? While people think of a question, I have a question. So are there situations when your abstraction is exact? Have you thought about when you're exactly capturing the behavior of the neural network, or if there's any situations under which that might happen? That's kind of an interesting way of understanding kind of the limitations or places where this would perform particularly well.
Yes, sometimes it's exact, especially in this example. In this example, we consider the 3D dimensional space. There are 2 input variables and 1 output variable. In this case, our approach is exact. But because we determine an upper face by an edge and 1 vertex. So in high dimensional, there will be high dimensional edges and vertex. We omit this case. So in high dimensional cases, our approach is not exact.
Got it. Any other questions in the room? Yeah, we have a question back here.
Yes, in the last talk, we heard a little bit about complexity, and I was wondering if you could speak to that. You mentioned you find the combination of all of the vertices, and how well does this scale as you increase the number of vertices in the whole thing?
Well, yes. Okay. In the high dimensional cases, we will consider one, like in n-dimensional space, we will consider n-1 hyperplane and vertex. We will combine them. So actually, we use 1 vertex to determine a hyperplane, and then determine an upper face.
Thanks.
I have another question then for you. So are there plans to integrate, I see you have some code, and I would like to hear a little bit more about the code you have here. So do you plan to integrate this into some of the well-known deep learning frameworks so that it's easier to use your methods, or do you have intentions to do that, or anything like that that you can tell us about?
Yes, I think our work is just the beginning, and the Rilo function is a very significant function, so we resolve it first. And actually, we have some approaches for solving other functions in deep learning.
Right. So you're saying that there are other important functions we'll need to handle before maybe we should be putting it into larger frameworks, or is that what you're saying?
Oh, I'm not sure.
Oh, sorry. No, I don't want to put words into your mouth.
Okay.
No. I mean, I'm just asking. How easy would it be for me to use your tool today on my neural network that say only uses ReLU? Could I do that?
Yes. Okay. I think it's not very difficult to extend to other functions, because we will find, for example, for the sigmoid function, we will construct a ReLU function as the upper bound, and another ReLU function is reversed and as the lower bound, and we will approximate a convex hull of these two linear bound.
Right. So you can apply that to something that's not just ReLU.
Yes, it's not just ReLU.
Yep, that makes sense. Perfect. Yeah. Any other questions online or in the room? Questions? Sure, I have another one then. So, a big part of what makes deep learning scale very well in practice is the usage of heterogeneous hardware, right? Like we're running these things on GPUs in practice and things like this. I'm curious, is there an avenue potentially for your abstract domain to be run on a GPU, or are you already doing that? Because that seems like a very useful step in getting it to scale on kind of the practical problems that people use today.
Yes, that's a good question, and I think it's a future direction. But now we only used CPU to solve these problems, because calculating this convex hull is not convenient to calculate by GPU.
Got it. Can we get the next speaker to queue up? Very much. Do we have time for one more quick question if anyone has one in the room? Maybe I'll ask a follow-up then to that one. So, what do you think would be the first thing you would have to solve, the first difficult challenge in getting it to run on the GPU?
Oh, well, because calculating convex hull, there are some operations that it's not very easy to parallelize calculated.
Right. There will be some sequentialization in the optimization, perhaps, that would
Yes.
cause you issues. Got it. Perfect. Great. Let's thank our speaker one more time. All right, great. So next up we have Alex, who's going to be telling us about on learning polynomial recursive programs. Take it away, Alex.
Okay, hello everyone. This is a joint work with Vincent Cheval, Masashir Mohammadi, and James Worrell. And first I want to start by describing what I mean by learning. And the framework that I will be using is Dan Anglin's minimally adequate teacher. And what does this involve? So let's say that we have a program like the one you can see on the left, and we don't know the context. So imagine it's a black box, and I will call it an unknown target, which maps strings to rational numbers. And we would like to find out what is in the black box, and we have access to a teacher, which basically consists of two oracles. The first oracle is a membership query oracle, to which we can ask what's the value of a certain input W, And we have an equivalence oracle to which we pass a hypothesis, something which we think might be in the black box, and the teacher will tell us if they're equivalent, in which case we halt. Otherwise, the teacher will provide us with a counterexample, by which I mean just a word on which the hypothesis and the target function disagree. Next, I will talk about something which seems a bit unrelated at the moment. So I will talk about sequences, and yeah, I'll just give you two examples of probably very well-known sequences, the Fibonacci sequence and the number of involutions. And an involution is simply a self-inverse permutation. And the first thing to note is that the second sequence, the number of involutions, grows a lot faster than the first sequence. And this can be intuitively explained by looking at the recurrence relation they satisfy. So for the Fibonacci sequence, Fn is equal to the sum of the previous two terms, whereas for the number of involutions, it's In is equal to the previous term plus n minus 1 times In minus 2. So we have in red, we have a polynomial popping up, which might explain why the growth of the second one is larger. Now, if we do some basic algebra, we can express the general term of the Fibonacci sequence in the following shape. So we have a row vector times some matrix multiplication times a column vector, whereas for the involutions, I can do pretty much the same thing, but now instead of having a matrix which is constant, I have a matrix which changes one of the entries. So it goes 1 to 3 all the way up to n minus 1. I can view this as a matrix of polynomials in which I can just plug in numbers. So the first sequence belongs to the class of C-finite sequences, whereas the second one belongs to the class of D-finite. And why am I talking about sequences and recurrences? Well, because we can obviously write programs which compute the general term, but we can also come up with automata which solve this task. And yeah, let's look again at the program that I had in the beginning. So I can have it in this form. I can actually write down the function that it computes. So on an input string W over the 2-letter alphabet, it will output the length plus 1 factorial if the number of b's in the string is odd and 0 otherwise. Or I can use, I can reframe it as an automaton. So how would this look? This is the graphical representation, which is a bit inconvenient to work with if we want to analyze what it does. Or we can use like the more, well, algebraic representation. So a p-finite automaton is defined by three quantities. So the initial state, which is a row vector of constants, a transition matrix, a family of transition matrices, each corresponding to a letter. So for example, for the transition matrix of the letter A, I can have x times the identity, and this is a matrix of polynomials. And I have transition matrices for the other letters, and the final state vector, which is, again, a vector of polynomials. And how does the computation happen for this object? So basically, you take the initial state vector, you multiply it with the matrix corresponding to the first letter of the string, instantiated at 1, times the second matrix, instantiated at 2, times the third one, instantiated at 3, and you multiply by the final vector, instantiated at the next number, at 4 in this case, and if you do the computation in this case, it's exactly 24, which is what we would expect. So this type of automata generalized the finitely recursive sequences. If I were to have just constant entries in the matrices, then they would generalize the C recursive sequences like Fibonacci, and yeah, that also might explain the order of growth. Now I want to outline the main results of our work. So in the field of automata theory, like two important problems are the problem of equivalence, so deciding if two automata are computing the same function, and the exact learning problem in Anglin's framework. So I guess it's folklore the fact that for deterministic finite automata, the equivalence problem can be solved in polynomial time. Later in in 1987, Anglin showed that the exact learning framework can be solved in polynomial time. Then Zheng in 1992 showed that for Q-weighted automata, so when the entries of the transition matrices are just rational numbers, so not polynomials, the equivalence problem is in polynomial time. Then in 1995, Anglin et al. Showed that, well, there is one type of automata for which we cannot solve the equivalence problem, the learning problem in polynomial time, and that is for non-deterministic finite automata under some cryptographic assumption. Then in 1999, Beimel et al. Showed that for Q-weighted automata, the exact learning problem is in P. And a bit more recently, in 2022, Van Hert et al. Showed that for Z-weighted automata, so when the entries in the matrices are integers, the exact learning problem is decidable. And what do we do in our paper? So first of all, we introduced this new type of automata, for which we showed that both the equivalence and the exact learning problem can be done in polynomial time. And we also showed that for Z-weighted automata, the learning problem can be solved in polynomial time. I'll briefly outline the main ideas for each of these three results. So I'll start with the exact learning for Z-weighted automata. And the idea is to do a reduction from this problem to the problem of exact learning Q-weighted automata. And we still have access to these two oracles, the membership oracle and the equivalence oracle. And we use the algorithm for learning Q-weighted automata. If it tries to make a membership query, that is perfectly fine. It gives an input, and the oracle returns the integer output. However, the problem might occur when we're trying to access the equivalence oracle. And why is that? Because the equivalence oracle might complain about the fact that we are asking it if it's equivalent to something which is not a Z automata. So what do we do to fix this problem? We have a separate procedure which takes the hypothesis and decides if it can be represented as a Z-weighted automata. And in case it cannot, then, well, we have already found a counterexample which we can pass it back to the learning algorithm for Q-weighted automata. And if it is, then we pass this to the equivalence oracle. And it also does some sort of transformation. So it takes the hypothesis and makes it into the correct shape. And it can be seen as a constructive analog of Fatu's lemma, which basically says that if we have a sequence and the sequence has a recurrence with rational coefficients, but all the terms of the sequence are integers, then there is a recurrence just with integer coefficients. And then the equivalence oracle can either say, okay, yes, you found the target, in which case we halt, otherwise it returns a counterexample. Okay, so now going back to P finite automata. For the equivalence problem, we are looking at backward reachable vectors. So these are basically the vectors that can be reached by well, kind of ignoring the initial state. So to be a bit more specific, for the empty string epsilon, the backward reachable vector is just the final state. And if we would have something like AAB, the backward reachable vector for that would be the matrix corresponding to the first letter, but evaluated at x now, not at any number, times the matrix corresponding to the second letter, evaluated at x plus 1, times the one for the third letter, evaluated at x plus 2, times the final vector, evaluated at x plus 3. And when we put all these vectors together, so the backward reachable vector for each possible word, and we take their span, we get something which is called the backward space, and this is a very important object in the study of weighted automata. And yeah, the algorithm is basically a saturation algorithm. So what it does, it starts with the empty string, and it checks if the backward reachable vector for the empty string is in the span of everything that we have stored so far. For the empty string would be just the span of the empty set. Well, it's not. then it will add one letter. So is the backward reachable vector for A in the span of the backward reachable vector for the empty string? If it is, it goes to the next letter, which would be B. It does the same thing for B. And then it adds one more letter to the left of B, and we continue on this path because for the backward reachable vector for B, it was not in the span of the previous vectors. And this keeps going until we're basically saturating. And why does this work? So it's very similar in spirit to the algorithm proposed by Tseng. And in that work, they use the fact that, well, if you have a sequence of vector spaces that are subspaces of q to the power n, then it will not run forever. It will not increase forever, and it can increase at most n times. And we use a similar idea, but now because we're working with polynomials, we have to use modules rather than vector spaces. And now the question is, okay, if I have a strictly increasing sequence of modules, for how long does it run? And the answer is, well, not for too long. And for this, we had to develop a technical lemma, which I'm not expecting you to read, but it says that, yeah, well, it's going to be polynomial in the desired parameters. Okay, and the last thing is the exact learning for p-finite automata. And this is the big picture. I'm going to take each of these parts separately and explain what everything means. We start by constructing the hypothesis automata. And to do so, we are using a set of access words, which are columns, and a set of test words, which are rows in a table. And this table is reminiscent of the Hankel matrix. And for example, the value at the intersection of row A and column BB would be the value of the function evaluated at ABB, which we can access using membership queries. And yeah, after we have this table, we can do some polynomial interpolation in order to construct the hypothesis automata. We then pass it to the teacher. The teacher says if we have learned the correct automata or not. If we have, then we halt. Otherwise, we add a contra-example. We get a contra-example, and what do we do with it? Well, we basically check on which is the first prefix on which the automata is wrong. And let's say that in this case it's correct on BA but not on BAB. We add BAB as a row to the table. And why do we do so? Because intuitively the rows in this table are what help us differentiate between states. So this is, if you want to make a comparison with Anglin's algorithm, these are the test words, and the columns give you the states. Okay, and yeah, so we would like to loop back and construct the hypothesis automata, but the danger is that, well, we might loop forever. What I haven't told you so far is that this partial learner makes an assumption about how many states the target automata has. And, well, using that, we are able to compute timeout. And if the table becomes too large, so if the number of table exceeds some timeout, which depends on the number of states and the maximum degree of the polynomial in the target automata that were guessed, then it means that we have the wrong choice. And the big algorithm, the only extra thing that we need to do here is to search for the correct values of n and d. And once the correct values of n and d are found, then we can guarantee that the partial learner will eventually output the correct hypothesis. Okay, thank you very much. And if you have any questions, I would be more than happy to take them.
Great, we have time for questions. Any questions from the audience? Yes, we have a question.
Thank you for the talk. I was wondering if, for instance, someone wanted to apply this, if you can think about, for instance, the encyclopedia of integer sequences. You gave the example of the involution sequence. So maybe a somewhat unrealistic approach, unrealistic assumption of the model is that you can arbitrarily ask for a counterexample to your current model, but would it be practical to try and adapt this to, well, sequences that we can compute on the fly, but we can't really find an arbitrary counterexample? For instance, is there a bound on how many words you would have to check before you know whether your model is correct?
So let me make sure I understand your question. So you're basically asking me if if we know that the number of queries that we have to make is not too large.
Yes, essentially. Or for instance, you don't need an arbitrary one. You can view them in sequence, for instance.
So okay, in short, the answer is that, well, we can guarantee that the number of queries is polynomial. Everything runs in polynomial time. But what I mean by polynomial here, well, we do give some specific bounds in the paper. So that's one place where you can look exactly. But they are, yeah, it's basic. We're sometimes using arguments like, well, if you compose two polynomials, you get a polynomial. There are sources of improvements, and I think our intuition tells us that our bounds can be improved by a lot, but I guess that's like future work.
Thank you.
Any other questions? Yeah, we have a question back there.
Thank you for the nice talk. I'm curious if there's an extension to Englin's algorithm for alphabets, maybe infinite alphabets or symbolic.
No, so everything that we have here works only for finite alphabets, and the size of the alphabet actually appears in our bounds.
And what is the dependence on the size of the alphabet?
So I think it appears as, I don't know, the size alphabet raised to some power, which is a constant. So it's polynomial in the size of the alphabet. I'm not sure if it's not linear, but it's polynomial in the size of the alphabet.
Any other questions? I have a quick question. So in England's algorithm, a subroutine is this equivalence check where you give it a proposal candidate, say DFA, and it'll give you a counterexample or tell you that they're equivalent. So in this setting that you're in now, what happens with this equivalence? It seems like this becomes maybe harder. Is this kind of factored out in your algorithm, or
So
what happened there?
Basically, the reason why we started with the equivalence algorithm is because we want to make sure that the oracle that we assume we have access to can be run in polynomial time. And yeah, we have an algorithm which says, well, equivalence can be solved in polynomial time, so the oracle would basically
got it. So that's in there, and you've worked that out. Perfect. Yeah. I just missed that. Thank you. Any last minute questions? Oh. Well, I think with that, then we'll thank our speaker very much for the talk.
Thank you too.
There we go. All right. Great. So next up we have Noah, who's going to be telling us about programming by demonstration for long horizon robot tasks.
All right. Hi. Yeah. I'm Noah. So I'll be presenting, as was told, my paper titled Programming by Demonstration for Long Horizon Robot Tasks. The main contribution of this paper is a novel algorithm for synthesizing programmatic robotic policies from demonstrations. So you might be wondering, what are programmatic robot policies? Well, programmatic robot policies is essentially a program that's specifically designed to govern the behaviors of a robot. But why use programmatic policies rather than neural network policies, which have been responsible for much of the recent progress in robotics? Well, the answer is they don't generalize very well to different environments. they are difficult to interpret and verify, and they have a lot of data which is required to train. On the other hand, programmatic policies are generalizable to multiple environments, are interpretable and amenable to formal verification, and can be synthesized effectively from less data. And so now that I've motivated the utility of programs for robotic tasks, I'll discuss some of the properties that these programs must have. These programs must enable long horizon tasks, for example, household chores or restaurant work. Moreover, these tasks often have repetitive steps, which necessitates complex loop structures in the program. And additionally, these programs must enable decision making, which requires conditional blocks. Lastly, these programs must be able to execute in large environments with many object types, locations, properties, and relationships. And both of these factors end up yielding a very large program space. I'll now give a representative example program to demonstrate the complexities of programming with robot policies. Here's a program for a robot that must visit all of the rooms in a hotel and collect the dirty bed sheets. This requires going to each room, finding a laundry bin in the room and opening it, finding all of the bed sheets and beds in the room, then checking if any of these sheets are dirty and on the bed, and if they are, close the bin. Notice that this program has multiple nested loops, perception of appropriate objects, and conditional flow based on these perception results. And writing such a program requires expertise, resources, which makes it difficult for end users of a robot. This motivates the use of programming by demonstration, wherein programming by demonstration requires an end user to provide just a demonstration for the task at hand. This demonstration is then passed through a synthesizer, which generates the final program. And providing such a demonstration is much easier than writing a program for end users. I'll now explain how a demonstration for the program we saw earlier can be easily generated by such an end user. A demonstration consists of a sequence of actions over locations and object instances. Each demonstration takes place in a specific environment with specific locations and objects. For example, let's assume the hotel has 2 rooms, each with beds, sheets, and laundry bins. In this environment, the user provides a demonstration for the task at hand as follows. First, they go to the room and open the bin. Then they go to the first bed with the sheet and take the sheet and put it in the bin. Then they close the bin before going to the next room. Similarly, in the next room, they go to the bin and open it. They go to both beds and grab both of the sheets and put them in the bin and close it before leaving. So now with the utility of programming by demonstration motivated for robotic tasks, I will move on to explaining our approach. In this paper, we present a novel algorithm for programming by demonstration, specifically designed for such long horizon robot tasks, namely ProLex. Our approach in ProLex begins by generating a program sketches from the given demonstrations, using a novel reduction to learning regular expressions from positive strings. Next, we perform a top-down enumerative search over our DSL to generate a set of candidate programs. A major novelty of our algorithm is a refinement technique where a large language model is used to guide the process of partial program completion. Lastly, our pruning method uses a novel technique for abstracting partial programs into regular expressions, which is used to prune away unrealizable partial programs earlier in the search. I'll now break down the components of ProLex and start by discussing our sketch inference engine. We made the observation that this could be reduced to a problem of learning regular expressions from positive string samples. This learning problem is very well studied in the literature and has many off-the-shelf implementations. The steps of our inference are as follows. Given demonstrations, we abstract a sequence of actions into a specific string form. We then use an off-the-shelf regex learner to generate a regular expression that accepts these strings. And finally, we translate the learned regex into a program sketch. The first step of sketch inference is a demonstration abstraction, which simply replaces the object instances in the demonstration with more general object types. This is important for later stages of our synthesis, for recognizing repetitive patterns in the demonstration. After generating the abstract string, the next step in our sketch inference is to learn a regular expression that accepts the string. Such a regular expression essentially generalizes the abstract string into a structure that captures conditional and repetitive patterns in the demonstration. For example, when using an off-the-shelf learner, this is the expression that was learned from the given demonstration above. As you can see, the pattern in the demonstration is captured by the regex. In both rooms, a go-to is followed by a bin opening, which is also followed by a group of actions responsible for picking up and placing sheets. And lastly, the bin is closed before leaving the room. All of this is picked up in the regular expression that's learned. And now that we have a regular expression that generalizes the given demonstration, we can easily translate this into a program sketch. Specifically, all of the Kleene stars represent loops in the program, including the nested ones. And the conditional sub-expression, denoted by the question mark, represents a conditional block in the program sketch. These translation rules, when applied to this regex, produce the following sketch, with the nested loops from the Kleene stars and the condition. And now that we have a sketch, I will describe the next step in Prolex's algorithm, which is to find completions to these program sketches. As mentioned, our algorithm performs an enumerative search over a DSL. Completions for unknown holes in the sketch, performs an enumerative search over a DSL to find the completions in the sketch. However, as you would expect, naive enumeration becomes quickly intractable. To address this challenge, we come up with a novel idea to use a large language model to guide and prioritize our search for sketch completion. Specifically, we observe that large language models work well as common sense priors. In this work, all of the hole completions have real-world semantics, which can be reasoned about by large language models. I will now walk through an example and show how a large language model can be used to prioritize the search for sketch completions. Here is a partial version of the program we saw before. There are multiple holes in which our synthesizer must find appropriate completions for. Here's a list of the completions for the hole shown. As you can see, the correct object sheet is one of the candidate completions. However, there are many potential other completions that may appear in the list before, which the synthesizer must enumerate before checking sheet. Looking elsewhere in the program, though, we can see that this hole fill corresponds to an object which must be on top of a bed. With this knowledge, we can now reorder the list of candidate completions such that objects may be found on top of a bed will have higher priority. Similarly with the dirty predicate, we can again reorder the list and deprioritize other options which are less likely to be relevant in this context. This type of reasoning is well suited for large language models and allows our synthesizer to reorder completions for each hole and guide the search toward the target program more effectively. In summary, Prolex uses large language models as common sense priors over the real-world semantics, with the partial program as context to guide enumeration towards more likely partial programs based on the language model's score. However, even with the gains made by the large language model sketch refinement, many non-feasible partial programs must be elaborated. This motivates our pruning procedure. Our pruning strategy uses a form of abstract interpretation where, similar to the idea of treating demonstrations as strings and learning regular expressions that can be translated into program sketches, we also observe that we can over-approximate a partial program as a regular expression. The idea is to infer a regex such that if it does not accept the string representation of the demonstration, we can soundly prune away this partial program during our search for the target program. In our paper, we introduce a novel algorithm that, given a partial program, infers an over-approximating regular expression to be used in the pruning procedure. At a high level, we first use partial evaluation to generate a string of the known statements that will be produced by the execution of the partial program. This is to maximize the known information in the over-approximate regex. Then, to transform the remainder of the partial program, we must determine the potential number of loop iterations and the set of potential condition block evaluations. The idea is that the more partial programs, we can eliminate more partial programs, the more specific our over-approximate regex is. You can find the details of this algorithm in our paper, but I will walk through now an example showing how certain loops in the program can be over-approximated using knowledge from the demonstration environment. Here we are given a loop with a hole to be completed. We know from our DSL that this loop occurs over an object type, and based on the information in the environment, could be filled with 2 cups or 3 forks. We generate an over-approximate regex of this code fragment based on the set of potential loop iterations inferred from the environment. In this case, we have the disjunction of the loop repeated 2 or 3 times. This regex is much more informative than the loop that is repeated an unknown number of times, which leads to more pruned partial programs. Additionally, we prove in our work that the partial programs pruned by this methodology will not yield programs that are compatible with the target program, or with the demonstrations. Thus, our method will not miss compatible complete programs where they exist. I will end the talk today by going over some of the results from our evaluation. We evaluate on a benchmark of 40 tasks derived from a robotics benchmark named behavior. We evaluate on 3 varying environments, which are easy, medium, and hard, based on the size of the environment. The environments have over 1,000 object instances and 80 object types, which all of this leads to a potential program space of over 4 million complete programs per task. Prolix, with this in mind, was able to find a program consistent with the demonstration for 80% of these benchmark tasks, with a 2-minute timeout and 1 demonstration. Moreover, Prolix was able to find the ground truth program for 81% of these tasks. We also found that with more difficult environments, our solution was able to find more programs matching the ground truth program. This is because the more challenging environments allow us to prune more candidate partial programs. We also compared to the Cygus Solver CVC5 as a sketch completion engine. This was done by defining our DSL over using syntactic constraints and generating semantic constraints based off the initial and final world states generated by the demonstration. We found that CVC5 could not adequately find programs without first being given a sketch. And even with that, we found that on easy environments, CVC5 could only find consistent programs on 25% of tasks within the time limit. Lastly, we used GPT 3.5 as a baseline solution for this problem. We found that comparing GPT 3.5 by giving a specification of our DSL, the full environment, and the demonstration proved difficult, as when given only a fragment of the environment, GPT 3.5 was unable to solve any of the tasks. To reduce the amount of information given to GPT 3.5, we omitted the information about the environment and asked it to produce the final program. Here, it was only able to find consistent programs 45% of the time, and was only able to find a program matching the ground truth 25% of the time. To summarize, Prolix implements a regex-based sketch inference method using an off-the-shelf regex learner. Prolix utilizes large language models as a common sense prior to complete holes for the sketch. And Prolix provides a novel over-approximated regex pruning strategy and is more effective in realistic, long horizon tasks than baselines. Thank you.
Great, we have some time for questions. Any questions from the audience? In the back.
So these look like high-level plans for a robot rather than, movement or other things.
Yep.
How realistic are these programs in the sense that can you actually run a robot with just this amount of instruction?
Yes, that's a good question, actually. So some of what I'm working on right now is getting these programs to actually evaluate on real robots. So I'm co-advised with a roboticist professor as well. So right now, one of the difficulties we have is with actuation with arms. So picking things up is still a challenging task for robotics. So we're focusing on an information gathering task right now with similar programs where we would go around and collect information about environments. And so we're working on a method to do that. So it is pretty realistic.
And you could drop a sheet, and there can be humans in the room, and there can be so many things.
Humans in the room is fine. The actuation stuff is a bit difficult for picking things up. That's still a pretty open problem in robotics generally, but yeah.
Question here? Oh, and maybe the closer one. I don't know who was first. Maybe he was first, I think. So why don't we let him ask first? Yeah, sorry.
I was just wondering if type information could be used to, for instance, specifying that bins should only contain sheets.
Yeah,
so you get some. Yeah.
That is actually part of our solution. I didn't get into that too much, but we have a lightweight type system. So, for example, properties. If we're inferring, where is it? I don't have to show it, but in some cases, properties can be covered by a set of objects. so we know that certain properties don't have certain, or certain objects don't have certain properties, like they're not applicable. So that's also part of the way we refine it a little bit, but I was focusing more on the large language model guided refinement.
Now in the back there, yeah.
Thanks for the nice talk. So I have two questions. One is, do you care about the interpretability of the regex? You showed an example where you have source code and regex side by side. And I'm wondering if the regex corresponds to natural programs that a human would write. The second question is, if you have multiple holes, how do you prompt the LLM to synthesize? Do you search for the combination of all the things that would fit in all the holes, or thanks?
Okay, yeah. So I'll answer the second question first. You might have to repeat the first question. For the second question, we just do one hole at a time in program order. We experimented a little bit with doing a couple different orderings of holes, but we didn't really find much of a difference with that. So basically what we do is we give all the context up until the first program hole, and then ask it to solve or find a completion for that hole, and then move on in the partial program search, essentially. And if you could repeat the first question, sorry, I'm not sure I quite picked it up.
Just curious about the interpretability of the synthesized regular expressions.
Yeah, so I guess when I was talking earlier about interpretability, it was more so about the program itself that gets implemented. I think some of the regex we find aren't super interpretable at first glance, but going through the sketch translation rules we have, the programs that get generated are pretty interpretable, I would say. I don't know if that answers your question. Okay.
We have a question here.
So in your experiment, have you investigated out of distribution generalization? So demonstration is with respect to, say, length, 5 rooms. You want to apply, see whether the program you learned can be applied to a hotel with 100 rooms and so on, and see what happens.
Yeah, so the way we did our interpreted generalizability is once the program was generated, we did an eye test, manually inspected it and see if it matched the ground truth program that we were expecting. And then based on that, we know that whether or not it would generalize to more programs, because the ground truth programs will have loops over all of the rooms, for example. So in a hotel with 4 rooms or a hotel with 100 rooms, it would have the loop would repeat that many times based on that. So yeah, we didn't really experiment with it, but.
Thanks for the talk. I was wondering, it's a very naive question on my part, but I was wondering whether regular expressions were actually expressive enough to capture a lot of the programs you would want to have. For example, if you want to, for example, regular expressions can't do things like, having, checking if a string has the same number of A's and B's, for example. Then we can imagine a program for a robot whereby you would want to say pick up all the forks, no matter how many they are, and then put all those forks in a place, for example, and that would enable that would essentially be of a pattern of A to the n and B to the n for any n. And I was wondering whether you had whether this whether you had considered this and whether this is actually an expressive enough representation.
Yeah, so we found that the regex are expressive enough for our DSL, and then the way that we've implemented the sketch translation rules. So that example that you gave would end up referring to 2 sequential loops, essentially. So there would be a loop going through, we'll save 1 room for simplicity, but going through all the room, finding all of the forks and picking them up, and then a second loop of placing all of those forks in some specific location. So it would be able to pick that up from the demonstration. You would have a block of picking up, basically what the demonstration for that would look like would be a block of picking up all of the forks, and then a block of picking up all of the, or putting down all of the forks in some place. And then the regex you would get for that would be a cleany star over that first block, and then a cleany star over that second block. Does that answer your question?
All right, well, let's thank our speaker very much.
Okay, it's time to begin the last, possibly the best, session of POPL on gradual typing and verification. My name is Ron Garcia from University of British Columbia, but let me hand it off to Cesare Andrici, who will tell us about securing verified I/O programs against unverified code in F-star.
Thank you. Can you hear me? No? Oh, no. Okay. Hello, I'm Cesar Andrić, and today I'll present to you joint work with many great collaborators. In this paper, we devised a secure compilation framework that allows us to link verified code against unverified code securely. We do this for F-star, but the problem that we treat is much more general. It's a problem that exists in all proof-oriented languages. So in a proof-oriented language, we can write a program, write a specification, and then verify that the program satisfies the specification. For example, we can verify that the web server responds to every request. We can do that by taking the specification, annotating the code using refinement types, and annotating functions with pre- and post conditions, and then the language has a tool that will verify if the annotations are satisfied. And if the verification succeeds, then it gives us a strong guarantee that the program satisfies the specification. So we like these strong guarantees, and for these strong guarantees, proof-oriented languages were used to verify an increasing number of realistic applications. These are just a few of them that we can use today, and they actually are used, and some of them were integrated in tools like Firefox or Windows, and here I refer to the cryptographic primitives from Evercrypt or Everparse. And what can we learn from these projects is that most often the verified code is linked with unverified code. And still, with such a mix, with such a hybrid setting, we still want strong guarantees. But what happens in practice is that most often the specification of the unverified code is assumed. And this is bad because none of the proof-oriented languages offer any guarantees that these specifications are satisfied. So this can be easily unsound, and if the code is untrusted, it can be also insecure because the code can be buggy or malicious. So this is not what we want. And the alternative is to convert the assumptions into dynamic checks and to enforce the assumptions on the unverified code. And to get our strong guarantees, we want a solution that is verified. So in this paper, we look at this problem through the lenses of secure compilation. So our solution is called SCIO star. It's a verified secure compilation framework that dynamically converts, dynamically enforces the assumed specification. And it allows us to link verified code against unverified code securely, even if the code is adversarial. In this work, we assume that the two are in the same language, but one is annotated with pre- and post conditions and one is not. This is to make all assumptions explicit, but nevertheless, we have to enforce the assumptions. So our framework uses two methods, two techniques to enforce these assumptions. The first one is adding higher order contracts during compilation. So what happens during compilation is that the functions that interact with the unverified code are wrapped into new functions that have dynamic checks before and after each call. And these are great to enforce assumptions made about arguments or return values. For example, that the file descriptor passed as argument is open, or that a return string was read from a file. However, this technique is not enough. We need a second technique. And to give you an example of why, so this higher order contracts exist at the boundary between verified code and unverified code. So we add the, oh, okay. Okay. So imagine that the verified code calls into unverified code, and the unverified code has a missile. It can launch that missile, it gives us back control, and then we have to run a dynamic checks to do what? To find out that they launched a missile, it's too late, right? So what we do is we have a second technique we use a second technique that adds a reference monitor during linking. And this reference monitor enforces an access control policy on the unverified code to prevent any bad things from happening. And these two, so with these two techniques, our secure compilation framework gives us a resulting application that visually looks like this, where the verified code interacts with the unverified code through higher order contracts. And then there is the reference monitor. The reference monitor records everything that happens in both parts, but and in its internal state. And it uses that internal state to enforce the access control policy on the unverified code. Also, the higher order contracts also have access to this state to be able to enforce more explicit assumptions, but they cannot update the state of the monitor. All of this is mechanized in F star. So we were able to prove a soundness theorem that asserts that if we have a piece of code that is verified with respect to a global safety property, then using our compilation framework, we can link that securely against any unverified code. Right. So with this soundness theorem, and because everything is mechanized, we get our strong guarantees back, and this is great. So our high-level picture looks like this. SCIO star right now supports terminating higher-order I/O programs. By I/O programs, we mean programs that can open files, write to them, read from them, close them, open sockets, etc. And by higher order, we mean that the verified code and the unverified code communicate through a higher order interface, which means they can send callbacks to each other, and thanks to our framework, they can do this securely. Right. One more thing. In our framework, both the verified code can have initial control, and we also support the setting where the unverified code has initial control. We proved our secure compilation criteria in both cases. So to make this solution possible, we bring a few contributions. The first one is a new way to verify terminating I/O programs that benefits from SMT automation. The second is a compilation framework that converts systematically assumptions into dynamic checks. To our knowledge, our solution is the first to be verified. And also, we prove about our compilation framework a secure compilation criteria that is one of the strongest. It's even stronger than full abstraction. So let's start with the first. This is a toy example. If you want a better example, please look in the paper. We have a very nice case study of a web server. So how to verify an I/O program? Here we have verifprog. It's a function. It's a function that takes as argument another function called libparse. And the body of the function is only 3 lines. It opens data.csv. It takes the file descriptor. It passes this file descriptor to libparse, and then it closes the file descriptor. So to verify such a program in F star, we have to use monadic effects and use monadic effects to type this program. Here we use MIO, our own effect, and this allows us to write preconditions, here indicated by requires. It's a trivial precondition. And then we also write a postcondition indicated by ensures. And this postcondition states that if this program opens a file, then this file is data.csv. So basically, it allows this program to only open one file and to do the other operation. So this is just an example. And what MIO allows us to do is to write pre- and post-conditions over traces. What that means is that for each I operation, there is an event associated with it. For example, for open file, we have eOpenFile. For close, we have eClose. And we see that these events also have the arguments and the result values of the operations. And we have this whole for libparse. So here it becomes obvious that we have to make some assumptions about libparse to be able to verify the post condition against this local trace. So these events are put together into a local trace, and the post condition is verified against it. Also, I would like to mention that because this post condition is over traces, and you can see that it also characterizes the behavior of the program, but also of libparse. This is a global safety property for the entire thing. when the verifprog has initial control. And also, I would like to iterate why it's so important to enforce these assumptions. It's very easy to write an unverified libparse that just opens a password file and sends the data over sockets. So while we allow linking with such programs, we want to prevent the bad behavior of it. So the way we make assumptions about libparse is by typing libparse with a type that has pre and post conditions, and we call this a strong type. So we can give a precondition to libparse that, for example, the file descriptor given as argument is open, and we give it the post condition that the return value was read from the file descriptor. These two can be enforced using higher order contracts because they are about the argument and the return value. However, we need a second post condition that is about the behavioral libparse, and this post condition blocks libparse from opening any file. And this has to be enforced by the reference monitor, and actually this second post condition becomes our access control policy, denoted here by sigma. Now that we saw how we write our assumptions, let's see how we convert them into dynamic checks. So here is the same diagram again, but now with the example on each piece. So we have the verified program that expects a libparse that has a strong type, but we have a libparse that has a weak type that doesn't have a precondition or a postcondition. So our secure compilation framework bridges this gap using the two techniques, and there is this middle point we call an intermediate type. So the first thing that happens is that compilation takes the program and makes the program to expect a library with an intermediate type, and then the reference monitor, by enforcing an access control policy, actually gives a bit of specification to the library. So let's focus only on the types. So here is the same diagram simplified. We have the strong type that has refinements, pre and post conditions. What the higher order contracts do is that they will wrap this function into a new one and convert almost all the assumptions, all the specification into dynamic checks, except the post condition, except the part of the specification that's the access control policy, right? Because the higher contracts cannot enforce that. So so all the rest of the assumptions are enforced using higher order contracts. From a weak type to a intermediate type, I cannot show you exactly the structure of the weak type. I can just give you intuition here. It's a type that doesn't have any concrete specification, but the intuition is very simple. If we have a function of this type and we have a reference monitor that enforces an access control policy on it, then we can give this access, we can write as a post condition that this program satisfies the access control policy, right? If we have a program, we enforce the access control policy, then we can state that the program satisfies the access control policy. Right, so these are the simplest. These are the way we translate between types. And now I would like to talk about our secure criteria. So we prove about our compilation framework, one of the strongest secure compilation criterion. It is called robust relation hyperproperty preservation. It is shown to be stronger than full abstraction. So here, prog is our verified program, and context is the unverified code. With red is in the target, with blue is in the source. So what it says is that for any piece of unverified code that exists, let me read it again. For any unverified context, there exists a verified context, such that for all verified programs, if we check the behavior of the compiled program linked with the unverified code equals the behavior in the source of the verified program linked with verified code. And this criterion is usually very hard to prove in the literature. But our proof is by construction. And this is because we put a lot of effort into having two shallow embeddings that help with our proof, and also because we specialize the design of our higher order contracts to help with the proof to make it by construction. The proof and other definitions are in the paper. And I would like to reiterate that there is a very nice case study of a simple web server that was written and verified in F***, and also compiled and secured with SCI F***, our framework. Thank you.
Okay, questions?
Hi, nice work. So, do you support mutually distrusting programs?
What do you mean by mutually distrusting?
So suppose libparse also tries to protect itself from its.
No, I mean we are only interested in protecting from unverified code. We don't really do it the other way. We don't do it the other way.
Okay.
Can you go back to the last slide? When you indicate this is proved by construction, do you mean for every unverified context, you can actually generate as an algorithm to generate the verified context?
Yes, we defined a back translation function from an unverified context to a verified context.
Okay, yeah, thank you.
So I had a similar question here. It's about the back translation. Do you prove that that blue context that exists is somehow equivalent to the red one? Because otherwise I'm worried that if you do something funky, I mean, I know you're doing a back translation, so you have a way of generating this, but if I just look at the theorem statement, it seems to say that you could get crafty and come up with some sort of blue context that somehow compensates for certain behavior, like if it knows weird things about the compiler or about the monitors. Technically speaking, that theorem had stated, if it doesn't say that the red CTX and the blue CTX are equivalent, it feels like there's some danger that's possible. Based on only the theorem statement, though I understand that your proof is by construction, therefore if I go look at the way the proof is done, it probably, that worry goes away. What would you say to that?
I mean, what I can say is that it's proven that this criterion is stronger than full abstraction. Now, you say that it needs some kind of other condition to relate the context in the target with the context in the source.
I see. So you have a theorem that says that this implies full abstraction.
Yeah. So this is proved in Abbat et al. In CSF 2019.
Okay. Maybe we can talk about it offline, because I'm wondering how that proof goes.
Okay.
Hello. Have you measured the overhead of the adding these verification and annotations?
No.
Like the runtime overhead, I mean.
No, we do not deploy all the solutions that exist in literature. For example, soft contract verification that will eliminate some of the contracts. But we put a lot of effort into ensuring that we enforce only the required dynamic checks. And also our framework is parameterized by the monitor state. So when one does the compilation, can choose the state of the monitor so that it is as small as necessary, as minimal as necessary. So we did some effort into making things better, but we did not run any benchmarks.
Thank you.
One more question. Who writes these monitors, and what language can that person use?
So it has to use F star, and the person that does the compilation has to.
So that person could actually inject effects into the monitor, like open the file itself.
So
is
if
there
it's
protection against effects in the in the contract?
Yes. Yeah. So the contracts are
not the not the higher order contract, the monitor. Are there can the monitor have effects, or do you have contracts on the monitor that can have eliminate these effects? Because if you use full F star, that can happen.
So in F star supports effects, right, and it will check what effects a function has. So for the contracts, it's they cannot produce effects except some minimal related to the monitor itself. And for the monitor, one can only choose the state of the monitor, not the way the state is updated or accessed.
Let's thank our speaker.
Quick note for those who sit by the aisles, especially if you sit near the door, it would be amazing if you could just move inside a bit because people are switching between sessions and then they can come in and sit down without disturbing anyone. Thank you so much.
Okay, for our next talk, Konrad Zimmermann will be telling us about sound gradual verification with symbolic execution.
Oh, get my slides up here. All right, hello, I'm Konrad Zimmermann. And today I'll be talking about sound gradual verification with symbolic execution. This is some work that I did in collaboration with Gianna DiVincenzo and Jonathan Aldrich. But first, let's talk about Wile E. Coyote. As you might know, Wile E. Coyote spends a lot of time thinking about Roadrunner, specifically how we can catch Roadrunner. But all of his plans end very badly for him and not for Roadrunner. So one day, Wile E. gets an idea. He should use verification. That way his plan can't fail. But Wile E., he doesn't know separation logic or abstract predicates very well. So he can't figure out how to use static verification. But Wile E. finds the perfect solution, gradual verification. Gradual verification allows Wile E. to incrementally build specifications and get feedback on their behavior, learning new specification constructs as necessary. So this time he wants to trap Roadrunner by blowing up a bridge just as Roadrunner is about to cross. So he writes the software for the detonator and verifies it using gradual C0, the first and so far only gradual verifier. Verification passes, so now he just sits by and waits for Roadrunner. Roadrunner approaches and runs by without triggering any detonation. So now Wile E. wonders, how did Roadrunner get away this time? This story, it actually could have happened if Wile E. used a previous version of the gradual C0 verifier. Now, you've probably recognized by now that this is a pretty classic soundness problem. But how do we ensure soundness? To complicate things further, our verifier gradual C0 is based on the Viper verifier, and specifically its symbolic execution engine. Other verifiers, such as Proustian and Vercors, are also based on Viper. But up to this point, at least to my knowledge, we did not have any formal soundness result or even statement for any of these tools. So I'll go over several problems that need addressed in order to formally state and prove soundness of our gradual verifier, including the formalization of symbolic execution, static verification, and dynamic verification. As I described, there previously was an unsoundness issue in gradual C0 that we discovered through this work, which obviously needs addressed in order to ensure soundness. So for each of these areas, I'll talk about how we address the problem in question. And we'll start with symbolic execution. So as you might know, symbolic execution simulates dynamic execution and forms the basis for our static verifier, as I said. But dynamic execution often branches. So in order to prove soundness, we must prove that the verifier explores every state, and furthermore, that all of the states that it does explore are sound. We've used what we call non-deterministic rules to give an operational semantics for symbolic execution. Here we're using the word non-deterministic in the sense of like a non-deterministic automaton or Turing machine. So for example, to execute an if statement, we can evaluate this conditional expression to some symbolic value t. And then using a state where T holds, in other words, where the conditional is true, execution of the if statement transitions to the then clause. But that only covers one possible branch, so we have another rule, where we evaluate this conditional as before, and using another state where not T holds, in other words, where the conditional is false, execution transitions to the else clause. So in this way, we've specified two ways to symbolically execute the same if statement, which corresponds to the two possible dynamic execution paths. This is similar to an existing formalization of a symbolic type checker, actually, by Ku et al., but we extend it to include execution of loops and other constructs. So now let's move on to static verification. As I've mentioned previously, our gradual verifier is based on Viper. And so we've formalized the core subset of the symbolic execution backend for Viper that's used by our gradual verifier. I won't discuss the exact formalization, go see our paper for that, but I'll show how we statically verify Wiley's code. So we'll start with his catch roadrunner method that he wrote, which takes a world parameter. So we add this to our verifier state, but now we don't know at verification time what value this will be. So we represent this value with an abstract symbolic value, which we name 1 here, in brackets to distinguish it from the natural numbers. But we have a precondition, specifically a predicate instance, representing the well-formedness of this world. So we can also just add this to our verifier state, and now we're ready to symbolically execute the body of the method. First, we allocate a detonator instance, which we add to the symbolic state, and we represent its value with a new symbolic value, which we call 2. But this instance also contains 2 fields, armed and detonated, which are initialized to their default values of false. But then we set armed to true, and we update our verifier state. Now we call install detonator. If we look at its signature, we see that it requires this instance of the well-formed world predicate. But we have this in our verifier state. So we can consume this predicate from the state. But now the post condition gives us this exact predicate back, or an equivalent one back, and we add this to our verifier state. Since after the method returns, we know we will have this predicate again. So next, Wiley wants to trigger detonation by calling the detonate method. But its precondition requires access to the detonated field. This specification here is an accessibility predicate, and this specifies that the detonated field is contained in the method's frame. In other words, in the set of heap locations that it's allowed to modify. So in other words, this field might be modified during execution of this method. So we must remove it from the verifier state. But now the post condition ensures that access is returned, so we add this back to our verifier state. But now we don't know what its value will be when it returns, and so we represent its value with a new symbolic value, which we call 3. But the post condition consists of 2 parts, joined by this separating conjunction. And the separating conjunction, as we use it here, is part of the logic of implicit dynamic frames. But if you don't know anything about that, just treat this as an and you'll be fine for this talk. The second part specifies that if armed is true, then the detonated field will be true. So whenever we evaluate this armed value against our verifier state, we can trace this back and see that it must be true. Therefore, the then clause holds. So if we look at that, this states that the detonated field will be true. So we can evaluate this against our verifier state, and this shows us that this symbolic value 3 must be true. So we can just add this to our state. Now we're done with the detonate method call, but we have more to do. Wiley wants to verify that the detonator actually went off. So he adds an assertion, which is statically verified that the detonator was indeed triggered, and always will be for any run of this program. So we evaluate this expression against our verifier state, and we find that it's true. So the assertion is going to hold. Finally, we conclude verification by verifying the post condition, which involves consuming the well-formed world predicate instance. So now we've successfully verified this method. But now, if we spent all this time verifying Wiley's code, why did Roadrunner get away? Is it because Bugs Bunny is in his computer? Well, there's at least one other explanation, and that has to do with a combination of several things underpinning gradual verification. So gradual verification, in a very short nutshell, allows incremental development of specifications by allowing explicitly partial specifications. Now, that's a lot of words, so what does it look like? Well, we'll get into that, but partial specifications signal to the verifier to make assumptions where necessary to complete the proof. However, these assumptions are then checked at runtime. So we have to formalize this interaction, and to formalize the interaction between the static side and the dynamic side, we define what we call runtime checks and valuations. So one of these partial specifications is here in the header file that Wiley received from Acme with his detonator kit. So the body of this well-formed world predicate is just question mark and true. In gradual verification, question mark can represent any formula that is consistent with the rest of the formula. For example, maybe this question mark represents an assumption that Roadrunner is always going to be in New Mexico. But it could represent any possible satisfiable formula. This alone, though, should not allow unsoundness, because we should catch those errors whenever we actually run the program. And hopefully Wiley tested it maybe a little bit at least. So what happened here? So if we go further, let's just look at this method, install detonator, that Wiley's code called. And you might first notice the fold and unfold statements. These provide information to the static verifier, but they're ignored at runtime. But there is a problem here. This method unarms the detonator, which definitely did not turn up in our verification before. So how did this pass verification? Well, let's look at verification. First, we begin with a well-formed world predicate instance. We include this in our verifier state. Unfolding this predicate exchanges a predicate instance for the body, which simply adds question mark to the verifier state. This indicates that there's a partial specification in the context, and therefore the verifier can assume things and then check those at runtime. So now when assigning to the armed field, even though we don't necessarily statically know that we have access to it, we can optimistically assume that we can access it, and we add this to our verifier state. But now in order to ensure soundness, we need to add a runtime check that validates our assumption that we made. But you might notice here, there's a symbolic value in the runtime check. What does that mean at runtime? How do we even check that at runtime? Well, in our formalism, we relate a verifier state with a runtime state with a valuation function, which is a partial function that maps symbolic values to the values at runtime. And using evaluation, the models relation indicates that the corresponding runtime values exist and satisfy invariants such as separation. So now we can formally define semantics for runtime checks and actually assert them against our runtime state. So this allows us to precisely specify semantics for runtime checks without actually worrying about the complex source code transformations necessary to actually rewrite the program to do the checking. So in our example, the runtime check shown here is actually equivalent to the assertion that we can access and modify the armed field as we might expect. And the rest of the verification is unimportant, but it does succeed. So in conclusion, this method will succeed as long as it's given access at runtime to the armed field. And note that this actually requires a gradually verified program to keep track of the accessible heap locations at runtime and pass this set of heap locations in a callees frame when you call a method, at least wherever runtime checks are possible. There's some optimizations that you can do to get around this. But now we've verified two methods, and we still haven't seen where unsoundness can arise. But instead, the interaction between these two methods actually creates this unsoundness. So returning to Wiley's code, during verification, you might remember we assumed that the install detonator, in fact, it was specified that it only consumed the well-formed world predicate. But remember, the predicate body includes question mark, and this could represent any formula or any permission. Therefore, a naive gradual verifier would optimistically pass all the permissions that it has at runtime, because we don't know what permissions this method is going to need. So it would pass all the permissions that the caller catch Roadrunner has whenever calling this method. But if we look at this, if this question mark is allowed to represent access to the armed field, this is actually inconsistent, since we would have two separate instances of ownership of this armed field, one in the predicate body and one in the verifier state. This violates the normal separation invariant that we assume during verification. We have to preserve separation between these things. And so to fix this, one possible fix is by making static verification more conservative, somehow removing one of these overlapping permissions. But since the case I've described only arises with inconsistent assumptions, we instead change the dynamic semantics by defining what we call an exclusion frame. Since only the well-formed world predicate is consumed during the call, and the verifier state retains ownership of these armed and detonated fields, these fields are included in the exclusion frame, and therefore not passed to the install detonator method. So now whenever we execute it, it won't be able to assert this runtime check, and it will show an error. And this reflects the fact that this predicate is at a point before the detonator is allocated, and therefore, if we have that assumption, the specifications and assumptions are somehow inconsistent. So in conclusion, our paper proves the soundness of gradual C0 with these modifications. Basically, symbolic execution, gradual verification, and runtime checks all imply both safe execution and that all your specifications are satisfied. Yeah, I'll just flip through that for sake of time. So we've done all this, and we have a few more things, including verifying while loops, other approaches to fixing this unsoundness. We define dynamic semantics for our language, and we finally give a proof of soundness with respect to those semantics, and we discuss future applications of this. So one final note, I'm applying to PhD programs. I might have even applied to your institution, so happy to talk more about that offline. Thank you.
Questions from the audience? So I have a question while the audience thinks. How significant is the performance difference between using the symbolic execution and not? Do you know?
Well, okay, so a few things to that. One is that we only have implemented a gradual verification using symbolic execution. We think it makes it more predictable to use symbolic execution. We don't have any other implementation to evaluate it against, so I guess that is sort of up in the air.
Or do you maybe have a sense of how many checks are removed? Like, is it?
So that is that's done in another paper, which you can find a preprint of. Jenna is a primary author of that paper.
Okay.
But yeah, so we do a full evaluation there.
Okay,
yeah.
Great, thank you.
Thank you for a very nice presentation. Just to be sure I understand, using this technique with the gradual thing where it fails, it tries to access the armed variable, what means in practice is that when the Roadrunner runs it, he'll just get this error and still the Roadrunner will escape. So that other invariant is preserved.
Yes, right. Yeah, so under these circumstances, Wiley would not know it until he actually runs the program. And then Roadrunner would, yes, if this was the first time that he's testing it, Roadrunner gets away. Sad, but at least Wiley knows.
But it will tell him that the Roadrunner got away.
Yes.
Hey, nice talk. Don't mean anything bad by this, but was the previous version of also proved sound?
No. So like I said before, the tools that we ended up formalizing, or at least parts of them, those did not have any formal statement of soundness. So gradual C0 is the first implementation. There was previously a theory of gradual verification that was developed with abstract predicates, and proven sound, but that used a completely different reasoning strategy, and also the proof of soundness is somewhat less substantial because it actually checks everything at runtime. It didn't have this separation of the calculated runtime checks versus all the other checks that are implied.
Okay, and our last question.
In verification of concurrent programs, you want to prove some property about, some properties about like eliminating data races and stuff. And any property that you can verify or prove statically in our system, you want to be able to prove dynamically. And so it ends up with this question of, do you want to have some dynamic way of catching any possible data race, or how do you handle that dynamically, I think is the biggest question. Yeah.
Okay, let's thank our speaker again. Okay, and now Peter Campora is going to be talking to us about type-based gradual typing performance optimization.
Hey, so talking about optimizing gradually typed programs. First note, just speed matters, both developer speed. People want to go fast. They want to develop their applications as quickly as possible. They don't want to be slowed down unnecessarily. And secondly, they also want fast programs. Nobody wants a slow program for anything unless you're doing something kind of obscure. Ideally, the faster the better, as long as it's easy to develop. So I'll get to why this is kind of, I think, a blocker for certain things. But yeah, gradual typing, unfortunately, can have some performance issues. First, a little bit about it. So there's this kind of notion of like a couple of things that I think are really critical to gradual typing. One's the obvious thing, which is that you can mix static and dynamic typing within a single application. And secondly, that you can gradually actually start changing and adding types. So in this example here, there's micro-level gradual typing where we had this kind of simple successor function, and we annotated it to say that it takes in integers and returns an integer. And that's the only type annotation someone may want to add, to start with, and just check that they're doing the right thing. In other languages, they do it more at the module level. But either way, you gradually either add types to modules, or you gradually add types to functions within a module. The other thing about gradual typing versus optional typing is soundness. So you don't want to have annotations be completely erased and then have your type annotations not be kind of honored at runtime when dynamic values sneak into your kind of statically typed regions from your annotations. One thing related to performance, though, is that if you have kind of completely statically typed regions, there shouldn't be any runtime type checks on your values. So for this successor function, it was completely statically typed. You shouldn't have any unnecessary casts that are going on. However, when you're in your F1 function over here and you're kind of passing a dynamically typed value into the statically typed context, you have these casts that are inserted, which are just runtime type checks generally. And they usually have an associated blame label to kind of say where the problem is going on. You could think of that as like source location information or something else about your program. And so in this context, if something goes wrong, then you want to blame the kind of correct location and kind of say where your dynamic code caused issues when interacting with your static code. These runtime type checks don't come for free, and so you could get performance penalties, which I'll get into. First, I want to talk about a little bit of a case study that I personally experienced recently. So I transitioned into working on quantum compilers and inherited this quantum compilation code base that was completely written in untyped Python. And I was like, hey, it'd be cool if I could add some annotations. There's these different modules. That was a parser, kind of gate rebaser, ion transport, optimization routines, and code generation. And a test suite, and this is what I wanted to kind of really get to, that takes hours to finish, that's verifying certain things about transporting different amounts of ions around. We eventually were like, well, it would be nice if our builds and our continuous integration had more static type checking, so why not gradually migrate with MyPy? So this is an optional type system. It doesn't have soundness, but you still wanted some of that kind of static routines. And so, I could have thought about going and kind of typing a module at a time, either typing my parser and leaving my code gen and other things untyped, or typing the code gen and leaving other modules untyped until I kind of get to this top region where I've added types to everything. However, what could have ended up happening if we were dealing with soundness is that certain modules could have added, when you added those types, could have incurred a lot of runtime type checks that really slowed down your program in certain regions, and they might have had okay performance in other regions. And then finally, this would be hard to do all at once, once it was completely statically typed, if we were using soundness, you would have a fast program. And this would be a real problem to get into these roadblocks because, like I said, our test suite is taking hours to complete. If all of a sudden we're getting, 3 times more kind of slowdown, we're looking at half a day. If I get 10 times or more slowdown, I'm looking at an entire day, and that's really going to slow down developer progress, and it would just personally be really annoying for us to actually get kind of code developed and integrated while doing this. So yeah, soundness is great. However, slowdowns for certain things could be kind of intolerable, even at just a few kind of multiplication factors. So yeah, I want to avoid casts as much as possible, right? So it's nice if you can still gradually annotate things and mix static and dynamic, but not have unnecessary casts kind of incurred in the execution of your program. One way that you could think about doing this, and a few approaches have thought about previously, is to infer types. The way that this one kind of varies our approach is that we're going to infer types for functions, and then we're going to do type specialization based on that, and basically duplicate your functions and kind of use these fast versions internally when you have statically typed arguments, and otherwise, use your dynamically typed version. And this can be combined with other approaches to optimizations, like using a JIT, which will do that kind of on the fly. Based on dynamic information. And it can also be kind of used with approaches that look at your cast inserted program and also try to do analysis to take away casts. So it's orthogonal to a lot of different optimization approaches you could think about. And one thing we really wanted was that optimized programs still need to blame the same. So you don't want a freaking semantics changing thing for your program, right? You want the same value if it evaluates, and you don't want it to all of a sudden blame something else just because some optimization, started adding type information somewhere. And so we can do this while still using these fast versions of this program. So this program on the left, there's this kind of bottom call to F2 that fails. Let's see if I can highlight that. Over here, because it's passing an integer into this function, and then it eventually gets dynamically checked against Boolean, so that should fail and it should blame. Why? So when you're optimizing, you still want the same behavior. So when we're using these fast kind of inferred functions in the code generation and switching calls to them under the hood, we'll see that you're eliminating some casts that were here on the left by calling these fast versions. However, the same cast is still appearing right here. And so you'll eventually kind of step and execute until you blame that ly cast. And I guess most of the time you may not care that you get to your failure condition that much faster, but it is really important for your programs that succeed, and I don't think there's anything wrong with getting to your errors faster. It improves development speed. So yeah, the way that we're going to do this kind of hinges on subtyping to kind of keep things safe, which I'll get into later. But basically, we use subtyping judgments, which can't fail if you're casting from a subtype to a supertype. So yeah, the approach that we use is called discriminative typing. It uses my previous work that I kind of worked on with Sheng on migrational typing. So that's this kind of type inference approach to look at this kind of space of possible typings. The second thing we do is pick a maximally typed migration for each function and use those to kind of generate your specialized kind of fast versions. And then finally, we use a cast insertion procedure that uses subtyping judgments for safety. There's the subtyping constraint solving. So the first part of this is typing this region. So it may be the case that you've already partially migrated your program. So you're starting over here in this blue region. And then you're going to basically want to get to, the more static regions so that you're having static code interacting and not doing runtime type checks. Unfortunately, because you're dealing with a gradually typed language, there's usually either some dynamic features of that language that cause trouble or just inherently, like, you can do things that may make it very difficult to kind of infer static types for everything. So you could get to the situation where you have more than one possible set of maximal kind of migrations of types. We don't have any particular one to kind of say, which is the favorite, but we just kind of pick one and use those. So to kind of illustrate a little bit of this dynamic idiom stuff causing trouble, here we have a program that has a parameter that's obviously an int or a string, and another one that's a suffix that's kind of always a string. So it's perfectly fine to kind of type suffix with string, but trying to say int or string is just an int or just a string causes trouble. So you need some calculus with some kind of union type or something else. But if it doesn't have that, then you kind of have to leave it dynamic. So we're not going to consider union types. So in this case, the only things that you can do to enter string are leave it dynamic and then kind of try to maximally migrate towards your suffix parameter having type string. So this is the best kind of case that you can have. You can't fully infer types for this. Again, you need union types or something else. So we can consider all of these different typings at once with this technique called variational typing. It uses these variational types, which are kind of an interesting combination of like product type, and sometimes it acts like a union. It's a little interesting, but one of the things to note is that we have unique names for these types. So there's this choice name A that's going to be uniquely associated with this enter string parameter. And then there's going to be choice name B that's kind of uniquely associated with a suffix. And then we're going to have these additional things to kind of talk about the typing of this program. So the green tops represent this program will have a type checking success. The red bottom represents that it will have a type checking failure. And basically we can see that you can do whatever you want to suffix, but enter string has to be left with the dynamic type. If you try and move it to using type int or something like that, according to this over here, then you're going to get a null typed program. So it's not a valid migration. So we use that to kind of infer this like spectrum of different possible typings for your program. Then we go and we're just going to kind of arbitrarily, start picking migrations for all of these different functions. So what really kind of drives the meat of this is this variational cast insertion procedure, where you basically kind of get your type, your original type that somebody provided over here in a choice, and then you get this fast version type that we could find from that previous migration process. And then at different function application areas, you kind of say, hey, what choices do I have for the function that's currently being called? If the fast version, if all of its arguments are subtypes, then we're safe to go ahead and use the fast version, and otherwise we'll use the slow version. So there's a lot more going on with some subtleties in here, but that's the heart of it, is the use of subtyping, kind of constraint solving for this variational cast insertion process to make sure that we're only calling these specialized functions with arguments that won't cause blame errors. That will be new. And then we kind of evaluated this on reticulated Python and a bit on Grift. And we found that for guarded reticulated Python, we got speed up on most programs. And these are looking at basically, for certain programs, the entire kind of lattice configuration space of different typings. They're all relatively simple programs, but some of them have too large of a space to completely sample, so we would just randomly pick different typings. And then, yeah, we found most programs got some amount of speed up, with some getting really noticeable speed ups. We did get slowdowns, unfortunately, on certain programs, which, you know, is not great. However, you know, it's not too bad given that it's a small number of configurations that are hitting this. So to conclude, this discriminative typing could speed up many programs. The program semantics don't change, so it always blames the same. It always returns the same value, either tagged or kind of untagged. You only have an O of n increase in program size. I think it's a relatively simple combination of inference, specialization, and gradual subtyping use and kind of some constraint solving procedures. However, there are some threats, I think, to its use in generality. It works best in kind of simple functional languages with more rigid structure, and most gradually typed languages in practice are not that. And yeah, so extending the inference would be difficult. And then finally, there are pathological examples that can cause exponential blowups in compile time. However, in practice, at worst, I think we saw more like an order of magnitude slower, and usually just a couple 2 to 5 times slower for compilation time. But yeah, that's it. Thanks.
Hey, questions?
Yes, I saw you had this inference that you tried to take the few types that were added and sort of added them to more places. And at the same time, it seemed that you described the dynamic typing thing as you had a process of trying to add more and more as a human, which means it would be very nice if you got feedback about exactly which were those places where it inferred things. Does the system give any help with that?
No, this is under the hood. So it's some previous work that suggested migrations that would improve performance. So those were more clear about how your program was changing. This was intended to be, you know, a semantics preserving optimization under the hood. But yeah, it doesn't actually say anything about how the migration changed things.
I have 2 questions. One is a simple one. If you duplicate a lot of functions, we noticed back at the right already that you get register pressure. Did you experience anything like this?
That could explain some of the slowdowns as well. I think most of them were related to, there were certain cases where higher order casts would create proxies, and that would slow things down, even though it was like simple checks. But no, I didn't actually get down to that level of evaluating register pressure.
So the second question is more interesting in the sense, in particular, Python's type system is very impoverished.
Yeah.
Xena, for example, try to add union types. When you have union types, you experience what we experienced in type bracket, that surface programmers use union types to make very, very precise types, the maximal types, right? And then we have benchmarks where the performance just goes way down. So I don't think you can, we have to take your results with a grain of salt in the spirit of when you add real interesting types, like TypeScript level types to reticulate it, it won't work. That's my guess. I mean, it's not a question, it's more a statement, but you can please react.
I was going to say, I would agree with that. So we kept to a core small calculus just to evaluate whether this had any merit. But yeah, I think once you get to, set theoretic types or more complicated things, like if you're trying to do like partial object inference, yeah, you're going to create proxies that are going to create a lot of slowdown. So it's tough. I will say, though, there are certain things that you can do. I have this bonus slide. So if you have a program where you're like doing something like using plus in Python, which again is heavily overloaded to work with different things, you could still do an unsound kind of inference of integer types and use that as your specialization. And if you have a hot loop, you can still call that version and avoid like a more generic object cast that's like looking for underscore add. And then still use the slow dynamic version, like if you use plus to concatenate two strings or to work with different objects. But yeah, I think the more and more you push things, you could probably run into complicated proxies that are inferred and wouldn't help. So yeah.
Okay, let's thank our speaker. And now to take us home, Eric is going to talk to us about total type error localization and recovery with holes.
Yep, thanks. Everyone hear me? Good. Yeah, thanks for the introduction. So I'm Eric, an undergraduate at the University of Michigan. This is work in collaboration with folks there at the Future Programming Lab. Thanks for bearing with me on this last talk of the day. Though maybe it's on a sleepy Friday afternoon like this that we're in need of a reality check. And the reality is that most of the code we type is ill-typed. In fact, most of the time we're still writing out the thing, so it's probably very ill-typed indeed. Or think about that time you spent, you changed some important function definition or type definition and had to spend the next several hours or even days fixing the rest of your code. So in fact, these ill-typed states can persist for a surprisingly long time. And for these reasons, we hope, or rather expect, our editor services and tooling to be able to cope with our ill-typed code. In particular, it means we expect them to, first of all, localize type errors, or tell us what and where they are in our code. And also, even in the face of them, sort of recover optimistically, continue doing whatever it's doing and find potential other errors, ideally with minimal loss in service. Code completion, for example, shouldn't suddenly be unavailable because I have a type error somewhere. And so naturally, this problem has garnered plenty of practical interest. And we can see that production tooling supports some level of localization and recovery capability. Let's look, for example, at this program that has f that takes a Boolean, x determined by a conditional, and then f applied to x. We can immediately see that the branches of the conditional are mismatched with respect to typing. So there should be some sort of error diagnostic. And in fact, if we threw this at the OCaml compiler, it would say, yes, there is, and it's on false, having sort of assumed the first branch to be correct. And so OCaml C will stop here, but the OCaml language server, which probably most people use in editors nowadays, will go on to say that there's actually another error on the usage of x, because it's determined x already to be an int, but f takes a Boolean. OK, this is all well and good, but what about Haskell? Perhaps someone unexpectedly localizes the error to 5, saying it's not an instance of num bool. This is presumably has something to do with how type inference works for the num type class. Rust is a little different in that it prioritizes the first branch like OCaml, but also suggests that perhaps 5 is to blame in all of this. And then Hazel, the programming environment that our group is developing, is yet different, assigning the error to the entire conditional. And the cursor inspector down here tells us that the branches have inconsistent types. So obviously, all these languages have very different type systems, but from this sort of informal exercise, we can see that practical systems do support type error localization and recovery to some extent. But localization decisions can vary a lot, and often tools are trying to guess about user intention. Then to recover, they have to somehow operate with incomplete knowledge of the types at play. And together, this means that upstream localization decisions can greatly influence downstream ones, perhaps somewhat unexpectedly. And so we think, therefore, that this subject could benefit a lot from some rigorous treatment. But unfortunately, our current developments in theory don't really reflect this reality. Most of the code we write is ill-typed, but conventional language definitions are only concerned with the semantics of well-typed programs. This is made most obvious by the fact that our type systems look generally like some variation of this judgment form. And so the result is that if a type error appears anywhere, as far as the specification is concerned, the program is meaningless as a whole. And so we'd like a way to alleviate this by being able to create precise specifications for the typing semantics of ill-typed programs and localize and recover type errors along the way. And these type checker semantics should describe all well-typed and ill-typed programs. We'll call this notion totality, and it'll sort of guide us as we go along. So this paper is about, we've developed techniques to achieve total type error localization and recovery by sort of elegantly blending local and global type inference techniques. For the former, we present in a sort of tutorial style the marked lambda calculus, which is a judgmental framework for total type error localization and recovery for bidirectional type systems. We choose bidirectional type systems as our starting point because the sort of flow of typing data it creates is conducive, we think, to intuitive error localization. Then we'll describe type pool inference, which is about how to layer a global constraint-based inference system atop the marked lambda calculus in a way that allows us to neatly combine bidirectional and unification approaches for even better localization. So while these two paradigms have been thought of perhaps as opposing or alternative techniques, we'll hopefully see how they can actually complement each other. And hopefully you'll be able to see that these techniques are actually fairly general and hopefully applicable to what you're doing right now. So to start this short tutorial, we'll start with a small, gradually typed lambda calculus with a standard bidirectional type system in which synthesis corresponds to inferring the type of a term from its syntax, and analysis is checking a term against an expected type. And it's important to note that we have the unknown type here, but in fact, it's actually only necessary, as we'll see, for ill-typed programs, handling ill-typed programs only. And we require then only the static semantics of the gradually typed lambda calculus, so no runtime shenanigans going on here. In our standard bidirectional type system, we would probably have a rule that looks like this, incomplete one, for synthesizing the type of a variable occurrence. We can conclude, of course, that X synthesizes type tau if the pair is in context. So hopefully this is straightforward. But the question is, and this is where totality comes in, what if X isn't in scope? And so this causes problems if we were to try to implement this rule, which might look like this OCaml code for synthesis. The none case in the lookup corresponds exactly to being unable to fulfill the premise. And it's really not immediately obvious what we should do in this case. A common approach is to just throw an exception with a diagnostic and leave it to the caller to handle, or similarly by returning an error value. But in either case, we've sort of aborted the type checking process early at the first error, and this just isn't going to cut it for the 21st century. So at this point, we've successfully localized the error, but the question is, how can we actually recover? Given what I said earlier and the fact that this session is about gradual typing, you probably guessed it by now, but it's by using the unknown type. And so the idea is to augment this type checking process with marking, where we localize and report errors by adding these marks, which intuitively correspond to compiler diagnostics or sort of editor decorations, for example. And then we'll use the unknown type, which provides exactly the right mechanisms via consistency to recover in a principled manner. So we'll take the original syntax of the language and add the aforementioned error marks, which are given by these sort of fancy parentheses in red with a subscript. But it's important to note that these are just sort of symbolic representations of actual error messages, which we don't talk about too much. For now, we've added only one error mark, which denotes exactly that the variable is a free variable. So then we'll extend the original typing judgments into these marking judgments, where unmarked terms are marked into marked terms. And these are now the judgments that actually express the error localizing and recovering type checking process. And then the idea is that sort of downstream services, editor services dependent on type information, such as completion, will then be based on these typed marked terms. So thinking about the success and failure cases of this variable rule, we actually get two synthetic marking rules. In the success case, we don't need to mark any errors. Hopefully, this is straightforward. And then in the failure case, when x is not in the context, we'll need to mark x with an unknown, a free variable mark, and then synthesize the unknown type since we don't know anything about it naturally. Another common error occurs when some terms type doesn't match the one that's expected. In a bidirectional system, this commonly occurs when we have some sort of subsumption principle that we want to apply. And we can straightforwardly sort of derive a corresponding analytic marking rule. But again, totality guiding us here. The question is, well, what if the types are inconsistent, like in this example? And just as last time, we'll add a new mark denoting exactly this error. And then hopefully it's straightforward to see how we can derive the second rule on the right here that handles the error case. And again, we'll mark the term with that error mark. And so hopefully these two examples, though they're short, give you a sense of how this framework works. And if we were to continue the development for this minimal language, we would simply follow this pattern. And it turns out you would need this set of marks, which cover the remaining failure cases that would probably arise during type checking. And for the sake of time, I won't cover them, but you can see the full development in the paper. But now the question is, okay, with this development in place, we should be wondering, as researchers, how do we know the recipe? This sort of recipe has given us the right rules and that we haven't made any mistakes. From the start, I mentioned this notion of totality that would guide us. And now we can actually formally state it to make sure we haven't missed any rules. Here's the theorem, and it states simply that every unmarked expression can be marked synthetically and analytically. And of course, there's an accompanying theorem that requires that marking gives us only one result, as one would expect and hope. Secondly, marking shouldn't deform the syntax except by adding marks and removing these marks, which is given by this sort of square superscript erasure operation, should give us back what we started with. And we should also have that marking shouldn't introduce any error marks on well-typed terms because they're well-typed, which we give by this markless judgment. And then there will be a corresponding statement for ill-typed terms, which should have at least one mark. So putting these pieces together, we can view marking as a sort of total function, taking arbitrary terms, well-typed or not, of the unmarked syntax to well-typed terms of the marked syntax. These are then used by downstream services. And this well-formedness theorem from the last slide is exactly described by this identity loop. And all this meta theory is mechanized in Agda, which can be found in our artifact. So the recipe that we've described is you can take your existing type system and formalize how type errors are localized and recovered from. You could start with a non-gradual system, but you'll need to add the unknown type, just the static portions to handle ill-typed programs. And then systematically, considering the success and failure cases, we can derive the marking rules, as we saw. And then it's important to know that all the decisions about how to actually localize were made by us during the process. And so this framework is not really prescriptive with respect to a specific strategy. And in fact, we actually, in the paper, just formalize the sort of three different possible ways to localize errors for inconsistent branches in a conditional, as we saw at the beginning. So since the marked lambda calculus is for bidirectional systems, it might not do everything we'd want it to. In this program, the type of f is given to be unknown, so the bidirectional system operates gradually, but we notice that, well, it's applied as a function, so maybe it's a function, but it's also being used as a number, so maybe it's a number. In other words, there's no way to sort of fill this unknown type or type hole, as we call it, with a known type that would satisfy all the constraints. And we think, well, some sort of global constraint-based inference system would have caught this error. And so the second part of this paper, we're talking about how we can layer constraint-based inference atop the marked lambda calculus to get sort of the best of both worlds, where the latter provides local type inference with error localization recovery. And then type hole inference, as we call the system, solves and marks for these sorts of global inconsistencies. And it's important to note, rather than being a standalone type checker, this is an example of a downstream service that you would use with the marked lambda calculus. And so without getting into the weeds of how this all actually works, we can just, you can refer to the paper for details, but we'll just see how we can take the previous example into Hazel, where we've implemented this type hole inference system. So this is what it looks like. And this is a constraint-based system, so we gather constraints and try to solve them with a unification algorithm. And when unification is able to solve the constraints, we'll proceed as normal to find the appropriate substitution. However, like here, when it's unsolvable, we'll sort of degrade gracefully to maintain these partial solutions, which are all the possible type fillings for the unknown type, which are then offered to the user for selection. And we can see here in this example that we have a red exclamation on sort of where the unknown type would be. That indicates that the constraints are inconsistent. And the cursor inspector tells us that they are and that they're int and int arrow unknown. So instead of failing outright, the inference system collects both these possible type hole fillings and presents them to the user, which we can actually preview by hovering over like this, and then select the one that we actually intend. So for example, when we hover over int, it fills int with a type hole, and now the application of f is marked with an error because actually control has now been returned to the bidirectional system. And likewise, if we hover over the other one, now the second usage of f is marked with an error. And so the nice thing about this approach is that it's neutral in the sense that we don't try to guess about user intent, but simply offer all the possibilities to the user for selection. And this facilitates a sort of workflow of filling in type holes and then returning control to the bidirectional system. And it turns out that these bidirectional and unification approaches can actually work together quite nicely. And so there's, of course, more in the paper. Please consider trying using these techniques in your next language, or tooling or editor support for your next language. And if nothing else, we hope this work spurs more work about the semantics of ill-typed programs. Thanks.
Okay, questions from the audience?
Hi, Eric.
Hi.
So this kind of process, I think, was previously used in parsing, where it was discovered that, like, by manually encoding all of the incorrect paths, you can produce really good error messages for people, which is really great. But then it requires, like, the implementer of a parser to, like, write a lot of extra code, and people just generally don't like doing that. So I'm kind of like, at a first approximation, it kind of seems like this more or less requires doubling the number of, like, judgment forms that you have to write in your language for your semantics. And if you have, like, a sufficiently complicated language, that could be, like, a lot. And I'm just curious if there's, like, maybe forward-thinking work about, like, figuring out how to, like, optimize or, like, choose specific things that you want to, like, focus on, or, like, automate it or something. ChatGPT it, I don't know.
Yeah, I think hopefully it was evident that this recipe is really not complicated at all. And because of that, I think there's certainly possibility for some level of automation. But of course, the language designer or the tooling designer is going to have to decide how they actually want to localize these errors. And so there needs to be some sort of user input from that. Yeah, it's definitely true that you have to write a lot more rules, but hopefully you saw that the rules really mirror the original typing rules quite closely. So it's not like we're coming up with a whole new half of the system from scratch.
And hopefully worth it.
Yeah.
Hi, this is a really great work. It looks very clean. I'm really curious, why has this paper not been presented at POPL 20 years ago? Actually, I have a real question. What is the complexity, the added time complexity that your instrumentation adds compared with plain typing?
Sorry.
Do you have like results about how much time it takes to run your type checker as opposed to the like naive type checker?
We haven't done benchmarks of that sort, though.
I'm not talking about benchmarks. I'm like complexity. If you have some ideas about like the.
I mean, so it does, since if you're referring to the marked lambda calculus, right? It's bidirectional, so it does the same bidirectional traversal that a traditional type checker would do. So I don't see any reason for it to be.
For example, if you collect the types of all the variables, maybe it's more costly. You need more data structures or to check things. I don't know. I'm asking if it's the same complexity or if it's going to be more.
I think it should be the same.
Yes, thanks.
Hey, very nice talk. Yeah, I think this is an interesting area. My advisor used to do work in, if you had ill-typed, like type inference constraints, kind of changing and removing types to try and suggest things that would unify. And there's like a lot of spaces of solutions in that context, but I
Yes.
don't know how many there are here. But along those lines, have you like thought about like, I don't know, machine learning or something else to kind of give recommendations of like, you may want to use this to kind of fill your holes?
So are you specifically, so I guess for the latter system, type hole inference, yeah, we've definitely looked at sort of the body of work that exists for that, and people have used various techniques and methodologies to determine how they should, like where they should localize inference errors to. We haven't, we're not so much, I guess the approach we've gone for is trying to be as neutral as possible. So we're not trying to guess where the user is intending by perhaps saying, oh, they use this sort of, this constraint appears more, so maybe that's what they intend. But simply offer all the possibilities to the user so that they can actually select what they intend.
Have you like put it in novice programmers' hands and seen if they got decision paralysis or anything?
We haven't yet, but yeah, we're hoping to actually incorporate this tooling for the class that we're teaching.
All right, thanks.
We're here. Have you considered adding, instead of making more type rules, adding slack variables to the unification equations that you derive? And then when the slack variables are filled, you can actually pinpoint the holes, the problems that there are in your code. So slack variables are an old, a bit of background. Unification is approximately generalization of Gaussian elimination on abstract trees, right? And in Gaussian elimination, you use it for optimization problems. And optimization problems typically use slack variables to turn inequations into equations. You can see an ill-type program as an inequation, and then add slack variables, and then the slack variables, when they fill up, as opposed to staying empty, point exactly to the same places. As a soft typing experience by Fagan and Wright, who based their work on Didier Remy's record calculus.
Okay, I don't know too much about that. We haven't thought about that, but that sounds like it could be an interesting avenue.
And last question.
Hi.
Hi.
I'm kind of curious. Here in your marked on that calculus, it's kind of a simple thing. You only need consistency. But I guess if you wanted to apply these kind of techniques to fancier type system, you need to gradualize them in some way. So you need to get the equivalence of consistency for whatever crazy relation your type system is using, right?
Yeah, so the sort of caveat of the marked lambda calculus is that, well, first of all, you need a bidirectional system. And second of all, you need these like gradual typing mechanisms. So, you know, if you had a sort of gradual version of whatever fancy type system you're thinking about, maybe a gradual dependent type system, like if you already have this type system, you can then, based on whatever constructs you have there and whatever rules there, you just need to consider sort of the failure cases and then derive the rules. So yeah.
Thanks. That's very nice.
Okay, let's thank Eric. Okay, that concludes this session, and we are going to transition immediately to Philippa.
Please move into the middle, away from the aisle, so that other people can find seating. Thank you.
So we're at the end of POPL, and thank you, all of you, for coming. I've had a real buzz all week. It's been great. And I've got some thank yous. So I'd first like to thank Derek Dreyer, who has not just been the most wonderful PC chair, but also has been helping out right the way through, whether it would be a few months ago or working hard this week whenever it was needed. He's been fabulous. I'd also like to thank this absolutely fabulous AV team And you saw this photograph yesterday. The coming in to a place like this, where they have the normal way for them to do it, and to hook in to the POPL AV way of doing it. That has been, you know, I think you've seen there's been some teething problems every so often, but both teams have been absolutely super in terms of sorting them out. So thank you very much to them. We got this, yeah. We've got the fabulous student volunteers, and I have a slide now. So they've been brilliant. And I don't have a slide of the IET team. I'm just going, bother, I wish I had a slide for the IET's team. They've been great all the way through. And in particular, I'm not sure whether you know, they're very pleased with themselves this year because they've got the award for the best venue in London for 500 people. Yeah, they're a bit constrained on the 700 plus people, but 500 they've got the award. But they're more proud of the fact that they've got the award for the best team. And they are absolutely sort of very positive about it being a team effort, whether it be the organizational management or the food or the AV. And I think they've done an absolutely fantastic job. So please can we thank them. Now, Peter Chairman asked me if I would be chair of POPL'24. And as I'm sure you can appreciate, in some sense, my face fell in the sense that, oh my goodness, what a lot of work. But actually, 20 years' time, I am going to have a huge positive memory of the most wonderful meeting that we've done here. And absolutely, it's down to the vibrant spirit and positivity of this POPL community that's absolutely fantastic. So whether you're an experienced person that's been here for decades, or whether you're the young person just starting and wondering whether to get into this field, I hope you've loved this meeting and want to continue the enthusiasm for the next few decades. Thank you so much for coming. So we're at the end, and now see some of you, perhaps most of you, tomorrow. Bye-bye.